Hi everyone. So now we are going to watch this 9 hours of marathon on BJTs. So it will be starting at 11 a.m. and it will be ending at 8 p.m. So in this 9 hours we are going to cover everything that is required for your placements or for your gate examination from bipolar junction transistor. Okay, there can be some written test question or some question can be asked in interview as well, or some question can be asked in gate examination as well. So there can be some questions that you need to encounter from bipolar junction transistor that we are going to study in this particular lecture. Okay, and this guarantee I can take. If you study this 9 hours of lecture, after that you will not have to refer to any resources, and every single question you will be able to solve which has been asked in your particular examination, be it your written test or your gate examination. Okay then, so we are targeting a subscriber count of 9,000. With the end of the video we are targeting a subscriber count of 9,000. So I hope we will be able to reach the target. We roughly need 200 subs. So 200 subs we roughly need, and at 12 a.m. or at 11:59 p.m. I will have to make this video private. Okay, because this is a part of paid course. But if we get enough subscriber, we will get good amount of motivation. If we achieve this target, we will get good amount of motivation. If we are getting good amount of motivation, then certainly we can think of extending it a bit more. But if we are not getting enough viewers, if we are not getting enough subscriber, if we are not getting enough likes, then we might lose our motivation and we have to make this video private. Okay, because a lot of students are studying this from paid course, so that thing we need to consider. Okay then, so let's start studying our bipolar junction transistor. And one more thing, before watching this video you should have a basic idea of MOSFETs. Okay, basic idea would work. If you know basics of biasing, if you know basics of amplifier, then that would be enough, because I am correlating a few things from MOSFETs to BJT. Because in our course, first we have studied diode circuit, then we have studied MOSFETs, then we have studied op-amp, and then we are studying BJTs. So I will correlate a few things from MOSFETs, because MOSFETs are more important topic than BJT. That's why I covered it before BJTs. Okay, MOSFET have been already covered, so we will correlate a few things. So that basic idea you need to have. If you just have the basic idea, then you will be able to understand it. Okay then. So yeah, thank you very much. Let's start studying our chapter, that is bipolar junction transistor. And just one more update. So if you are someone who is looking to prepare for GATE 2025 examination, then you can prepare with us with our course Road to IIT/IISC GATE 2025. Here we are starting right from the zero, and we are going to cover everything that is required to get the admission into IITs or IISC. So we will be targeting a rank around 1000, because in 150 days, if we are starting right from the zero, so this is what we can target. So recorded video lectures are there, test series are there, class notes are there, one-to-one live session is there. So you can watch the launch video before enrolling in the course. Deadline to enroll in the course is 3rd of September, because after that we will not be able to guide you personally, and after that we will be closing the enrollment as well. So do watch the launch video. Here I have told everything, price plan, what you will be getting in refund, what we are going to deliver in this particular course. So do watch the launch video, Road to IIT/IISC in 150 days from zero, PrepFusion. So this launch video, if you watch, you will have a clear idea of what we are going to cover in this particular course. So if you are looking to prepare, if you are starting right from the zero now and you're looking to prepare for GATE 2025, then you can prepare with us with this particular course. Now let's start with BJTs without any delay. Okay then, yeah. So let's start. Hi everyone. So today we are going to start BJTs. So we have already covered MOSFET, we have already covered op-amp, we have already covered diode. Now we are going to start BJTs. But in the BJTs, we are not going to cover very in depth of BJTs. Okay, because when we studied MOS, we covered very in depth. We saw the device physics, we saw the biasing, then we studied the DC analysis, then we studied the AC analysis. And in AC analysis, we saw different kind of amplifiers. Why we are not covering BJTs in depth? Because it is not asked that much in the examination. Okay, they don't ask that much of BJTs in the examination. Why they don't ask? Because BJTs are not being used nowadays. Only in high frequency circuits sometimes you can see BJTs, but mostly for amplifier purposes MOSFET will be used. So industries are using MOSFETs only. Even if you go to M.tech, so there also you will use different kind of FinFETs or MOSFET. So there also MOSFETs are used. That's why we are going to cover only MOSFETs, not the BJTs in depth. But whatever that is required for your written test, whatever that is required for your interview, whatever that is required for your GATE examination, certainly everything that is required, we are going to cover that thing. Much more than whatever that you require, that will be covered. So you don't need to worry that if I know complete BJT or not. Whatever that is required, certainly I am going to cover. Much more than that I am going to cover. Okay, so no worries about that. Let's start the BJT. We will start by comparing MOS here and BJTs here. So how many types of MOS we studied? Two types of MOS we studied. NMOS and PMOS, right? Here also there are two types of BJTs, NPN, NPN and PNP. Okay, this is BJT, bipolar junction transistor. Why it is known as bipolar? Bipolar. In MOSFET, what did I tell you? What did I tell you? That always there is only one charge carrier. If I am talking about NMOS, the electrons are the charge carriers because electrons will flow like this from source to drain. And if I talk about PMOS, holes were the charge carriers, right? Holes were the charge carriers. So only one charge carrier was there. Here in NMOS, this is the P substrate. But it is not contributing in charge carriers, right? It is not contributing in the current. That particular hole is not contributing in current. Only the electrons are contributing in current. So there were only one charge carrier. In this case, both electrons and holes will travel. Both electrons and holes will be moving and both will be contributing in the current. That's why it is known as bipolar. So two charge carriers are there, electrons and holes. So this is a very good interview question. Sometimes in the PSU it can be asked like why it is called bipolar. So some people think that there are two junctions. That's why it is known as bipolar. No. There are two charge carriers. That's why it is known as bipolar. And in case of MOS, there was only one charge carrier. So bipolar. Why it is called bipolar? I am just going to write two charge carriers. You will understand it. Two charge carrier. Electrons and holes. That's why it is known as bipolar. Okay. What this node was there in NMOS? This node was known as gate. This node was source and this node was drain. You should have a very clear idea of MOS. If you have the very clear idea of MOS, you will be able to understand it very quickly. And this is your N channel. Generally, BJTs are taught before MOSFET. This should not happen. This should change, because if you know the MOSFET, BJTs will become very easy. BJT is tougher than the MOS. Okay, this is the actuality. BJT is tougher than the MOS because there is one extra component would be coming. So that I will tell you what is that extra component. Now this is the structure of BJT. NPN we are studying. Here we studied about NMOS. So here we are studying NPN. Then we are going to study about PNP. In the same manner, in the MOS we studied PMOS. So first we are going to study NPN. Then we are going to study PNP. Okay. This particular node, this is known as emitter. So what is this structure? N-type substrate, N-type semiconductor, then P-type semiconductor and N-type semiconductor. All are clubbed together. NPN. N-type semiconductor, P-type semiconductor, N-type semiconductor. Okay. This is base and this is collector. Emitter, base and collector. Emitter means emits. It emits the charge carriers. In base it stays there and collectors collects it. On a very crude level, I am telling you. I am not going in depth. On a very crude level, on a very basic level, I am telling you. Like when we study device physics, I will certainly tell you how the current flows, what is the equation of how do we get the equation of current, why it is exponential. Everything we will tell in the device physics lectures. But here, whatever that is required as an analog engineer, as a subject of analog electronics, whatever that is required, that we are going to cover. Okay. So emitter, it will emit the charge carriers. In the base, the charge carriers will stay, and in the collector, the charge carriers will move and the complete current would flow. That's it. Okay. So now, what do you, by watching this structure, by seeing this structure, what is the cross-section area of collector, base and emitter? Like which cross-section area is the maximum? Which of them is having the maximum cross-section area? What do you think? By looking at the structure, collector is having the maximum cross-section area, then emitter is having the next one, and base is having the least cross-section area. Say yes or no. So collector will have the maximum, then emitter, and then the base. Okay. Now my target is the current should flow. This is my target, right? My target is current should flow. So I have to give some bias here, right? I have to give some bias, because if there is no bias, even in the diode, if there is no bias, current doesn't flow. This was your PN diode. If there was no bias, the current would not flow. Bias means simply giving some voltage, simply giving some supply. So that we have to give. We have to give some supply. What do you think? Which supply I should give to these two terminals for the current to flow? For the current to flow, which supply I should give? if I apply positive here and negative here, do you think current will flow? Because what are the majority here? Electrons. If I am applying positive, what will happen? Electron will come here, right? But my target is electron should move towards the collector. From the emitter, electron should move towards the collector. So what do you think? What should I do? I should apply negative here. I should apply negative here and positive here. So what will happen? The electrons will move from here to here and holes will move from here to here. Say yes or no? Now those electrons that are moving, that has come here. These electrons have moved and come here. On a very crude level we are studying. Now what do you think? What should I apply here? If I need to attract the electrons, what do I need to apply? Positive. Say yes or no? So I need to apply a positive to attract the electrons. And here I will apply negative. So basically these two NP, this is forward bias and this is reverse bias. If I am doing this thing, then the current is flowing. Right? Now even if this was forward bias and this was reverse biased, because at N you are applying positive, at N you are applying positive. So this is forward bias and this is reverse bias. Actually this can be taken as a reference. Base can be taken as a reference, base can be taken as a ground. So if base is grounded, then here you are applying negative and here you are applying positive. So what do you understand by that? That your collector is this junction PN. This particular PN junction is reverse biased and NP is forward biased. So this is the most important condition, that this much of part should be forward biased and this part should be reverse biased. So in that a good current will flow. But now even if you apply negative here, still some current can flow. This is forward bias and this side is also forward bias. Both sides are forward bias, still the current can flow. Why it flows, how much the current flows, what is the mechanism of that we don't need to study. Okay, even this mechanism are not required, but you should have a crude idea, you should have a basic idea how the current is flowing. What do you need to remember? You just need to remember that this node is known as emitter, this node is known as base, and this node is known as collector. Now tell me one thing, in NPN transistor, electrons are moving in this direction and holes are moving in this direction. So what will be the direction of current? Electrons are moving in this direction, you applied some bias, the electrons moved in this direction and holes are moving in this direction. So what will be the direction of current? The direction of current will be, if you talk about holes, the direction of current is the same as the direction of the movement of holes. The direction of the current is same as the direction of movement of holes. So this will be the direction because of holes. And because of electrons, the direction of current is opposite to the movement of the electrons. The direction of current is opposite to the movement of the electrons. Electrons are moving in this direction, so the current will flow in this direction only. So because of electrons and holes, both the currents are flowing in this direction. So current is getting out of emitter. The current is getting out of emitter, right? So the current is getting out of emitter. So on a very basic level, we have understood what is happening in case of BJTs. So in case of BJTs, the current will get out of emitters. The current is getting out of emitter. And here, this will be the collector current and this will be the base current. Look, the current was flowing in this direction, right? So you can tell it, this is the collector current, this is the emitter current, this is the collector current. Now from where this current is coming, because all the electrons are moving here, right? But some of the electrons will have this trajectory as well. Okay, some of the electrons will have this trajectory as well. So because of that, base current is flowing in this manner. So on a very crude level, we are studying it. That's why you might find it like you are not able to understand it. But whatever that is required, that will certainly come to you when it is the time. Okay, on a very crude level, I am telling you that this is the collector current, this is the emitter current, this is the base current. So basically, what do you need to remember from this? So on a circuit level, we need to remember. This is how we will show your transistor on a circuit level. On a circuit level, this is how BJT looks. So this is a BJT. You don't know whether it is PNP or NPN, which node is emitter, which node is collector, which node is base. You don't know anything. So I will tell you how to recognize which node is what. So in that case, you just need to see this particular node. This is base, which is common to both of the junction. So this is base. It was gate in the previous case of NMOS. So this node is base. Now wherever you see the direction, this this direction, wherever you see this direction, this node is emitter. Wherever you see the direction of this arrow, that node will be emitter, the other one will be collector. It was the same case in case of NMOS as well. Wherever you see the arrow, that was source, and other node was drain. Same in case of PMOS as well, right? Wherever you see the arrow, this was source, and the rest was drain, and gate was this one, right? But in this one, what we said, the one which is at higher potential, that would be source, and one which is at lower potential, that would be drain in case of PMOS, and in case of NMOS, one which is at higher potential, that would be drain, and the other node will be source. But here this is not the case. Always this will be emitter, always this will be collector, and always this will be the base. Always, nothing will change. In case of BJTs, the drain, in case of NMOS, drain and source were interchangeable, but in case of BJTs, emitter will be emitter only, collector will be collector only, base will be base only. Well and good. No issue about it. And if I make this structure in front of you sometimes, let's just say I have made this structure. I have made this structure in front of you. What this will be? This will be base only. There is no doubt about it. The arrow, this is the arrow sign, no? This is the arrow sign. So if this is the arrow sign, then this will be emitter and this will be collector, right? So that would be your NPN, PNP actually. Now you don't even know whether it is NPN or PNP. So how will you recognize it? You will see the direction of arrow, right? This is the direction of arrow. In the direction of arrow, you will write P to N, because this is just a way to remember. Otherwise, like people will tell you this is the NPN transistor, you have to remember. But you, by looking at the circuit, by just looking at this particular block, how will you tell which kind of transistor it is, NPN or PNP? So how will you remember? You will see that this is the arrow direction. So if this is the arrow direction, that means this node will be P and other node will be N. This is the arrow direction. Just a way to remember. Arrow direction is this, so P to N. So this is P, this is N, then this will be N only, because there is no PPN transistor. There is no NNP transistor. There is PNP or NPN. So if you have recognized this is P and this is N, then certainly this will be N only, no? Right? So this is NPN transistor. So this is how you can remember it. Did you understand what did I tell you? So let's see everything again. So this was one transistor, this would be other transistor that we are going to see later on. So what did I tell you? You need to see the arrow sign. This is the arrow sign, this is emitter. This will always be base and other one will be collector, right? Now which one will be P, which one will be N, you don't know anything, and you don't need to mug it up as well. What you will do, sir, that this is the arrow direction, so from P to N there is a current, so P to N. It's not that the current is flowing in this manner, no, nothing like that. This is just a way to remember. The arrow direction is this, so this will be P and this will be N, so other one will be N. Now tell me, in this one, this will be emitter, this one will be collector, and this one will be base. No doubt about it. Which kind of transistor is that? This is the direction. This is the direction, P to N. If this is P, this is N, this has to be P only, because this cannot be N. So NPN transistor, PNP transistor. This is how you can remember. Okay. So you don't need to mug up anything. See the arrow direction, that would be emitter, other one will be collector, base is the side one. In the arrow direction, you can write P to N. The other one, upper one will be N only. Well and good. Everything is crystal clear, no doubt about it, right? Now let's show the current. What is the direction of current? Arrow, you see, arrow. So this will be your emitter current. This will be your emitter current. Now all the currents will flow in the direction of emitter only. So this is your emitter current, so this will be your collector current, and this will be your base current. The target is to go into collector only. This is the collector current. IE current, you know, from upper IE current, IC current would be coming, and from here IB current would be coming. What was the scene in this one? Here this current was 0 only. The gate current was 0. The gate current was 0, and the complete MOS was driving one current, that was ID. But here the base current is not 0. So what is the scene here? That your IE current, so let's write it here, that your IE current is equals to IC plus IB. This is the scene, that your emitter current, that is equals to IC plus IB. Now if you see this PNP, if you see this PNP, if you see this structure, what you will do, this is emitter, this is collector, this is base. From P to N, P to N, the arrow direction is P to N, so this will be P only. Well and good, no doubt about it. What is the direction? This is the direction. So this will be emitter current, this will be collector current. The target is in the emitter current, both current will be added. So what will be the direction of base current? This will be the base current. Because this is the arrow direction. Emitter current is coming, base going here, IC going here. So IE is equals to IC plus IB. The emitter current is equals to base current plus collector current. IE is equals to IC plus IB. It will be applicable in both PNP and NPN. Well and good. Now what is the current equation? So for current equation for collector current is given. For collector current, the current equation is given, that is IC equals to IS exponential e to the power VBE by eta VT. So this is the expression, and this is also an approximate expression. There are a lot of assumptions. After that we derive this particular equation. So here we are not going to see the derivation of this particular equation. Certainly we are not going to see the derivation. Even for this one also we did not see the derivation, because that is not required. That is not at all required. Even for your gate examination, this derivation is not required. Whatever the derivation that is required, that I certainly do. Small signal derivation is certainly required. So that we certainly do. But for the purpose of gate examination, these kind of derivations are not required, because there are a lot of assumptions. In deriving these equations. So that's why always this sign should be there, that this is not completely equal, somewhat equal, right? What is IS? Reverse saturation current. IS is the reverse saturation current. Reverse saturation current. In diode circuit, we studied about reverse saturation current, right? In diode circuits, we studied about reverse saturation current. Like even if there is forward, even if the diode is forward biased, there will be some current flowing in the opposite direction. That is known as reverse saturation current. So IS is reverse saturation current. What is beta? Thermal voltage. Sorry, not beta. What is VT? VT is thermal voltage. Do you guys remember VT? VT we have used a lot of times in analog electronics course. VT 26 millivolt. VT is generally equals to 26 millivolt at 300 Kelvin. Okay, if you don't know, I will write it down. What is VT? Here we can write down. What is VT? VT is thermal voltage. Okay, and VT is proportional to temperature. VT is proportional to temperature. It is proportional to temperature. And also one more thing. What is that thing? That VT is equals to 25 or 26 millivolt. 25 or 26. Okay, 25 or 26 millivolt. So I am writing 25 millivolt at the rate 300 Kelvin. At 300 Kelvin. So VT is 25 millivolt at 300 Kelvin. VT is known as thermal voltage, that is proportional to temperature. If temperature changes, VT will rise. Okay, if temperature rise, VT will rise. VT is known as thermal voltage. VB, you know, this will be between base and emitter. Whatever the bias you apply between base and emitter, that would be your VBE. So this will be your VBE. VBE divided by eta VT. Okay, and the other thing you got to know, that the collector current is equals to IC plus IB. One more thing is there is a relation between IC and IB as well, because we have three variables, IE, IC and IB. If we know one of the value, let's just say we know the IC value, but we are having two equations now. We need one more equation to determine all the variables, right? We have the IC equation, we have one more equation, that IE is equals to IC plus IB. If I know one more expression, then I can write down IE, IC and IB, all the values, right? So the other expression would be IC equals to beta AB. So there is a relation between IC and IB. So on the next page we can see this relation. Okay, on the next page we will see this relation, IC equals to beta AB. On the next page we will see it, but let's just write down other things. So this was your equation for saturation region in case of NMOS. In case of NMOS, the condition was your VDS should be greater than VGS minus VT. Drain to source voltage should be greater than a particular voltage. Your drain to source voltage should be greater than a particular voltage. Here also there is a condition that your collector to emitter voltage, VCE, this should be greater than a particular voltage that is known as VCE set, then only this equation holds. So this equation holds only for a particular expression, that is your VCE, your collector to emitter potential, emitter potential should be greater than a particular potential that is known as VCE set. So generally VCE set value is 0.2, that we will see later on. We will write it down, but your VCE should be greater than a particular potential, then only this equation will hold. The same thing we have studied in BJTs as well, in case of NMOS or PMOS as well, that ID equals to mu n CoX W by 2L VGS minus VT square is only applicable if your VDS is greater than a particular voltage, that is VGS minus VT. Say yes or no. Same thing here, IC equals to IS e to the power VB upon eta VT, that is applicable if your VCE, if your collector to emitter voltage is greater than a particular voltage that is known as VCE set. So IS is reverse saturation current here, VT is thermal voltage, I is equal to IC plus IB. There is one more relation, IC equals to beta IB. Right? Now one more thing we forgot to write. What is that? Here we are not having the space. Can I generate some space? Let's check that out. Yeah. So this was the ideal current, right? Ideal current. But always there is some non-ideality, that is this one. So that we have studied in MOS, that mu n CoX W by 2L VGS minus VT whole square. That is there if there is no channel length modulation. If there is channel length modulation, if this is a practical MOS, then 1 plus lambda VDS factor also comes. So this ID current in saturation region is not always constant. It depends on this VDS potential as well. It depends on the output potential, VDS potential, this VDS potential as well. So similarly here you feel like that the IS, if I fix this VB potential, then my current would be constant, my IC current would be constant if I fix this VB potential. This is what I think, but in a practical case, what is the scene? That your IC current is not constant. This expression is the same, IS exponential VB upon eta VT. There is no doubt in this expression, but it will depend on VCE as well. So that is known as 1 plus VCE by VA. So this is the actual final expression for practical cases. So IC equals to IS exponential VB by eta VT into 1 plus VCE by VA. Right? VA is known as early voltage. Here I can write VA is early voltage. VA is known as early voltage. So these are the things we have studied. You can see it on a complete block level. This was our BJT. We will see it. This is NPN. P to N. We have the arrow direction. We have the collector current, base current, and emitter current. So emitter current is equals to collector current plus base current. Emitter current is the maximum. Okay. This is the father of everyone, daddy of everyone. IE. That is the maximum. I equals to IC plus IB. What is IC? IC is IS exponential VB by eta VT. What is VT? Thermal voltage. Right, and thermal voltage is proportional to the temperature, and thermal voltage value is 25 millivolt, approximately 25 millivolt at 300 Kelvin. If temperature rises, the VT value will also rise. But this was the expression, this was the ideal expression, and this is applicable only when your VC potential is greater than VC set. VC potential is greater than a particular voltage. VC should be greater than VC set, then only it is applicable. Same in the case of NMOS as well, that ID equals to mu n CoX W by 2L VGS minus VT square is applicable only if your VDS is greater than VGS minus VT. Right? This was the ideal case. In case of practical case, we have seen that in saturation region the current is not constant. In the saturation region, what happens? It depends on the output potential as well, that is VDS. So here it will also depend on VCE. So that would be IS exponential VB by eta VT into 1 plus VCE divided by VA, where VA is early voltage. So you can see the analogy, right? VA is equals to 1 by lambda. Do you understand it? Here VA is equals to 1 by lambda. Can you understand this analogy? The same expression into 1 plus lambda VDS, output potential, that was output supply VDS. The same thing, VCE by VA, from collector to emitter bias divided by VA. That's it. Output divided by VA, it was multiplied with lambda. So lambda can be taken as 1 by VA, right? Or VA can be taken as 1 by lambda. So with the analogy, we can compare both of the things. The only thing is this gate current was 0 here, but here the base current is finite. That is very low. Base current is very low, but that is finite. So let's see the relations. So I is equals to I is equals to IC plus IB, that we already know. One more relation is there, that is IC equals to beta IB. What is beta here? What do you call beta? Look, in this expression, collector current is not coming. In this expression, this is the relation between IC and IB. This is the relation between collector current and base current. So what you can call beta? It is known as common emitter. It is known as common emitter current gain. Common emitter current gain. So this is what we call beta. Beta is common emitter current gain. Okay. Like if this node was common, then this was our input current, this would have been our output current. So IC by IB is equals to beta. IC by IB is equals to beta. So beta is known as common emitter current gain. So beta value is typically 100, from 100 to infinite. It can be anything from, actually it can take any value, but beta value is typically high. Beta value is typically high. Beta is typically high. Typically high. Tell me one thing, if from here you can get to know that beta is equals to IC by IB, or you can say IB is equals to IC by beta. If beta is infinity, what will happen? IB will become 0. IB will be 0 ampere. Say yes or no? IB will be 0 ampere, right? If beta is infinity. So if beta is infinity, IB will be 0 ampere. So it will, our BJT will kind of act as MOSFET only, because there is 0 ampere current. So when we will study the AC analysis, in most of the cases the base current will be 0. So in that case, BJT and MOSFET will be nearly the same for the AC analysis purpose, but these expression will be different. IC expression, this current equation, that is different. Here this is the current equation, and here this is the current equation. So final expression, like the gain would be GM R0 only, but the value of R0, value of GM will be different in case of BJT and MOSFET. Are you understanding this point? Because the expressions are different here. Here the expression is exponential, and here the expression was parabolic, right? There was square relation, here it is exponential relation. So IC equals to beta AB. This is what you need to remember. IC is equals to beta AB, and beta is known as the current gain, common emitter current gain, right? So if you put this by equation 1 and 2, by equation 1 and 2, by equation 1 and 2, what you can see? IE is equals to IC is beta IB, right? IC is beta IB plus IB is IB only. So IE is equals to beta plus 1 IB. IE is equals to beta plus 1 IB. This is also you can keep in mind. So basically, if we will be writing some equations, if we are writing some equation and we need to write the complete equation in terms of IB only. Let's just say in our equation, IC expression is also coming, IB expression is also coming, and IE expression is also coming. But we need to write the complete expression in terms of IB only. So what I will do, I will replace IC with beta IB and IE with beta plus 1 into IB. Beta plus 1 into IB. This is the third equation. This is the third equation. This is also you can remember. Sometimes what is the scene is that sometimes this is given that your collector current is alpha times of, your emitter current is alpha time of collector current. And what is alpha here? What is alpha? Alpha is common base current gain. But this expression is very rarely used, very rarely used, very rare. What are the important expressions? These are the important expression. These two are the important one. And this you need to keep in mind that if beta is infinity, then your base current will be 0. This is what you need to keep in mind. So IC equals to beta IB, that is an important expression. IE equals to beta plus 1 into IB, that is also important expression. This is not that much of important. This is not mainly used. Now, do you think there will be any relation between alpha and beta? Certainly there will be a relation between alpha and beta, right? There will certainly be equation, there will be certainly a relation. So if I divide equation 3 by 2, so what I am doing, dividing 3 by 2, so what I will get, IE by IC 3 by 2. What was IE? IE was beta plus 1 into IB, right? And what was IC? IC was beta IB only, right? So now what you will get, IE is equals to beta plus 1 upon beta into IC. So this was 3, this was 4, this was 4, and this is 5. So from equation 4 and 5, from 4 and 5, so what do you see? Alpha is equals to beta plus 1 upon beta. There is some error. Yeah, really sorry for this mistake. Actually, this is IC equals to, this was IC equals to alpha IE. Really sorry for that, because your output current will always be collector current only, no? Output current will always be collector current. Here only we can apply the input. Here we cannot apply the input. In case of MOSFET, I told you one thing, that here only we can apply the input. Either at this node, either at this node. If base is common, then we will apply the input as source. If source is common, we will apply the input as at gate, right? And if drain is common, we apply the input at gate and get the output at source. Similar thing will happen here. If your base is common, you will apply the input at emitter and get the output at collector. So same thing is there, that this is your input current and this is your output current. So IC equals to alpha I, IC equals to alpha I, IC is equals to alpha I, or IC equals to beta IB. So on both of the expression, this is remaining at this side. IC equals to beta IB, IC equals to alpha I. So from equation 1, 4 and 5, what you get, alpha equals to beta upon beta plus 1. So this is the final expression. So alpha is approximately equals to 1 or lesser than 1. Alpha value cannot be greater than 1, because if beta is infinity, what do you get as alpha? If beta is infinity, beta plus 1 can be replaced with beta only, so alpha will be 1. So if beta is infinity, alpha will be 1. If beta is infinity, alpha will be 1, right? If alpha is 1, what do you understand? The IC current is equals to IE only. So if beta is infinity, then what will happen? It's the same kind, like what happens in MOS, the complete ID current flows. So similarly, the complete IC or IE current will flow if beta is infinity. If beta is infinity, from collector current will be equals to emitter current. So complete I current will flow. That can be equals to IC equals to IE. So here I can write in short, or beta equals to infinity. Not here, I should write here. For beta equals to infinity, this current I and this current will also be I, and this current will be 0 ampere. For beta equals to infinity, IC equals to IE equals to I. This is the same, right? So in conclusion, what do you need to remember? In conclusion, I can write the conclusion. So only thing that should be remembered is IC. First thing is that IE is equals to IC plus IB. What is the next thing? IC equals to beta IB. What is the other one? IE equals to beta plus 1 into IB. And if in the question alpha value is given, we will convert that alpha value to beta. Let's just say alpha value is given 0.99. What will be the beta value? Beta value will be 99 only. If alpha is given 0.99, what will be the beta value? You can calculate it, because if beta is 99, what you will get? 0.99 only. So that would be the answer. That's it. So these things only you will have to remember. That's it, nothing else. And if I make a BJT as well, so in BJT what you need to remember, this node is emitter, this node is collector, this node is base. This current is collector current, this current is emitter current, and this current is base current. What else you need to remember? The IC current equation you need to remember. IC current equation. This is the current equation you need to remember, and that is applicable only when your VC potential is greater than VC set. So till now in this lecture, this is the conclusion of the lecture that we have studied till now. So till now what we have studied, let's see it again one by one. This was the structure. This was on the block level. This was on the structural level. In the circuit, this will be the scene. And how will you recognize which is P, which is N? This is the direction. This is the direction of arrow. So this will be P. I can change the color. This will be P to N, and this node will be P only. Sorry, N only, because NPN is possible. NPN or PNP. From P to N. This is P, this is N, this will be N only. So NPN transistor is there. Well and good. So what is the current equation? What is the collector current equation? That is IS exponential VB by eta VT. But this expression is only valid for VC greater than VC set. For VC lesser than VC set, what is the expression? That is of no use. For VC less than VC set, what is the expression? That is a very, very complex expression that we will not even see in the device physics lecture. Generally, people say that that is equals to reverse saturation current only. Somewhere I have seen this, that VC, if VC is less than VC set, then the current expression will be equals to reverse saturation current. But that is not correct. In device physics, I may tell you what is the what is the use of that particular region. So in the next part of this video, we are going to see the region of operation. So that we are certainly going to see. So this is the current expression, but that is the only for the ideal case. For the practical BJTs, this is the expression, that IS exponential VB by eta VT into 1 plus VC by VA. So on the VC potential as well, your collector current will depend. That's it. Okay. Yeah. So this is what we have studied till now, and then we have studied the relation I equals to IC plus IB, IC equals to beta IB, and I equals to beta plus 1 into IB. And sometimes in the question, if alpha value is given, we can convert that into beta. Well and good. Beta value is generally very high, and alpha is generally equals to 1. That's it. Let's move to the characteristics now. So first we are drawing IC versus VBE, output current versus input voltage. What we are drawing. This is your BJT, right? VBE, base to emitter, and this is collector. So collector current and base to emitter voltage. This is what we are drawing. So this was the characteristics that we have already studied, ID versus VGS. ID versus VGS in case of MOSFET. ID versus VGS. In case of enhancement type MOSFET, this was ID versus VGS. Right. So in this one as well. So in these characteristics as well, what was happening in case of MOSFET? Before VT, the current was 0. So similarly, before a particular voltage of VB, the current will be 0. After that, the current will rise. Here, how did the current rise? Parabolically. This expression was parabolic. The current rose parabolically. The current rises parabolically here. What is the expression here? IC equals to IS exponential VB by eta VT. So here the current rises exponentially. So if this is the parabolic rise, then this will be the exponential rise, no? Because exponential rise is faster. Exponential rise is faster. your function is y equals to e to the power x, other function is y equals to x square. What will be the value of, if I put x equals to 2, what is the value you will be getting here? E square. And what will be the value you will be getting here? This is 4. This is very high value. And let's just talk e to the power 10. And what will be the value for this one? 10 square, that would be 100. E to the power 10 is very, very high. We can take it infinity as well. So e to the power 10 is very, very high. So in exponential, the rise is very fast. But in square relation, the rise is slow. Exponential rise is very fast. So that's why I showed it like this. Okay. Now let's solve a question. From this particular question, I need to make a very important point in front of you. So let's solve a particular question. That is, for 10x increase in IC, what will be the change in VB? So let's just say initially your current was this. IC equals to IS exponential VB by eta VT. This was your current, right? VT you can take 25 millivolt and eta you can take equals to 1. If eta is 1. What is eta? I forgot to tell what is eta. In case of diode, in diode we studied what is eta. Eta is known ideality factor. Eta is known ideality factor. So eta is known ideality factor. Let's forget writing it. Okay, here I forgot and no space is also there. So you should know what is eta. Eta is known ideality factor that we are taking equals to 1. So this will be the equation. Exponential VB by eta VT. For this I am calling it VB1. Okay. For this particular current, your VB was VB1. Now there is 10x increase in IC. Now your current has become 10 IC. So what will be the expression? IS exponential VB2 by eta VT. This is equation 1. This is equation 2. So what you can do? Divide equation 1 and 2. If you divide equation 1 from 2 to 1, 2, 1. You can divide 2 to 1. So what you will get? I am dividing. So 10 is equals to exponential VBE2 by VT divided by exponential VB1 by VT. What I can write it? Basically, what do you understand by this exponential VB2 by VT? E to the power VB2 by VT. E to the power VB2 by VT divided by e to the power VB1 by VT. This is the scene. Now, if it goes upward, what will happen? E to the power VB1, e to the power VB2 minus VB1 divided by VT. So now this will go upward. So 10 would be equals to exponential VB2 minus VB1 divided by VT. Right? So what you will get? What is the change in VB? VB2 minus VB1. That would be VT ln 10. And if you put the value VT ln 10, where is my mobile? As far as I remember, it comes somewhat around 0.06 volt. Let's check. So after solving, you get somewhat around 57 millivolt. 57 millivolt. 57 millivolt. So your change in VB was 57 millivolt. This was your change in VB. 57 millivolt. Let's just say this was your VB1. This was your VB1. And it was some, let's just say it was some 0.7 volt. And this was your IC1, initial IC you can say. Now the current changed to 10 IC. So where will be 10 IC? 10 IC will be somewhat like here. 10 IC in the Y scale. 10 IC will be very large. So let's just say this was your 10 IC. But 10 IC will be more above, right? So like, what do you understand? The current changed by 10 factor of 10. But VB changed very, very little. Only by 60 millivolt. 10 changed by a factor of 10. Sorry, the current changed by a factor of 10. But the VB value changed by some 60 millivolt only. So there is a very small change in VB even if the current IC is changing. The IC current changed drastically, but there is very small change in VB. So generally in the questions you will see that VB value is taken as constant. VB value will be taken constant. VB value doesn't change. So in the question they will give you a fixed VB voltage. What is the reason behind that? The reason is, even if there is a drastic change in IC, still the VB value changes very little. We take a very high change in IC, we take a change of 10 times, but here what did we see? We see that the VB value changes very little. So this is also a very good interview question. In the interview, they will ask you that, first they will ask you, draw the IC versus VB curve. You will draw like this. Then they will say, look, your IC is increasing, but why in the question sometimes you see that VB potential is constant? Why is it so? Why do you take VB to be constant, that is equals to 0.7 volt? Generally in the question, VB is taken as 0.7 volt. It can be taken anything, but generally in the question, VB is given constant, that is 0.7 volt. What is the reason? That even if there is a drastic change in IC, there is a very little change in VB. Now, if someone has studied MOS, what did I tell you? What is your transconductance? That is equals to change in output current with respect to change in input potential. Output current IC with respect to change in VB. This value is very low, even if this value is high. So what do you think? What is the GM value? Look, if you change very little in VB, there will be very high change in IC. So GM value is typically very large for BJTs. Here there was square relation, so it wasn't that large, but for BJTs, GM value is typically very large. Did you understand this point? So sometimes this is also asked in the interview, that in case of BJT, they will give you a BJT, they will give you a MOSFET. Then they will make you compare the GM values. So in case of BJTs, GM value is typically very large. This is, we are not going to write here. When we study the small signal analysis, we are certainly going to write it, and we will see a very good question as well. But just here I made this point, so I took this particular point. So GM value is typically large, and here what did you understand? That even if there is drastic change in IC, the VB changes very little, and if VB changing very little, that means the VB value can be taken as constant. That is sometimes taken as 0.7 volt. Mostly it is taken as 0.7 volt. Okay, so here I can write as a conclusion only that in the question, typically VB equals to 0.7 volt. But you always need to read the question what VB value they are giving. Not blindly take any value. Okay, you shouldn't take any value blindly. You should always read the question, because in GATE 123 there was a question in electrical engineering question paper. They asked the DC analysis of BJT. There they took VB value to be 0 volt. Okay, VB value to be 0 volt, not 0.7 volt, not 0.6 volt, not 0.5 volt, 0 volt only. So you have to take care. But VB value you can take always constant. Okay, so this was the first characteristics. I hope you must have understood it. So IC versus VB curve we have drawn. Now what we are going to draw? In MOSFET we draw two curves, ID versus VGS and ID versus VDS. ID versus VDS. Here also we are going to draw two curves, IC versus VB and IC versus VCE. IC versus VCE. Output, between output and output. IC versus VCE. This is your base, this is your emitter, this is your collector. This is your VCE. This is your IC. So IC versus VCE, right? So here in this one, first it linearly rises and then saturates. So this region is known as linear region, and this region was saturation region. Similar thing will happen here. First, what will happen is that if your VC is greater than VC set, if your VC is greater than VC set, let's just call this potential as VC set. If your VC is greater than VC set, then your current will be constant, right? Because this expression will be valid. This expression will be valid if your VC is greater than VC set. VCE is greater than VC set. Why your current will be constant? Your current will be constant with respect to VC, because after that your current is not depending on VC. Even if your VC is getting changed, the current will still be same, because this current is independent of VC. So if your VC is greater than VC set, then your current will be constant with respect to VC, not with respect to VB. With respect to VB it can change, but it will change very little. But with respect to VC it will be certainly constant, because it is not depending on VC. Say yes or no, right? It is not depending on VC, that's why it will be constant. But let's just not put the box around it. Can I remove the box? Yeah, I need to remove the box. Why do I need to remove the box? That you will understand. Here I will write VC is greater than VC set. So current will be constant. So I can make a constant current that would look something like this. I can make the constant current, and before that it rises very little actually. The current rises very little, like this. I can show. I shouldn't show it linearly. I will just show something like this. It rises like this. Rises very little and rises like this. Okay. So this will be your, here this particular region is known as active region, and this particular region is known as saturation region. Isn't it surprising? You will say, sir, current is increasing. How are you calling it saturation region? And why this region is called as active region? So why it is called as saturation region, you don't need to worry about it. Okay, no need to worry about it. If you want to learn it more, if you want to learn in depth, then certainly EC student will learn it in device physics. There is very good concept behind all these kind of characteristics. We will develop the characteristics right from the scratch once we study EDC, electronic devices. But in the interview, it is not that important. It is not important that they are going to ask you the device physics. Okay, so no need to worry. Till now, till this point, if you know this thing, that this will be the characteristics, you know one thing, that if VC is greater than VC set, like for analog designers, this region is not even important. For if you are studying analog electronics only, so for analog designers, this region is not even important, because they will drive their amplifier in this particular region only. So we will always talk about active region, not about saturation region. Okay, we will always talk about active region, not about saturation region. So for saturation region, what do? They take a fixed VC voltage. Like this VC set potential is generally taken as 0.2 volt. Sometimes they can take it 0.7 volt as well. It is not fixed, but generally they give a fixed voltage. That if your transistor is running in saturation region, that means if your VC potential is lesser than 0.2 volt, if your VC potential is lesser than VC set, then you can take your VC voltage to be fixed. For this region, you can take your VC voltage to be fixed, that is equals to 0.2 volt. Are you understanding this point or not? So this particular region, I hate this one. After this particular region is known as active region, and before one, that is known as saturation region. Why it is called active? Because in this region we are going to use our BJT as an amplifier. And why we are going to use our BJT as an amplifier? Because what we want our output current not to be dependent on the output voltage. We want our output current not to be dependent on our output voltage, because here this will be our output voltage and here we will be collecting our output. So if our output current is depending on the output voltage, then your output will keep on changing. No, but if you want a constant output, your output current should not depend on your VC potential. This is what you want. Similarly, here in this region we bias our transistor, because we want our output current to be independent of our output voltage. The same thing we are doing here. So this is our active region. This is not known as saturation region. This is known as active region. So in active region, the current is constant like this. So I hope you are understanding the concept. But what is the scene? The scene is something different. Similarly, here there was 1 plus lambda VDS. So sometimes output current depends on your VC potential as well. That depends on this manner, VC by VA. So if your VC is equals to minus VA, then your current will be 0. If your VC is equals to minus VA, then your current will be equals to 0. So this was the ideal curve, but this will be the practical curve. This will be the practical curve. If your VC is equals to minus VA, VC is equals to minus VA, then your current will be 0. This is how the practical curve will look like, right? Now for different, this was your curve for ID versus VDS for different VGS value. If your VGS value increases, then your current increases. If your VGS increases, then your current ID increases. So here, what did you understand? That your VGS3 is greater than VGS2 is greater than VGS1, right? So similarly here as well. Wait, there is a outside noise, so I have to stop the video. Yeah, so the noise is on. So this will be the characteristics for different VBE potential. So this is, let's just call this one as VB1, this one as VB2, and this one as VB3. So ideal characteristics we are drawing, if it is practical, then it would be somewhat like this, right? There will be some slope because it will depend on VCE potential. But since this is ideal, it is not depending on VCE potential, so it will be somewhat like this only. So here, what do you understand? Your VB3 would be more because the current is more. VB3 would be more than VB2, would be more than VB1. Well and good. Everything is absolutely clear, right? Okay. Yeah. So till now we have seen all those things. First we study about the current equations, then we studied two characteristics. Now let's revise the characteristics. So IC versus VB, it will be exponential relation. Here the expression is also clear, but if you change, even if there is a drastic change in IC, there will be very less change in VB, right? So VB value can be taken constant, that is typically given as 0.7 volt. Then here VC, if your VC is greater than VC set, then your output will not depend on VC potential ideally, but practically it sometimes depends. So this is our region of, this is our interest. Here in this region we will be interested, but surprisingly this region is not known as saturation region. This region is known as active region, and the previous one, that is known as saturation region. So this region is known as active region. So if VC is greater than VC set, if VC is greater than some particular potential 0.2, or it can be taken as 0.7 as well, depending on the question. In the question it will be mentioned. So if your VC is greater than that particular potential, then it will be running in active region, and the equation for that is IS exponential VB by VT 1 plus VC by VA. And then we draw these characteristics for different VBE potential. So these are the characteristics, right? Now let's talk about the region of operation, like when we will get the saturation region, when we will get the active region, because here it is clear that you will get this region when your VDS is greater than VGS minus VT, right? But here we have two different junctions. So based on that, we will tell in what region, like based on this we will tell like for which particular bias you will be in active region, for which particular bias you will be in cutoff, which particular bias you will be in saturation. So that we will tell. But let's just take this emitter to base bias, So sometimes this emitter to base junction, sometimes this particular junction is known as emitter junction, because base can be taken as a reference, right? It's not that you cannot apply any potential at base, you can certainly apply any potential, but base can be taken as reference. So you can call this as emitter junction for emitter to base. For this diode, this much of region can be called as emitter junction. JE. And this much of region, because base can be taken as a reference, so sometimes it is known as collector junction. It will not be asked in the interview, neither in the examination, but for the terminology only, you will need to know that this is known as collector junction, this is known as emitter junction, because in the question sometimes I will be saying, okay, collector junction is reverse bias, emitter junction is forward bias. So these things I will be telling in the question. So you should know what do I mean by collector junction. If I mean by collector junction, that means I am talking about this much of configuration. From collector to base bias I am talking about. And if I am saying emitter junction, that means emitter to base bias. Understanding this point? Crystal clear? Okay. Now, if your emitter to base bias is reverse biased, if your emitter junction is reverse biased and your collector junction is also reverse biased, then your device will be in cutoff region. So if this is reverse bias, no, then it will be in cutoff region. Here if there is reverse bias, that means this n is at negative, sorry, n is at positive, and this base is reference only. So if this n is at positive, if your emitter is at positive, then, and if base is grounded and emitter is at positive, then it will be cutoff region. Okay, if base is grounded and emitter is positive, let's just see it in the circuit. This is the circuit, right? This is the circuit. So I will draw it more clearly, because on the circuit level you should also know. So let's make the circuit level. This was your base, this was your emitter, this was your collector. So let's just say this is at positive bias and this is at ground or 0 volt, you can say. Now you would know this is P to N, this is P, this is N. Now you would know that N is at higher bias, N is at higher bias, so current cannot even flow. This is reverse bias, so this is cutoff region. Okay. Now for saturation region, what is the thing? That emitter junction should be forward biased and collector junction should also be forward biased. Emitter junction is forward biased and collector junction should also be forward biased. Then it is known as saturation region. What about forward active? That your emitter junction should be forward biased and your collector junction should be reverse biased. And what is known as reverse active? Totally reverse of this. Reverse bias and forward bias. But these three are only the interest one. Like we will be interested in these three region only. If both of the cutoff region, you will be able to understand there will be no current, because if both of the region are reverse bias, then there will be no current. Certainly you will understand. So that is cutoff. Cutoff means there is zero current. IC equals to IB equals to IE, all are zero. How will you remember the saturation forward active? Sometimes forward active can be written as active region only, because generally in analog electronics we don't talk about reverse active. Even in the device physics we don't talk about reverse active. We only talk about saturation and active. So sometimes it can be written as active region only. So you just need to remember this one. You can forget about this one as well. Okay, you can forget about this. You don't need to see this one. Your race is between saturation and active. For both of them, that means for the current to flow, at least your this junction should be forward biased. This junction should be forward biased for the current to flow. From base to emitter, it should be forward biased for the current to flow. Now the thing is, you need to see this one. You need to see this one. This is N. You need to see this one. If this is forward biased, then your device is running in saturation region. That means your device is running here. And if this region is reverse biased, that means if this region is reverse biased, that means your device is running in active region. I guess there is a lot of outside noise. I hope that is not disturbing you. So this will be our interest, because I would know that here this will certainly be my forward biased for the current to flow. If this becomes forward biased, then it will be in saturation region, and if this becomes reverse biased, then it will be in active region. That's it. So this will be my matter of interest. So no need to mug it up. We will solve a lot of problem. You will certainly remember it by its own. When we solve the problem, you will certainly remember it. So let's compare active versus saturation. So in active region, this will be certainly valid. This equation will always be valid. This equation will always be valid. This equation will always be valid. All these equations will be always valid. VB equals to 0.7. This will be given. This will be valid here. Okay. Here IC equals to I equals to IC plus IB. This will certainly be valid. IC equals to beta IB. This will not be valid. IC equals to alpha IB. IE. This will not be valid. VB will be given equals to 0.7. This will certainly be valid. VC will be given. That will be fixed. If your device is running in saturation region, then it will be fixed. Okay, this will be valid. Now in case of active region, your collector current is maximum. In case of active region, your collector current is maximum. Here you can see. In case of active region, collector current is maximum. It is rising and then maximum. Here it is low. In case of active region, your collector current is maximum. So in case of active region, collector current is maximum. Collector current is always proportional to base current only, so it will be maximum only. Here it will be minimum. In case of saturation region, your collector current is minimum. If collector current is minimum, then certainly base current will also be minimum. These two formulas are not applicable when we are talking about what? Saturation region. What all are applicable? That always IE equals to IC plus IB. That is 100% sure. Is that so? Is that 100% sure? Yeah. Is that so? Let me think. Yeah, that is 100% sure that IE equals to IC plus IB. That will always be applicable. VB equals to 0.7. It will certainly be there. That will always be applicable. Here VC will be greater than VC set, than this particular potential. And if your device is running in saturation region, then your VC can be taken as 0.2 volt. In case of active region, your IC and IB are maximum, and in case of saturation region, both are minimum. Let's just assume you did not understand anything here. You did not understand anything here. We will solve a problem. You will understand everything there. Let's start with the problem. You will get to know everything. But here, let's just write. Here, your emitter junction should be forward biased. In both of them, emitter junction will be forward biased. In this one, your collector junction will be reverse biased, and here, your collector junction will be forward biased. So let's solve a particular problem. There is a lot of outside noise, so that's why I have to stop the video again and again. But let's start solving a problem now. Your VB value is given 0.7 volt. VC set voltage is given 0.2 volt. VC set will be applicable only when your device is running in saturation region, right? You have to find the VC voltage and IC current for two cases, when RC equals to 1 kilo ohm and RC equals to 10 kilo ohm. So let's solve it one by one. Let's take the first case when RC is equals to 1 kilo ohm. Let's take the first case of RC equals to 1 kilo ohm. So RC is 1 kilo ohm. So what is this potential? This potential is 0.7 volt. Okay, how will you start the question? Since this is the first question, so how will you start the question? You will see this particular circuitry. You will get to know this is your P, this is your N. This will certainly be N only, because NPN. This is your base, this is your emitter, that you know. It is given that base to emitter potential is 0.7 volt. P to N, base to emitter potential is 0.7 volt. So this much potential is 0.7 volt. P to N. If this node is 0, what this node will be? This is your 3 volt, which is connected to 100 kilo ohm. This is your 3 volt. If this node is grounded, what this potential will be? 0.7 volt, right? This node will be 0.7 volt. How much current is flowing here? Whatever the current that is flowing here, that current will be base current only. Say yes or no. Whatever the current that is flowing here, that current will be base current only, right? The current that is going into the base, that will be base current only. So what will be your base current? Your IB is equals to 2.3 divided by 100k, right? So that would be some 23 microampere. Your IB is equals to 23 microampere. Till now we have not assumed anything. This is there with respect to every region of operation. Even if your device is running in saturation region or in active region, this will not change. Till now there is no issue. Till now there is no issue, right? We did not even apply any approximation. We did not we did not do anything, like we did not assume any bias, nothing. We just see that this is 0.7, this is 3 volts. So what is the base current? That is 2.3 divided by 100, get 23 microampere. Now we have to assume. What we will assume? That assuming that our device is running in active region. So always we will solve in this manner only. Always we will assume our device, our BJT to be in active region. So let's assume. This is the method of solving. So first we will assume. Assuming BJT in active. BJT in active region. Assuming BJT in active region. So if BJT is an active region, this BJT is in active region, RC is equals to 1 kilo ohm. RC is equals to 1 kilo ohm. Let's remove this IC current. And from here we know what is the current that is flowing. That is 23 microampere. If this is 23 microampere, if BJT is in active region, then what is applicable? IC equals to beta IB. This is only applicable for active region. This is only applicable for active region. So IC equals to beta IB. What will be your IC? Beta value is given as 100. Beta value is given as 100. 100 into 23 microampere. So 100 into 23 microampere. 23 microampere. So this will be some 2.3 milliampere. So your IC current is 2.3 milliampere. This is your IC current. So here your current that is flowing is 2.3 milliampere. If this is your 2.3 milliampere, then what is the drop here? This is the drop. So what will be your VC potential? Your VC potential will be 5 minus 1 kilo ohm into 2.3 milliampere. So your VC potential will be 2.7 volt. This is all after assuming your BJT is running in active region. This is what you have assumed. So you got to know your VC potential. Now what is your BJT? So these are not your final answer, that IC is equals to 2.3 milliampere. This is my final answer. These are not the final answer. What are the final answers? This node is at 0.7 volt. This node is grounded, and this node is at 2.7 volt. Right? This was, you see the arrow, this is P to N. So this will be N only. Now tell me one thing. We need to see this bias and we need to see this bias. What is this? P is at 0.7 volt, N is at 0 volt. That means this is forward biased. P is at higher potential, N is at lower potential. That means this is forward biased. What about this one? N is at higher potential and P is at 0.7 volt. So N is at higher potential. N is at higher potential. That means this is reverse biased. So this junction is forward biased, this junction is reverse biased. What does that mean? That your BJT is in active region. So all the assumptions that you made, all the equations that you write, all are correct. So assumption correct. Assumption correct. Assumption correct. Did you understand how we are going to solve the problem? Did you understand this particular concept? That first we assumed our device to be in active region. If I am assuming my device to be in active region, then all these are applicable. So till this calculation, I did not assume anything. I knew this is 3 volt, this will be 0.7 volt. Always it will be 0.7 volt. It will be 0.7 volt irrespective of the region of operation. So it will be 0.7 volt. So this will drive 23 microampere current. Then IC equals to beta AB, beta is 100. So this is driving 2.3 milliampere current if I am assuming my BJT to be in active region. So if I assume my BJT to be in active region, then I got to know that my IC is 2.3 milliampere. Then what will be my VC? VC will be 2.7 volt. Then I check. Then I see my device. I get to know that from base to emitter we are forward biased, right? And from here to here, my emitter junction is forward biased and my collector junction is reverse biased. So this bias I need to check and this bias I need to check. So P to N, P is at higher potential, N is at lower potential, forward bias. P is at lower potential, N is at higher potential, reverse bias. All calculations are correct. That's it. Similarly, we are going to solve the second part. In the same manner, we are going to solve the second part. So what we are going to see, although calculations will be the same only, but yeah, I will do right from the scratch. Let's just say this particular question was given and right from the scratch I am going to solve it. I am not going to use any previous calculations. So this particular question was given where RC value was already given, that was 10 kilo ohm. So RC value was already given to you, that was 10 kilo ohm only, and this was your IC current. So what I would have done, I would have got to know the IB voltage. I don't know in which region device is working, but I know one thing, that this will certainly be 0.7 volt. There is no doubt about it. And what will be my IB? My IB will certainly be 3 minus 0.7. That would be 2.3 divided by 100K. That means certainly my IB will be 23 microampere. No one can stop it. Now I will assume, what I will assume? I will assume that assuming BJT in active region. So if I assume my BJT to be in active region, what will be my IC? IC will be my beta IB. IC will be beta IB. So what is the value of beta? Beta is 100. What is the value of IB? IB is 23 micro. So my IC will be 2.3 milliampere. Is that my final answer? No, that is not my final answer. I need to check the VC potential as well. So 2.3 into 10K. What will be my VC potential? VC potential will be 5 minus whatever the drop we get here. What drop we will get? 10K into IC. 10K into IC. So 5 minus 10K into 2.3. That will be 5 minus 23 minus 18 volt. Minus 18 volt. So this VC potential will be minus 18 volt. VC potential will be minus 18 volt. This node is grounded. This node will be at 0.7 volt, and this node, VC node, will be at minus 18. So from P to N, this was from P to N. This was your P, this was your N, and this will certainly be N. NPN. Okay. P is at 0.7 volt, N is at 0 volt. This is forward biased. P is at higher potential, N is at lower potential. Here, N is at minus 18. N is at minus 18. So here, N is at lower potential and P is at higher potential. P is at 0.7, N is at minus 18. N is at minus 18. That means this is also forward biased, right? N is at lower potential, P is at higher potential. So this is also forward biased. So your device is working in saturation region. Saturation region. So device is working in saturation region. What does that mean? The assumption is wrong. Assumption wrong. So whatever the calculation that we have made there, that is wrong. So all these answer, this answer, all these will be wrong. These are not your final answer. Your VC is not minus 18 volt. Your IC is not 2.3 milliampere. So what will be the correct answer? Do I have a page? I need to add another page. What will be the correct answer? For getting the correct answer, now I will have to use this VC set potential, that is 0.2 volt. I will have to use this VC set potential. VC set, that is equals to 0.2 volt. So RC is what? RC is 10 kilo ohm. What is given? Given if device is in saturation, if BJT or device, whatever we can write, if BJT is in saturation, then VCE would be equals to VC set, and that would be equals to 0.2 volt. So this node is grounded. What this node will be? 0.2 volt only. So what will be this current? What will be this current? So this current would be IC equals to 10 minus 0.2 divided by 10K. This potential is 0.2. 5 minus, this is actually, this is your IC current. But that is the same as this current only, no? Because in 10 kilo ohm, whatever the current is flowing, that same current is flowing in the BJT as well. So 10 minus 0.2 into 10 minus 0.2 divided by 10K. What that would be? 9.8 divided by 10K. 9.8 divided by 10K. So 0.98 milliampere. 0.98 milliampere. So this is the answer. IC is equals to 0.98 milliampere, and your VC is 0.2 volt only. What will be your IB? What will be IB? IB will be equals to IC by beta. IC by beta. Is this correct? No. This is wrong. Because IC equals to beta IB is not applicable now. IB will be the same only because this node is 0.7 volt. So here we did not make any assumption. We know that VB equals to 0.7, that is applicable for all, whether your device is in active region or in saturation region. VB equals to 0.7 is applicable for all. So this current, this is your IB current, that is applicable for all. So IB will be equals to 3 minus 0.7, that is 2.3 divided by 100K. So IB is 23 microampere. So whether your device is working in active or it is working in saturation, this will always be 0.7 volt if it is given in the question. So always we will take the same potential. VB is equals to 0.7 volt. Are you getting this point? So here, after assuming our device in active region, in the first case when RC equals to 1 kilo ohm, our assumption was correct. But when we took RC equals to 10 kilo ohm, our assumption went wrong. Here the device was working in saturation region. How did we check? We made the BJT and we checked that it was working in saturation region. So our assumption was wrong. So we had to take the saturation condition. So in the saturation condition, our VC potential will be 0.2 volt. That means our current would be 4.8 divided by 10K. Sorry. IC would be 5 minus 0.2. Sorry. This is 5, not 10. 5 minus 0.2. 5 minus 0.2, sorry, 5 minus 0.2, 5 minus 0.2 divided by 10k, so it would be 0.48 milliampere, 0.48 milliampere. 5 minus 0.2 divided by 10k, 0.48 milliampere. So VC will be 0.2 volt and IB will be equals to 23 microampere. 3 minus 0.7 divided by 100k, 23 microampere. So these are the correct answers. These are the correct answer, and in this one, these are the correct answers. Right? So both of the cases IB is same. It's not always necessary that IB will be same in both of the cases. And in this case, what will be your IC? IC will be, sorry, not IC, IE. I told you IE equals to IC plus IB is always applicable. So IE equals to IC plus IB. What is IC? IC is 480 microampere. Can I say that? Can I say that 480 microampere? Yeah, certainly I can say that. It is 480 microampere plus 23. So 503 microampere. This is your IE. IE is 503 microampere. Say yes or no. 480 plus 23, that would be 503. And in the previous case, when it was working in active region, so your IE would be beta plus 1 IB, beta plus 1 IB. That means 101 into IB was 23 micro, right? So 101 into 23. Divided by 1000. 2.323. 2.323 milliampere. This would have been your IE, right? Well and good. So I hope you must have understood the concept of BJTs. Now you are very comfortable with solving all the problems. In the next video, we will see the assignment. But before that, let's see the PNP transistor. That will be same as the NPN. So we will just write down the equations and everything. It will be a clear revision for you. So what do you think? Where there is an arrow, this will be emitter. Where there is an arrow, that will be emitter. What this will be? This will be collector. And what this will be? This will certainly be base. This is emitter, this is collector, and this is base. This will be your VEC potential. From here to here, this will be your VEC potential. This will be your VEB potential. VEB potential. Right? VEE I have written. VEC. VEC and VEB. VEC and VBE. VEB. So what will be the IC equation? IC equation will be IS exponential VEB by eta VT. VEB by eta VT into 1 plus VEC by VA. Well and good. This will be your IC equation. And all these are always applicable. IE equals to IC plus IB. And this expression is applicable only when your VEC is greater than VEC set. Your VEC is greater than VEC set. This is only applicable when VEC is greater than VEC set. IE equals to IC plus IB and IC equals to beta AB and IE equals to beta plus 1 IB. All these are applicable only for active region. For active region of operation, because we already know now this we are talking about active region. For saturation region, VC set will be given. Based on that, you will get your answers. Right? So what will be the characteristics for IC versus VCE? Output characteristics we are drawing. So let's draw the device here yet again. Emitter, collector, base. So IC versus VEC. Before that, I should make IC versus VEB. So how it will go? First till a particular point 0. After that, it will follow exponential. Exponential rise. First rise will be there. And if I draw IC versus VCE for different VBE potentials, I can draw it for different VBEs. For different VEB potentials, these are the curves. VEB3, VEB2 and VEB1. So VEB3 is greater than VEB2 is greater than VEB1. Region of operation, why did I write region of operation? Okay, next is assignment only. So region of operation, the same table will be there. So here I will just write in short only region of operation. How will I write? Active region. Forward active, the same table will be followed. Okay, if we are talking about active region, what does that mean? Emitter junction should be forward biased, collector junction should be reverse biased. Collector junction should be reverse biased. And what about saturation? Emitter junction should be forward biased and collector junction should be forward biased. What about cutoff? Emitter junction should be reverse biased and collector junction should be also reverse biased. And what about reverse active? Reverse active. In reverse active, emitter junction should be reverse biased and collector junction should be forward biased. But our area of interest will be these two only, right? Forward, reverse, forward, forward. Well and good. So I hope you must have understood the lecture. You must have enjoyed it. In one lecture, in just 90 minutes, we have covered everything from biasing to every single thing that we covered in some 5 to 6 hours. Nearly from 4 to 5 hours that we covered in MOSFET. In just 90 minutes, we have covered everything that is required for your interviews or the written test, right? So you must have understood everything. In the next video, we are going to solve the assignment. So I recommend not to solve the assignment before watching the solution. Let's watch the solution once. Watch the solution once. Watch the solution of first two to three questions. After that, you can attempt on your own. Okay. So these are the questions. Nearly, roughly around 20 questions we will be solving. We will be solving a lot of questions because I need to make you comfortable with problem solving. Okay. So yeah, that we are going to solve in the next lecture. So these are the questions. I am showing it in front of you. So no need of showing all the questions now because once you need to see the solution of at least 1 to 2 questions, then you should solve all the problems on your own. Then there will be another assignment that I have already written. So that also we are going to solve. Okay, then let's meet you in the next lecture with the assignment solution. Okay, thank you. Hello everyone. So let's solve the assignment. So let's you shouldn't solve the assignment on your own. First, let's just see the solution of some 2 to 3 questions. Then you can start solving on your own. So this is the first question. You have to find the value of RB. VC potential is given, that is 2 volt. So if this is 0, this will be 2 volt. This is given. And VB potential is given, that is 0.7 volt. So this is your emitter, this is your base. So this will be your 0.7 volt. Right? What kind of transistor is that? We don't know. We can write the type of transistor. How we will write? P to N. The arrow is this. So this will be P to N and this will certainly be N. So this is NPN. What is this? This is forward biased, right? P to N. P is at higher potential, forward biased. What is this? This is reverse bias because N is at 2 volt. N is at 2 volt and this is at 0.7 volt. So this is reverse bias. So what do you understand? This is in active region. That's it. This is forward bias, this is reverse bias, this is in active region. That we know now, right? Now this node is 2 volt. So what will be this current? This current is actually IC only because IC is the current through the collector terminal. So this current is IC only. So what is the IC value? IC value is 12 minus 2 divided by 5k. So 10 by 5k. IC value is 10 by 5k or you can say 2 milliampere. What is your IB value? Can you tell what will be your IB value? This node is 0, this node is 0.7. This node is 12. This node is 12 volt and this node is 0.7 volt. What will be your IB value? That would be 11.3 by RB. That will be your RB value. Since this is an active region, what I can apply? IC equals to beta IB. So 2 milliampere is equals to beta, that is 50, into IB, that is 11.3 by RB. So what will be your RB? RB will be 25 into 11.3. 25 into 11.3. So RB will be 282.5 ohm. That's it. So before applying IC equals to beta AB, I need to make sure. What do I need to make sure? That my device is in active region. So here I applied IC equals to beta AB. So if my device is in active region, then only I can apply this. Let's move to the next second question. Here beta is equals to infinity. This is the most important point, that beta is equals to infinity. So if beta is equals to infinity, then what will happen? If beta is infinity, then IC is equals to IE, and that is equals to 1 milliampere, and your IB will be equals to 0. So this current is 0. This current is 0. Now this 1 milliampere current will be flowing through this particular resistance as well. This is the 1 milliampere current. So what will be this potential? What will be this potential? This potential will be 0.5 volt, because 1 milliampere into 500, it will be 0.5 volt. If this is 0.5 volt, then VB potential is given. VB is 0.7 is given. VB is 0.7. Base to emitter is 0.7. Not from here to here it is not 0.7. Base to emitter is 0.7. Base to emitter. This node is emitter, this node is collector. This node is collector, this node is base, this node is emitter. Right? So this particular potential, only this much of potential is 0.7. So if this node is 0.5, what this node will be? 1.2 volt. Are you able to understand this point? And this node will be 3 volt only. So this was your N, right? This was your P, this was your N, and this was your N. So N to P, N is at 3 volt, P is at 1.2 volt. So N to P, this is at higher potential. So what do you understand? This is reverse biased, and this is forward biased. This is forward biased, this is reverse biased. So again it is in active region. Understood? This is in active region. So if it is an active region, you can apply all the equations now. So by the way, no need to apply, because already beta is equals to infinity. So if beta is infinity, this current is 0 only. This current is 1 milliampere. Right? We just need to find this potential, that was 1.2 volt, because if this is 0.5, this would be 0.7. So it would be 1.2 volt only. So this will be 1.2 volt. Now what you can do? This current will be equals to this current. Say yes or no. The upcoming current that is coming will be equals to this current. So what is that upcoming current? Current coming from upwards. That is 3 minus 1.2 divided by 60K is equals to 1.2 divided by R2. Right? If I consider R2 in kilo ohm, so can I remove this kilo here? R2 in kilo ohm. I am assuming my R2 is in kilo ohm. So I can remove this kilo from here, because let's just say my R2 is 30 kilo ohm. If I solve this equation, I will get some R2 value, that I will get 30. So I have already assumed R2 be in kilo ohm, so my answer would be 30 kilo ohm. So from this kilo to kilo, that would have been getting cancelled, no? So I have assumed my R2 be in kilo ohm, so I can remove this kilo from here. Are you getting this point? Now my calculation will be easier. Otherwise, I have to take that 10 to the power 3. Okay, so that would be 60 into 1.2, that would be 72 plus 1.2. Let me solve it. So if I solve it, what do I get? My R2 value is, I am getting 40. R2 value I am getting 40. So what will be the actual answer? R2 will be 40 kilo ohm. RT value you are getting 40 in kilo ohm. 40 in kilo ohm. So R2 value will be your 40 kilo ohm. Did you see what did I do here? What did I do here? I just removed this kilo. Considering that my R2 is in kilo ohm. If you take this kilo here, you can still solve it and you can get your answer. This is just a way of calculation that I can remove this kilo from here, and I am in my brain I am assuming R2 in kilo ohm. So if I get the R2 value by solving this equation, I get the R2 value to be equals to 40. If my R2 value is 40 and I consider that in the kilo ohm, so my answer would be 40 kilo ohm. Right? And here what I did, I just write down all the potential. This was 3 volt, this was 0.7 volt, since this 1 milliampere was flowing here, this was 1.2 volt. If this was 1.2, this was 3, this was in active region only. So again and again we will check active region of operation, so that you can do on your own as well. You have to find the VCE potential. beta value is given, VB voltage is given, VB is given. If this node is 0, this node will be at 0.7 volt. Irrespective of the region of operation, this is applicable, right? This will be 0.7 volt. What will be this current? This is your IB current. That will be, IB current will be 11.3 by 100K. 11.3 by 100K. So 11.3 by 100K, it would be 113 microampere. Say yes or no? IB current would be 113 microampere, right? Basically, this is the scene, 11.3 by 100K. 10 to the power minus 5, yeah, 113 microampere. Again, you have to consider, because you don't know this potential. In the previous question, here we knew this potential. In this question as well, in this question, what did we know? Again, we knew this potential, VC potential was given. In this question as well, we knew the VC potential, right? Because this potential was given. Here, do you know this potential? No. For knowing this potential, you need to calculate the IC current. This will be your IC current. So you need to calculate the IC current. So again, you have to assume, assuming that it is in active region. Active region, that I am assuming. Assuming if it is in active region, so what will be your IC? IC will be equals to beta IB. So beta value is given, that is 80 into 113 micro. So 113 into 80 divided by 1000, that would be 9.04 milliampere. So this current is coming out to be 9.04 milliampere. So what will be your VCE now? What will be your VC potential? Let's just call this potential as VC. So what will be your VC potential? That would be 12 minus 2 kilo ohm into 9.04 milliampere current. So what that potential will be? Minus 12. So that would be minus 6.08 volt. 6.08 volt. So this is your VC. Is that the correct answer? No. This answer is wrong. Why this answer is wrong? Because your this potential, this particular potential, let's just make the BJT now. Why this answer is wrong? Because this node was at 0.7 volt and this node is becoming at minus 6.08. So this was your N and this was your P. This was your N. This is certainly forward biased, but this is reverse biased. N is at negative potential, P is at positive potential. N is at lower, P is at higher. So this is reverse biased. If this is reverse biased, what do you understand by that? That it is acting in saturation region. And if it is acting in saturation region, so for saturation region, what is the condition? For saturation region, what is the condition? Wait a second. Yeah, so for saturation region, the condition is this is forward bias, no doubt about it. But this has to be reverse bias. This node is at 0.7 volt. This was your N, this was your P. This was your N, this was your P. Where this potential can go? If you need to make this as forward biased, this was forward biased only, this should be forward biased only. P should be at higher potential. So the potential here, this potential, let's just call this potential is VC. So VC should be lesser than 0.7, right? This is the condition. Your VC should be lesser than 0.7. For any value of VC lesser than 0.7, this will be forward biased and should be at higher potential. Here we got to know that our device is working in saturation region. So for the saturation region, this has to be forward biased. This has to be forward biased. So for any value, if your VC is less than 0.7, it will work. So what will be the answer? That's it. Now don't say, sir, 0.7, this can also work. Array, this will not work. Why this will not work? Because we got to know that this will come if you assume your device to be in active region. So active region is not there, only saturation region is there. Sometimes I have seen that people give VC equals to 0.2 volt because they say that in the saturation region, the answer is like VC is taken as 0.2 volt only. But when the IITs framed this question, they did not think in this manner. What did they thought? They thought that we should frame a question in a manner that the guy will get to know that it is acting in saturation region. But now if it is acting in saturation region, then what can be the possible value of VC? So only one of the possible answer is there. Now you cannot say that VC is less than 0.7 volt So this can also be the possible answer. Nah, this cannot be the possible answer. Why is it so? Because if my device was going in saturation region, just below that, at that particular point only it will stop. At point 2 only it will stop. What do I mean to say? That VC potential cannot change. If I am saying that I am getting my saturation region of operation at VC equals to 0.2 volt. So after that, always VC will be 0.2 volt only. So your answer will be 0.2 volt. Okay. So your answer will be 0.2 volt. So this I don't need to write. So just you need to get to know that this device is working in saturation region and your VC set will be 0.2 volt. VC set will be taken as 0.2 volt. That would be equals to VCE only. That would be equals to VCE only. That would be equals to VCE only. Yeah, so let's solve this question now. So in this question, you have to find the collector current. So what will be the collector current? This will be the collector current. No, this will not be collector current. This will be the collector current. Why? Because collector current is the current flowing through the collector, not through this resistance. Collector current is the current flowing through the collector, not through this resistance. This current will be something else. This will be my collector current and this will be my base current, right? Now the same base current is flowing in this loop, no? The same base current. This is the base current. The same base current is flowing in this loop. So this will also be the base current. This will also be the base current. So same base current is flowing in this loop. So what will be this? This will be IE. Why it will be IE? Because this current is IB, this current is IC. So what will be the current coming from upward? That would be IC plus IB. Now that IC plus IB can be equals to IE. Or you can say this was your IE. This was your IE. That IE current flew from this loop. What do I mean to say is that there was a network. This was your IE current. The IE current was flowing from this loop. From here upward also there would be IE current, no? The current the network was taking, it was delivering the same current. So it was delivering IE current. This was the network. And from upward also IE current would be flowing. Or you can say IC and IB is there. So upward current would have been IE only. Okay. So both of the analogy you can see. Now your target is to find the collector current. So again I will have to apply the KCL KVL, but here I will have to apply the KCL KVL intelligently. I have to take intelligent equations. If I start from this 24, can I write down the KCL in this direction? If I try writing the KCL in this direction, what will happen? In this direction, I am writing the KCL in this direction. So I know the drop across this resistance, but do I know this drop? Do I know this drop? No, I don't know this drop. So I cannot write the KVL in this direction. I cannot write KCL KVL equation in this direction. I cannot write KVL in this direction. So in this direction I can write, right? Because I know the drop across this one. I know the drop across this one. And I know this drop as well. Because your VB drop is 0.7 volt. So I know all the drops. This drop I know, this drop I know, and this drop I know. So let's see the equation. What that equation will be. 24 will be equals to what? Or you can start from 24. 24 minus this potential, minus this potential, minus this potential. So I'm writing 24 is equals to, what 24 will be equals to? 4.7K into IE plus 560K into IB plus 0.7. (24) is equals to 4.7K into IE plus 560K into IB plus 0.7, right? Now I need to proceed in the question. So how will I proceed in the question? I have to take an assumption because I don't know this potential. Do I know the potential of this point? I know the potential of emitter. I know the potential of base as well. Do I know the potential of collector? No. So I cannot tell whether my device is in active region or saturation region. So again I have to make an assumption. What is the assumption? Assumption is assuming active region. This is the very important point, that you are again assuming it. Once you assume, you get some values, then you verify. So assuming it is in active region. So what will be the equation now? 4.7 K I am ignoring. Again I will ignore the K. Okay, K value. This is 10 to the power 3 that I am ignoring. Why I am ignoring? Because I am considering my IE and IB value to be in milliampere. Whatever I will write down the equation, whatever the answer of IB I get, that will be in milliampere only. So let's write down the equation, you will understand it. So how can I write IE? IE will be beta plus 1 IB. What is the value of beta? Beta will be 100 plus 1. That would be 101 IB. What did I do? IE is equals to beta plus 1 IB. This is what I did. So beta is 100, so 101 IB plus 560K IB plus 0.7. What did I do? I have taken IB and IE in milliamperes. So now I will solve this equation. From there I can get the IB value. What I will get? I can solve this equation. As far as I remember, it was some 0.0225. 0.0225. This is the IB value you will get. That is in milliampere. That is in milliampere. So what is the actual IB value? That is 0.0225 milliampere, right? If you solve this equation, this is the IB value you will get, 0.225. But that is in milliampere because you have already considered IB to be in milliampere. From milli to kilo, that is cancelled. So IB is 0.0225 but in milliampere. So this is your answer, or you can write 22.5 microampere. So what will be your IC? IC is 22.5 micro into 100. IC will be beta IB. So that would be 2.25 milliampere. This will be your IC. Is that the final answer? Is that answer is final answer? That is the correct answer. Is that so? No, because we had made this assumption. So we have to check if the assumption is correct or not. So what is the VC potential? This potential. VC potential we need to check. So what will be your VC potential? VC potential will simply be 24 minus 4.7 K into IE current. IE current. You don't know IE current. So what will be your IE current? IE current will be IC plus IB. IC plus IB. This current plus this current. This current plus this current. So what that would be? It would be somewhat around, this 2 will come in 2.27 milliampere. It would be somewhat around 2.27 milliampere. So this is your IE current that I need to put here, 2.27 milliampere. Why I am doing this calculation? To make sure if my assumption is correct or not. So that I will make sure 4.7 into 2.27. 7 into 2.27 minus 24. So 13.3. Some VC value I am getting is 13.3 volt. So this is the VC value I am getting. This is the VC value you got. So let's make our BJT now. So after making the BJT, what did I get to know? That this node is at 3.3 volt. This node is at 0.7 volt and this was grounded. So certainly this is forward biased. What about this? This was your N, P, N. So N was at higher potential, P was at lower potential. So this was reverse biased. So it was certainly working in active region. So assumption that we made here, that was correct. This assumption was correct. So this will be the final answer. If this assumption was not correct, then VC potential would have been given. It would be some 0.2 volt. Then you could write down the current IC and then you could get the. If this assumption was not correct, then could you solve this problem? Yeah, you could have solved this problem. Certainly you could have solved this problem. Then you would assume this to be 0.2. Then you would do something. If you assume this to be 0.2, then I don't think this will even turn on. Because if this is 0.7, this is 0.2. Where the current will flow? Current will flow in this direction. So I don't think that question will become relevant. So in this question, it has to be in active region only for this bias. So it is in active region. Well and good. Let's move to the next point. Actually, this cannot even come. In this bias, it cannot even come to be in saturation region. Why is it so? Because these two are connected. Collector to base are connected. So this will certainly be at higher potential than this one. If there is any current, if there is base current, what did I say? I just made a very good observation here that if I am saying that my device is gone, if my device is on, then certainly there will be this base current. No? If my device is on, then certainly there will be a base current. So whatever the potential is there, this potential will certainly be Vc minus some this potential. If my device is on, this will be my IB current, and this potential will be some Vc minus drop across this. So certainly your P will be at lower potential and N will be at higher potential. So always it will be in saturation region. So always it will be in active region. So this calculation was not even required. Actually, if you could make an intelligent guess, what was the intelligent guess? The intelligent guess was, if your current is flowing, then IB will flow in this direction. If IB is flowing in this direction, then this will have some drop. If this is having some drop, if the particular resistance is having some drop, then certainly the base will have lower potential than the collector. That's it. Okay, so this is how also you could check. Let's move to the next question now. You have to solve this question. You have to find VC potential again. VC potential you need to find. Again, there is nothing given that whether it is in active region or saturation region. Nothing is given. Here I mentioned the options. The options are 20 by 3, 10, 14, 20. Options are very far away. No? Options are very, very far away. 20 by 3, 10, 14, 20. Very far away. Like, it's not that this is some 6.33 volt. 18 to 6.66 volt. This is some 6.66 volt. So there is good amount of gap, and beta value is 100. That is also a like larger value. It's not that beta is some 20 or 21. So for ease of calculation, I can take beta to be infinity. For ease of calculation, I can take beta value to be infinity because options are very far away. 6.66, 10, 14, 20. There are 4 volt gap, 6 volt gap. There is some 4 volt gap again. So options are very far away. So for the ease of calculation, I am taking beta to be infinity. Since options are far from each other, and we are taking beta to be infinity for ease of calculation. So if beta is infinity, then this will drive 0 ampere current. Say yes or no. This will be driving 0 ampere current. So what will be the potential here? That would be 20 into 5 by 10. What will be the potential here? 20 into 5 by 15. Sorry, 20 into 5 by 15. Right? 20 into 5 by 15. So that would be 20 by 3. This potential will be 20 by 3 volt. VB value is given, that is 0.7 volt. So what this potential will be? This potential will be 20 by 3 minus 0.7. This potential will be 20 by 3 minus 0.7. So what will be this current? This IE current. So IE current would have been, look, I started from here. This potential was 20 by 3 volt. So if this potential is 20 by 3, what this potential will be? 20 by 3 minus 0.7. 20 by 3 minus 0.7 divided by 10k. So what is 20 by 3? That is 6.66 minus 0.7 divided by 10k. What do you get? Minus 0.7 divided by 10. So 0.6, somewhat 0.6 milliampere. 0.6 milliampere. So this current is 0.6 milliampere. So again, this current will also be the same, right? Because we have, for ease of calculation, we have taken beta to be infinity. So that would also be equals to IC. Nearly equals to IC, I should write. Nearly it will be equals to IC only. So if this current is 0.6 milliampere, then what will be your VC node? VC node will be 20 minus 10 into 0.6. That would be 14 volt. So this node is coming out to be 14 volt. Is that the final answer? No. We have to check if our assumption is correct or not. What is the assumption? That if you are taking beta equals to infinity, then certainly you are assuming that you are working in such active region. In active region only, this much high value of beta you will get. In active region only, you will get this much of high value of beta. That beta is equals to infinity. So you are again assuming it to be in saturation. Again, you are assuming it to be in active region. So in active region, you will get this much of high value of beta. So this node was at 14, this node was at 20 by 3. 20 by 3, this is some 6.66. Again, this is reverse biased because this was your N, this was your P. So again, this is reverse biased, so it was certainly working in active region only. So this was active only. So in active region only, you get this much of high value of beta. In active region, you get this much of high value of beta. So there also you check that this was this was working in active region only. So that's why VC is equals to 14 volt. This was the answer. So what was the intelligent thing we did here? That we checked that the options were very far away. So I could take beta equals to infinity. So my IB current would be equals to 0. So that would help my calculation to be eased, right? My calculation will be easy. Let's move towards the next question now. This is the problem. You have to find the region of operation, in which region it is working. Let's find the region of operation. How will you find the region of operation? You know this potential. You just know this potential. You know this current. This current is IB. This current is IE. So what this drop will be there? This drop will be plus 2 minus. This drop will be plus 2 minus. So you have to work in this loop, because in this loop only you know all the potentials, right? This is 10 volt. You know the potential across this resistance. You know the potential across this resistance. You know the potential across here as well. So your 10 volt will be equals to 10 volt. 10 would be equals to, better I should start from here. 10 would be equals to, because my target is to find this potential. If I know this potential, if I know this potential, if I know this potential, if I know all these potentials, then my task will be easy to tell in which region it is working. So tan would be equals to 270 into IB. If I am writing 270 into IB, what do you understand by that? That I am assuming it to be in saturation. I am assuming it to IB to be in milliampere. I am assuming IB to be in milliampere. That's why I am writing 270 into IB, right? Otherwise, I would have written K. If I am not writing K here, that means I am assuming my IB to be in milliampere. Plus 0.7 plus IE. Again, assumption I am making, assuming active. Again, I am assuming it to be active. So what will be the answer? Tan would be equals to 270 IB plus 0.7. Now I can apply I equals to beta plus 1 IB. So what that would be? Beta plus 1 IB. So 101 IB. IB would be equals to 9.3 by 371, 0.025. 0.025. In the mind, I have taken it to be milliampere. IB is 0.025 milliampere. So what will be your IE? IE would be into 101, 2.53 milliampere. 2.53 milliampere. And what will be your IC? That would be 200, 2.5 milliampere. Certainly, you just need to multiply with 100. 2.5 milliampere. So these are the other values. Now I can find the potential of each node. What will be your VC potential? VC potential will be tan minus 1k into 2.5. Tan minus 1 into 2.5. Tan minus 2.5. That would be 7.5. Right? What will be my VE? VE would be 1 into IE. 1k into IE. So that would be 2.53. You understand it? What will be my VE? This is my VE. So that would simply be 1k into IE. 1k into IE. 2.53 volt. This is 7.5 volt, 2.53 volt. What will be my VB? VB would be 2.53 plus 0.7. 2.53 plus 0.7. So what that would be? 3.23 volt. Right? 3.23 volt. So these are the values VB, VC and VE. Let's make the MOS now. Not the MOS, sorry. BJT. Let's make the BJT. This is your BJT. This particular node, अरे यार ये screen black हो गया. Yeah, forget it. So look at the board, not at my face. Yeah. So your VE is at 2.53. This is at 2.53. This is actually Pn. This is your N. P to N. This is your N. So N is at VC is at 7.5 volt. This is at 7.5 volt. This is 2.53, and your this P is at 3.23 volt. 3.23 volt. P is at higher potential, N is at lower, forward biased. P is at higher potential, N is at lower potential. Sorry, N is at higher potential, P is at lower potential, reverse biased. This is forward biased, this is reverse biased. What do you think? What is the region of operation? Active. This is the active region of operation. So what is the answer? This is the answer. The answer is it is working in forward active region or active region of operation. Okay, well and good. Let's move towards the next question. So transistor is working in active mode. Transistor is working in active mode. When Vc equals to 2 volt, your Rc is equals to Rc1. When Vc is equals to 4 volt, your Rc equals to Rc2. You have to find the ratio of Rc1, Rc2 by Rc1. Solve it on your own. Think about it and then tell the final answer. If your transistor is working in active mode, then what do you think? If transistor is working in active mode, so let's make the diagram more clear only. Transistor is working in active mode. So where is the active mode? This is the active mode. No? IC versus VCE I am drawing. IC versus VCE. IC versus VE. This was the active mode. No? This was the active mode. So in active mode, IC is not the function of VCE. Not the function of VCE. So even if your VC potential is changing, your IC value will be same. What do you understand? Even if VC is changing, VC is changing, IC will be same. Even if VC is changing, IC will be same. So what your IC will be? In the first case, what will be your IC? Tan minus VC. VC is 2 volt divided by RC1. At that time your RC was RC1. That would be equals to tan minus, in the next case what was your VC? That was 4. Tan minus 4 divided by RC2. So what is your RC2 by RC1? RC2 by RC1. That would be 6 by 8. 6 by 8. 0.75. That's it. This is the ratio. Did you understand what did I check here? I checked that if you know, if you are changing VC potential, your IC will not change. IC will be same only. So even if your VC is changing, IC will be same. Tan minus VC by RC. So tan minus 2 by RC. Tan minus 2 by RC1 is equals to tan minus 4 by RC2. So RC2 by RC1 is 0.75. Well and good. Let's move to the next question. You have to find IB current. So what will be the IB current? This node is at 0. This node will be at, because this is grounded, what this node will be at? Minus 0.7 volt. So what will be the current? Current will be in this direction, IE current. What will be your IE current? IE current will be minus 0.7 plus 10 divided by 6.3K. So 9.3 divided by 6.3. 9.3 divided by 6.3. That would be 1.48 milliampere. So if this is your IE, what will be your IB? IB will be 1.48 divided by 81. 1.48 divided by 81. Why did I do so? Why did I do so? Why did I do so? Because IE is equals to beta plus 1 IB. So what will be your IB? IB will be IE upon beta plus 1. So 1.48 divided by 81. 1.48 divided by 81. So 18.22 microampere. Now is that the final answer again? No, because you have to check the region of operation. So this current was, this downward current was 1.48. So what this current would be? You don't need to calculate IC again, because you know one thing, that your IC will nearly be equals to 1.48 milliampere only. It will be somewhat lesser because IE current is higher. It will be somewhat lesser, but you are checking the region of operation only. If you are checking the region of operation only, you can assume it to be somewhat equals to 1.48 milliampere only. Are you getting this point? I am checking only the region of operation. I am not marking my final answer, just checking the region of operation. So I can take it nearly to be equals to 1.48. Otherwise, from here also I can check it would be 1.47 milliampere somewhat. Okay, so yeah. So what this voltage drop will be? 1.48 into 5 into 5. Arey bhai. Okay, so let's just call this as VC. So what your VC would be? VC would be 5 minus 1.48 into 5. So what is the answer you are getting? This VC will be negative. VC will be negative bhai. Minus 2.38. Minus 2.38 volt. So if you make the BJT, this node was at 0 volt, this node was at minus 0.7 volt, and this node was at minus 2.38 volt. Again here you made the assumption. What was the assumption? Assuming active, then only this will be applicable, no? IE equals to beta plus 1 IB. So here you again made the assumption. But here what you are getting to know, this is your P, this is your N, so this would be your N only. This is forward biased. What is this? This is forward biased. And what is this? This is also forward biased, because P is at 0, N is at minus 0.7. So this is forward biased, but here P is at 0, N is at minus 2.38. So again, this is in saturation. The assumption that you made, that was wrong. Okay, the assumption that you made, that was wrong. So assumption wrong. So here in the question they should have mentioned, what they should have mentioned. If you here like this is my error only, because this cannot be 5 volt. So I need to change the question. I need to change it that you need to find IC. You need to find IC with VC set given. VC set is given, that is equals to 0.2 volt. I need to change the question. Why I change the question? Because like what is the scene is that I go to know that this is working in saturation region, right? So this IE current will be the same that I calculated here, because there was no assumption, because I know this will always be 0.7. So this current will be the same. Now I can give VC set that is equals to 0.2 volt. So from here to here I know the potential, then I can write down this current. But how will I write down this current? Oh, you can write down. You can write down. How you can write down? Because IC is equals to IE plus IB. Okay. So let's get to the same problem only. The problem is the same. You again need to calculate IB only. You can write down the IB. How will you write down the IB? Because you know IE current, that you know. Now one thing you know, what do you know? That this drop is 0.2 volt. This drop is 0.2 volt. This is minus 0.7, this is 0.2 volt. So what this drop will be? Minus 0.5 volt. Right? It would be minus 0.5 volt. Yeah. So it would be minus 0.5 volt. So what will be your IC? IC will be equals to, so this answer is wrong. This is not the final answer. IC would be equals to 5.5 5.5k divided by 5.5 divided by 5, because 5 minus of 0.5 divided by 5k, that would be equals to 1.1 milliampere. So your IC would be equals to 1.1 milliampere. This current would be 1.1 milliampere. Forget about this. This current is 1.1 milliampere, right? This current is 1.1 milliampere. IE current, there is no doubt this will certainly be 1.48 milliampere. So what will be your IB current? Your IB current would be 1.48 minus 1.1. 1.48 minus 1.1. That would be 0.38 milliampere. This is the final answer actually. Okay. right? So this is the final answer. Okay, one correction I would like to make here, that here I will go. So here we should not comment on IB value. We can only comment on IC value. When I was writing this point, I was also getting confused. In the previous lecture, I told you that IC should be maximum and IC should be minimum in active and saturation region respectively. But you should not comment on IB value. Why so? Because in saturation region, IB is not depending on IC. It is not only depending on IC. It is depending on IE and IC. So just now we solved this problem. Just now we solved this problem. In this problem, what did you get to know? That if you are working in active region, this was your IB current, and if you are working in saturation region, this is your IB current. So here this current is higher and this current is lower. But if you are acting in saturation region, this was your IC current, and if you are working in active region, this was your IC current. So certainly IC current here, that is higher. That is for sure, that this IC current would be higher. Okay, but if you change it, like if you talk about IB, so in IB you cannot comment. So in saturation region, we only know this characteristics. We know the characteristics between IC and VC, that this will go like this. So here this will be lesser. In saturation region of operation, IC current will be lesser than the active mode of operation, but we cannot comment on IB. So that I need to correct. So there, that should be corrected, that you cannot comment on IB value. Okay, so yeah, this is your final answer. This is the final answer, which I can, this is the final answer. This is not the correct answer. Okay, this is not the correct answer, because in this one, what did we get to know? That it was not even working in saturation region. But the question that I picked this question from GATE PYQ only. So there they changed this supply actually. Here I forgot to change the supply. That's why this question became interesting. Well and good. Let's move towards the next question. You have to find the Boolean expression at Z. Boolean expression we need to find. So these kind of questions we solved in diode circuits, if you remember. So what do? We make a table X, Y and Z. X, Y and Z. X can take 0, 0, 1, 1. Y can take 0, 1, 0, 1. If both are 0, if X is 0, that means this node is low. This node is low, that means this is off. If X is 0, then BJT is off. This node is low. This node is 0. So on a, like in a digital circuit, this will be a question of digital circuit only. In digital circuit, if X is high, then BJT is on. Then NPN is on. Sorry, not BJT. I should write NPN is on. NPN is on. And if X is low, then your NPN is off. Right? So at 0 it will be off. If this is off and Y is 0, for Y you have to apply open circuit test, because this is diode. I am applying open circuit test. So diode will be open circuited. So this is low, and if you apply open circuit test, this has already been gone. This is already gone. So there will be no current through R1. So this VCC will come here. So at this node you are having VCC, at this node you are having 0. So this diode will turn on. If diode turns on, then your Z will be equals to Y. And what is Y? Y is equals to 0. Say yes or no. Did you understand this point? X was 0, so this BJT was off. Then we need to comment on this diode. So for commenting on this diode, this was open circuited. We have to apply open circuit test. So Y was at 0 volt, and if I apply open circuit test, there was no current through this BJT. So the complete current would be, so there was no current through R1 as well. So VCC would be coming here. If VCC is coming here, then the diode is turning on. If diode turns on, Z will be equals to Y. And what is Y? Y is equals to 0. Well and good. Now if Y is equals to 1, again X is 0. If X is 0, this is off only. So again I will apply open circuit test. Here you are having 1 is equals to VCC only. 1 will be equals to high potential. This is high. High means VCC. 1 is VCC and 0 is ground. 1 is VCC, 0 is ground. So 1 is equals to VCC. So both are at high potential. P and N both are having the high potential. So you cannot comment whether the diode will be on or off. If it is on, then Z will be equals to Y only. If diode is on, then Z will be equals to Y only and Y is VCC. And if it is off also, if diode is off also, then Z will be equals to this VCC. Then in both of the cases you are having VCC only. So your Z will be equals to 1. Are you getting this point? Here what did I say? P side you are having VCC, N side you are having VCC. So you cannot comment your diode is on or off. Even if your diode was on, then your Z would be equals to simply Y only and Y is VCC. If your diode was off, then what would have happened? This is also off, this is also off, then VCC will simply come here. So Z will always be equals to 1 in both of the cases. Let's take the other case. In the other case, what will happen? If X is high, then this BJT will be on. And if BJT is on, that can be replaced with a simple short circuit. BJT is on, then that can be replaced with a simple short circuit. In digital circuits, this happens. When we study about CMOS logic, there I will tell you. In CMOS logic, I will tell you in case of NMOS and PMOS. Then same thing will go for transistor as well. That is known as transistor logic, CMOS logic and transistor logic. So in logic family, we will certainly study about all those things. So if this X node is high, then this BJT will be on. If this NPN is on, then that can be replaced with a simple short circuit. So Z will simply be equals to 0. So you don't even need to check Y, because if X is high, that will be on and Z will be always equals to 0 only. So it will always be equals to 0. So what is the Boolean expression at Z? Z is X bar Y. Although this question was of digital only, I should have put it in digital. When we study digital electronics, there I will put it. For analog, this will not be asked. Okay, in analog, in the placements or in the interview for analog profile, this will not be asked. This is the question of digital electronics only. So Z is X bar into Y, X bar into Y. These kind of questions we solved in diode circuits as well. How did I write this expression? I just need to look at this one. So X bar into Y. If you do X bar into Y, this truth table only you will get. You can make the truth table for X bar into Y. This is only you will get. Okay, let's move towards the next question. So VEB is this one. You need to find VEC potential. You need to find VEC. This is your PNP, P2N, PNP, P2N. Then the other one will be P only. P2N, PNP. VEB is 0.6. VEB. Which one is emitter? This one is emitter. This is base. So instead of writing emitter, I should only write E. E. This is emitter. This is base. This is collector. So we are not mugging up anything. We know this is PNP, P2N, and VEB potential given. So V emitter to base potential is given. So this will be 0.6. So 3 minus 0.6, that will be 2.4. If this is 2.4, what will be the current here? That current will be IB. IB current would be 2.4 divided by 60. 2.4 divided by 60K. 2.4 divided by 60. That would be 0.04 milliampere. IB current would be 0.04 milliampere. What do you need to find? VEC potential you need to find. VEC. So again, I will make an assumption, because for finding VEC potential, I need this current, right? Because collector potential I know, emitter potential I know, but I need to find collector potential. For that, I would need this current. So assuming active. So what will be your IC? This is your IC. IC will be beta IB. Beta value is given 50. 0.04 into 50. That would be 0.4 into 5, 2 milliampere. This current is 2 milliampere. If this current is 2 milliampere, what will be your VC potential? VC potential will be 500 into 2 milli. That would be 1 volt. This will be your VC potential. Let's make the BJT now. This was the BJT. P2N, PNP. Where this node is? This node, collector. This node is at collector node is at 1 volt. Where this node is at 3 volt emitter, and this node is at 2.4 volt. 2.4 volt. P is at higher potential, N is at lower potential. This is forward biased. N is at higher potential, P is at lower potential. This is reverse biased. What was this? This was emitter junction. This was emitter junction. And what was this? This was collector junction. So emitter junction is forward biased, collector junction is reverse biased. Which is the region of operation? Active region. So assumption is correct. Active. Assumption is correct. If assumption is correct, then what will be your VEC potential? VEC potential will be 3 minus 1, that is equal to 2 volt. Did you need to mug up anything here? No. You just made the BJT. Whether it is PNP or NPN, we can solve the problem efficiently. We don't need to think much. Arrow direction P to N and then P. Arrow direction, that means that will be emitter, other one will be collector, that will be the base. All the equations are same. IB equals to 0.04 milliampere. Then I have assumed to be inactive. Then I will get my IC value. Then I get my BC potential. Everything is same. Then I know all the potential across the BJT. Collector potential I know, emitter potential I know, and the base potential I know. So what was my collector potential? That was 1 volt. Base was at 2.4. Then I wrote it. Okay. Then I go to know this is P, this is N, this is P. This junction was forward biased. This junction was reverse biased. What was this junction? This junction was emitter junction, and this junction was collector junction. So collector junction was reverse biased and emitter junction was forward biased. So what was the region of operation? That was active only. So assumption was correct, and every calculation that we did, that holds true. So VEC would be 2 volt only. Well and good. Let's move towards the next question now. What you need to find? Reverse saturation current is 10 to the power minus 13 ampere. We need to find emitter current. Beta is equals to infinity. If beta is equals to infinity, they didn't even give this one, so we don't need that. If beta is equals to infinity, then IC equals to IE. IC equals to IE. They should have given this potential, no? No, they don't need to give this potential. Yeah. So IC equals to IE. And what is the equation? IS exponential VBE by VT. This is the equation, no? But that is only for active region. Active region. This equation is only there for active region. Say yes or no. I told you this region is always there for active region. This device is working in active region or not? Let's check. This was the diode, so P to N and N. This is 0.7, so suddenly this is forward biased. Here N and P both are at same potential. N and P both are at same potential. So can you tell whether it is reverse bias or forward bias? Both are at same potential. P is at 0.5, N is at 0.5. Both P and N are at same potential. So this is known as edge of active region or edge of saturation region. This is the edge. This is the edge. This is the edge. After that, it can change. Like if VC somewhat rises or it goes low, then it can change. It is the edge of saturation or edge of active region. So here this equation will be valid. In this case, this equation will be valid because this is the edge of saturation. Also, beta value is also given very high. So I told you beta value that much high will be in active region of operation only. So beta value is very high, so you can take it to be in active region only, right? So reverse saturation current is given, that is 10 to the power minus 13. So whenever this expression, this circuitry is given, no, you will by default consider to be in active region only. This circuitry will be used in amplifiers as well because this is the edge. Here, this is the edge of active region and edge of saturation region. This point is this one, edge. This is the edge. So you will by default consider it to be in active region. Okay. So this particular circuitry will be used in diode circuits as well. Not in diode circuits, sorry, in MOSFET amplifiers as well. And this is known as diode connected configuration. It is actually known as diode connected. Why it is known as diode connected? Like this is your BJT. Let's just say this is your BJT. So P to N, can you consider that as a diode only from P to N? This was your P node and this was your N node. Can you consider that as a diode? And whatever that was there, that was shorted, and this was your N. These two were shorted. So this configuration, this much of configuration is replaced by this, and this much of configuration is replaced by this. So that is why it is known as diode connector. Like effectively you can say that in complete BJT from N to N I can see a diode. This was your N node. This N node can be copied here. From N to N I see a diode. So that's why it is known as diode connected transistor. Okay. I guess this is the only reason why it is known as diode connected transistor. I tried to search about it, but I did not get much material. So I can assume that as a diode. So that's why it is known as diode connected. This is what I think. Okay. And I might have read it somewhere as well, but there are not much material available like why it is called diode connected. You can search about it if you have time, otherwise don't waste your time. Okay, so IS exponential VBE is 0.7 volt. What is VT is 0.026. What will be the answer? 0.7 divided by 0.026 exponential 4.92. 4.92, it would be 49.2 milliampere. 49.2 milliampere. This is your IC current, right? So this is 10 to the power 11 I am getting. So 10 to the power minus 2 it will be. So 49.2. Yeah, 49.2 milliampere. This is the answer we are getting. Well and good. Let's move towards the next question. Beta is equals to infinity. You have to find the I current. Beta is equals to infinity. You have to find the I current. This current will be 0. This current will be 0. If beta is infinity, 0 ampere. 0 ampere. What this potential will be? You can apply the voltage division. Let's call this node as Vx. What your Vx would be? Vx would be 1.65 divided by 1.65 plus 1.85 plus 6.5 into 10. So that would be equals to 1.65 volt only. So it will come out to be 1.65 volt. If this is 1.65 volt, what is VB potential given? 0.65. This is your 0.65. What this potential would be? 1 volt. Because this is 1.65, this is 0.65, so this potential will be 1 volt. So what will be the current here? Current here will be 1 milliampere. 1 volt divided by 1 kilo ohm, that will be 1 milliampere, and the same current will be flowing through the complete circuit because beta is equals to infinity. This current is 0. The same current will be flowing here. Complete the same current will be flowing through the MOS. So I will be equals to 1 milliampere. I will be equals to 1 milliampere. Are you able to understand this point or not? Vx potential is 1.65, then this node is 0.65, so this node will be 1 volt. If this node is 1 volt, then this current is 1 milliampere. The complete current is flowing through the in this complete BJT circuit. So this I will be 1 milliampere only. Here you don't need to check the region of operation. Why? Did I apply IC equals to beta IB here or I equals to beta plus 1 IB here? No, I did not apply, right? Did I apply IC equals to beta IB or I equals to beta plus 1 IB? No. So why do you need to check the region of operation? You don't need to check, right? Also beta is equals to infinity. If beta value is that high, that means certainly it is working in saturation region, sorry, active region only. If it is if beta is that much high, if beta is infinity, that means certainly it is working in active region. So this I should write active region. Let me check how much questions are remaining. 1, 2, and 3. Okay, let's finish it off. IC value you again need to find. Beta value is 99. IC value you need to find. Here options are not given. This is a numerical answer type question. Options are not given. So you cannot take risk. You cannot say that this current will be 0. This current will be IB this time. Because this will be a numerical answer type question, right? Only numerical answer type, because they did not give the option. So you have to tell the exact answer now. So you cannot say that this current will be 0 ampere, sir. You cannot say that. Now, how I will make my calculation easier? What do you think? Can I find VTH and RTH here? If you are following my course right from the beginning, it will not be tough for you. VTH and RTH. What is your VTH? VTH is open circuit voltage. Thevenin voltage is always open circuit voltage, because then this node will be 0 ampere. So Thevenin voltage is always open circuit voltage. So there I am finding VTH and RTH. So what will be my VTH? VTH is always open circuit voltage. So this node will not drive any current. This branch will not drive any current. So what will be my VTH? VTH will be simply 10 into 60 divided by 60 plus 60. That would be 5 volt. What will be my RTH? RTH will be 60 and 60 will come in parallel. I am finding Thevenins of this one. 60 and 60 will come in parallel. That would be 30 kilo. Right? So how will the circuit look like? This is 10 volt. This is 100 ohm. This is the BJT. This is 400 ohm. This is 5 volt. This is 30 kilo ohm. Did they give VB equals to 1 volt? VB equals to 1 volt. This much is given 1 volt. I will apply my KVL here. This will be my KVL. So what I can write? 5 would be equals to 30 IB plus 1 plus 0.4 IE. IE I can write beta plus 1. So that would be 100 IB. Did you understand what did I do? 5 is equals to 30 IB plus 1 plus this potential. 5 equals to this potential plus this potential plus this potential. So 5 is equals to 30 IB plus 1 plus 0.4 into 100 IB. Right? So 4 will be equals to 70 IB. So what will be your IB? IB would be equals to 4 by 70. Again you have made the assumption, assuming what? Active. Then only beta plus 1 IB is applicable. So that is 0.057 milliampere. 7 milliampere will come because here I have assumed IB to be in milliampere. So IB is 0.057 milliampere. Okay. Then what will be your IC? IC you need to multiply with 99. 5.665. IC is 5.65 milliampere. And what will be your IE? IE would be divided by 99 into 100. Look, it would be some beta plus 1 only, not 0.0 into just 100 of this. Why I am doing so much of calculation? It would be some 5.7 milliampere only. No, I'm really sorry, I'm wasting the time. It would be just multiplied with 100, so 5.7 milliampere. So IE will be 5.7 milliampere. But is that answer correct? No, because we have to check if our region of operation is the same or not. So can we find this potential VE? Then can we find this potential VC? And then we can find VB potential as well. What will be our VE? That would be 0.4 kilo ohm into 5.7. 0.4 into 5.7. 2.28. What will be my VC? VC would be 10 minus 0.1 into 5.65. Right? 10 minus 0.1 into 5.65. 0.1 into 5.65 minus 10. Pretty high. It is 9.43 volt. And what is your VB? VB is just plus 1. VB is V plus 1. This is 3.28. So these are the potential. You can check it. It will certainly be in active region only. You can make the BJT. This node you can write down, this node you can write down, this node you can write down. What you will understand? These are in reverse bias and this is in forward bias. Directly you can see VC is pretty high. If VC is that much high, that means N side is having so much of negative potential. So that is in active region only. So whatever the calculation that you made, that was correct. So what did they ask? IC. So IC will be 5.65 milliampere. So this is the final answer. IC is 5.65 milliampere. IC is 5.65 milliampere. This is the final answer. Well and good. Let's move to the next question. You have to find VC potential. VC potential you have to find. Okay. Pretty easy it is. Very easy. Let's take this array. Yeah. So VB value they did not give. They should have given VB equals to 0.7 volt. VB is equals to 0.7 volt. This node is 0.7 volt. So what this current would be? 2 by 100 milliampere. Right? This current would be 2 by 100 milliampere. 2 by 100 milliampere. What this current would be? 2 milliampere only, because 2 by 100 into 100. This would be 2 milliampere only. 2 by 100 into 100, 2 milliampere. So I can apply nodal here because I know the current in this direction, that would be Vc minus 10 by 2k plus Vc by 2k plus 2 milli is equals to 0. So 2 Vc minus 10 plus 4 is equals to 0. Vc is equals to 3 volt. Vc is equals to 3 volt. Right? 3.5, 1.5. Yeah. Vc is equals to 3 volt. That's it. That's the final answer. Nothing else. And again, I have to check the region of operation. If Vc is 3 volt, then again it is in active region only. Again, you can make the BJT. This was 0. This was at 0.7. This is 3. This will be in active region only because this will be reverse biased. Right? Let's move to the last question. Here you need to find for V0 to be equals to 5 volt. What should be the RC? V0 should be equals to 5 volt. What should be the value of RC? So what kind of BJT is that? We don't know. But P to N, the arrow will be from P to N. So it will certainly be P. So this is PNP kind of transistor, PNP. They can rotate the structure, they can rotate the BJT in any direction. You have to check P to N, then P. This is PNP. PNP. What this potential will be? They have written the mode now. VEB is equal to 0.7. So you have to think what you need to take. So my error. We need to take from this to this direction, no? From P to N. Like if I made the BJT like this, where we were taking the potential from P to N, this was 0.7. Again from P to N, this would be 0.7. Right? If this is 0.7, then what this node will be? 10 minus 0.7. This node will be 9.3. So how I can show it? This was 100k. I can write 100k here. This was 10 minus 0.7. This would be 9.3 volt. This is 9.3. What will be the current here? This will be your IB current. So your IB current is 9.3 by 100k. 93 microampere. Now IC current will be flowing in this direction, and sorry, IE current is flowing in this direction. From the arrow, you know IE current is in this direction. So IE is equals to IB plus IC. So IC has to flow in this direction. So the drop will be this one. So V naught is equals to IC into RC. What is IC? IC is beta IB. Beta is 50. So 93 into 50. Again, you are assuming it to be in active region. So 50 into 93, 4.65 milliampere. 4.65 milliampere. No, we should not assume. Here we will get to know, na, because they have already given your V naught to be 5 volt. So V naught is 5 volt. So here we can certainly check. If this is 5 volt, this node is at 10 volt and this node is at 9.3. So this is P and P. P is at higher potential, N is at lower potential. This is forward bias. P is at higher, N is at lower. Here this was P and N. N is at higher potential and P is at lower potential. This is reverse bias. This was your collector junction, this was your collector junction, and this was your emitter junction. This was your collector, this was your emitter junction. That means it is in active region only. So if it is an active region, you can apply all these equations. So what is your V naught? V naught is 5. What is your IC? IC should be 4.65 milli into RC. So what is your RC? 5 by 4.65 reciprocal into 5. 1.07 volt. Sorry, 1.07 kilo ohm. So this is the final answer. Your RC value is 1.07 kilo. That's it. So you have solved this assignment. This was a very good assignment. It took us around 80 minutes or 70 minutes. Right? So you must be comfortable with the DC analysis now. In the next assignment, we are going to solve very good question. So these you can try. This is the first question. This is the second one. This is easy. This is very easy. Here I should have mentioned VBE potential. VBE should have mentioned VBE equals to 0.7. VBE is equals to 0.7. It should be given. Then we will solve this question. You have to say that both transistors are matched. It is given that both transistors are matched. What do you understand by matched? Matched means both are having the same reverse saturation current. That's it. Both are having the same reverse saturation current. If they are saying both transistors are matched, what does that mean? Both are having same reverse saturation current. That's it. Matching doesn't mean VB value is same. Matching only means both are having the same reverse saturation current. That's it. Okay. Then this particular question, very easy it is. This is good one. This question is good one. Okay. So that we will solve. In this I will discuss something as well. So that thing I will discuss. So yeah, that's it. Or okay, this was asked in the written test. This question is the same as the previous one. Just some changes I did. So if you are solving it on your own, you can solve this one. Okay. You can solve this one. And this question. So these questions you can solve. In the next video, we are going to see the solution of all the questions. Okay then, thank you. Hi everyone, so let's solve this assignment. This is the assignment number 19 and this is the first question. So beta is given infinity, VB1 value is given, VC set value is given. So what they are saying, switch is initially closed and now it is opened at t equals to 0. You have to find the time t at which that transistor is leaving the active region of operation. Okay, so this is the question. So for t less than 0, the switch is closed. So let's make the circuit for t less than 0. For t less than 0, the switch is closed. This switch is closed. So this is the circuit. Right? Now what is happening here? This is 0.7 voltage drop. This is 0.7 voltage drop. So what this voltage will be? Minus 5 minus 0.7. This voltage will be minus 5.7 volt. Right? If this is minus 5.7, then what this current will be? Can you tell? Let's just say this current is I. So what this current would be? Minus 5.7 plus 10 divided by 4.3k. So that would be 1 milliampere. So this I would be 1 milliampere. And since beta is equals to infinity, then you can say this current will also be 1 milliampere, because IE would be equals to IC. So what is happening here? 0.5 current is flowing here, 1 milliampere current is flowing here. That means certainly from here 0.5 milliampere current would be coming, right? Now from where this current would be coming? From this side or from this side? From the capacitor side, no current will come. Why is it so? Because capacitor is having 0 voltage across it, that is fixed, and this is a short circuit path, so the current will flow from the short circuit path, right? The capacitor is having 0 voltage. This node is equals to this node, this node is equals to this node. This node is 0 volt only. So capacitor is having 0 voltage. If I call this is your VC, if this is your VC, then what is your VC 0 minus? VC 0 minus is 0 volt. So for t less than 0, the capacitor does not gain any voltage. The capacitor does not gain any voltage. Now what happens at t greater than 0? At t greater than 0, the switch is opened. So if switch is opened, then this path is gone. Switch is open, then there is no use of this path, because this path will not drive any current. So this path is gone now. This is the circuit. Okay. Now this is your circuit. Well and good. Now what is happening? There is the same 1 milliampere current here. The current is 1 milliampere. Now this capacitor is driving 0.5 milliampere current, right? Because this 0.5 milliampere current will be flowing through from the capacitor now. For t less than 0, it was flowing from the short circuit path. Now the current is flowing from the capacitor. So what will be your VCT equation? VCT equation. This node, this particular node, let's just say I call this particular node as VC, because this is 0. So this particular node is going down because capacitor is getting charge in this direction. Say yes or no. Capacitor is getting charge in opposite direction. So what will be your VCT? VCT would be simply 1 by C. 1 by C, and this is a constant current. So 1 by C, what is C? That is 5 micro into I dot dt. What is I? I is a constant current, 0.5 milli, because this is a constant current, right? Because this is minus 5 until the transistor is on. This is a constant current, and this is also a constant current. So certainly this will be a constant current only, right? So 0.5, we are starting from t equals to 0 till some time t into dt, right? So 100t, this is being 100t, right? 1 by C, 0.5 milli, 5 into 10 to the power minus 4 divided by 5 into 10 to the power minus 6. So it would be 100t. So this would be 100t. VCT is 100t. Now what they are saying, the time t at which the transistor leaves the active region. So at t equals to 0 plus, in which region transistor is working? At t equals to 0 plus, let's check that out. We are making the transistor. This node was at minus 5 volt. This node was at minus 5 plus 0.7 minus 5.7 volt. What about this node? This node was at VC. This is your N, P, N, right? No doubt about it. No doubt about it. N, P, N. So what is your VC 0 minus? VC 0 plus, like at t equals to 0 only. At t equals to 0 plus. Immediately when the switch was turned off, what was your VC 0 plus? That was 0 volt. So at that time, what was the region of operation of transistor? N is at 0 volt, P is at minus 5. That means this is reverse bias, right? N is at 0 volt and P is at minus 5. So this is reverse bias. So it means active region of transistor, right? So now the region is active. Now what is happening? VC is going down. VC is going down. This particular node is going down. So what do you think what is happening? The reverse bias is decreasing. Say yes or no. VC, if VC goes down, if this node goes down, that means N potential is becoming low. N potential is becoming low. P is constant. P is at minus 5. Now N is going down. Initially N is at 0. Now it is slowly going down. Let's just say N is at minus 1 volt. What was the reverse bias here? Here the reverse bias was 5 volt, because P was at minus 5 and was at 0. So here the reverse bias was 5 volt. If N is at minus 1 volt, what is the reverse bias now? 4 volt only. If N is at minus 3 volt, what is the reverse bias now? 2 volt only. If N is at minus 5.1 volt, Is there any reverse bias? No, it has become forward bias because P is at lower potential, N is at even lower than that. Okay, that means P will be at higher potential, N will be at lower potential. What I am saying that P is at -5 and N has become to -5.1. N is going down, down. It has gone to -5.1. That means this would be forward biased. And now your transistor will be working in saturation region. So this is what they are asking. You want your N node to go down. Your N node is going down. Till what point it will act in saturation region? Sorry, till what point it will act in active region? This is what they are asking. And they have also given VC sat value. So what is the VC sat potential? They have given 0.7 volt. So if VC is going down, that means transistor moving towards saturation. Moving towards saturation. Given VCE sat is equals to 0.7. VCE sat is given as 0.7. VCE sat, this is VCE sat, right? This is 0.7. What does that show? This node is -5.7. If your VC is, look, emitter is at -5.7, that's for sure. So VC minus VE, that means -5.7 is equals to 4.7. If your VC is at -5 volt, if VC is the -5 volt, that is the saturation condition. If VC is -5 volt, at that time you will reach your saturation. If VC is -5 volt, that is the saturation condition. So you need to find the time. Here minus sign will be there because it was charging in opposite direction. Here minus sign will be there. So you need to find the time at which VC becomes -5. So just find the time -100t, or I can write -100t is equals to -5 volt. So T is, let me check the calculation. T is some 50 millisecond, right? 5 into 10 to the power -2, 50 millisecond. So at T equals to 50 millisecond, your transistor will go into saturation region. Okay. So what was happening? Initially, the complete current was flowing through the short circuit path. Then the current started flowing, 0.5 milliampere current started flowing through the capacitor. So what is the capacitor voltage now? Capacitor voltage is -100t. The VC node, the collector node is going down. If the collector node is going down, that means the reverse bias across the junction capacitor, the reverse bias across the collector junction, the reverse bias across the collector junction is going down. That means transistor is moving towards saturation. The transistor is moving towards saturation. That means forward bias is increasing here. So transistor is moving towards saturation. When it will be in saturation? When VC is equals to VC sat. VC is equals to VC sat. That means if VC is equals to -5 volt, when VC is equals to -5 volt, at that time your transistor will be in saturation. So for that you just need to put when you will get -5 volt. That's it. Well and good, everything is crystal clear. It was a very easy problem. There was nothing difficult in that, right? Let's move towards the next question now. Let me check the calculation if everything is fine. Okay, that would be 10 to the power 2 only. Yeah. Okay, let's move to the next question. You have to find, what you need to find VC. What you need to find, I forgot to write. Find VC. This is the VC. This is what you need to find. VB is 0.7. This node is 0.7. Mode of VB, they should write. Mode of VB is 0.7. Here I also need to write 0.7. In which direction I will write? From P to N. From P to N. P to N. P to N. So this is 0.7. This is also 0.7. Which kind of transistor is that? PNP. And which kind of transistor it was? From P to N. The arrow direction P to N. So NPN. This was NPN. This is PNP. So 0.7, then 0.7. So 2.5 minus 0.7 minus 0.7. So what this node will be? So this node will be 2.5. From here you need to apply the KVL. in this direction. 2.5 minus 0.7 minus 0.7. 2.5 minus 0.7 minus 0.7. So it will be 1.1 volt. So this node is at 1.1 volt. 1.1 minus 1. How much current is flowing here? 0.1 by 10. This is your IB current. Basically your IB current is 0.1 by 10k. So it would be some 0.01 milliampere. Again you will make an assumption. What is the assumption? That it is working in saturation region, sorry, active region. Assuming active. If it is working in active region, what will be your VC? VC will be 0.01 milli into 1, sorry, 0.01 milli into what is your beta? That is 50. What I mean to say, what is your VC? VC is IC into 1 kilo ohm. VC is IC into 1 kilo ohm. IC into 1 kilo ohm. What is IC? IC is beta IB. So beta into 0.01 milli into 1 kilo. So VC is 0.5 volt. But this is not the final answer. Again, you need to check if this device is working in saturation or not. Sorry, if this device is working in linear or not. This is what you need to check, linear or active. If this device is working in active region or not. This is what you need to check. Why you are not checking for this one? For this one thing is for sure that these two are shorted. So certainly it is working in active region. It is on the edge of active region. Also, one thing I am sure is that I don't need to know the region of operation for this one, because here I did not apply IC equals to beta IB. Did I apply IC equals to beta IB here? No. I applied IC equals to beta IB only here, because here I found the value of IB, then I had to apply IC equals to beta IB. So in this one I did not apply anything. So for this I don't need to check. Only for this one I will check. So for this one, what this node was there? This node was at 1.8 volt. This node was at 1.8 volt. This node was at 1.8 minus 0.7. This was at 1.1 volt. And what this node was at? This was 0.5. So P and P. What about this? P is at higher potential, N is at lower potential, forward bias. And what about this? P is at lower, N is at higher. That means this is reverse bias. This is an active region only. So whatever the assumption that you made, that is correct. It is working in active region only. So VC is equals to 0.5 is your final answer. Well and good. Let's move towards the next question. So what is this? If you have studied MOSFET amplifier from me, if you have studied MOS, what kind of structure is that? Differential amplifier, right? This is differential amplifier. We will study differential amplifier, no worries. In BJTs as well, we will study the differential amplifier. But let's solve this problem. This is that complete DC analysis. No AC analysis is required here. Only DC analysis is there, because we haven't even moved to small signal analysis yet. So both transistors are matched. VB on is 0.7, beta is equals to 100. You need to find V naught when Vin equals to 5 volt and Vin equals to 0 volt. Both transistors are matched. VB on is 0.7. Beta value is 100 for both of them. What do you mean by matched? Matched means IS is same. That's it. Nothing else is same. Matching means only IS is same. That means reverse saturation current is same. Nothing else. Current is same. That's it. Your reverse saturation current is same. This is what we mean by matching. Right? You need to find V naught for both of the cases. So first let's take the first case. Vin equals to 5 volt. When Vin is equals to 5 volt, let's take that case. what they have given? They have given that VB on is 0.7 volt. Now let's just assume if both transistors are on, if both of the transistors are on, then this will be 0.7 volt, right? And this will also be 0.7 volt. If I say both of the transistors are on, then what will happen? This transistor will say that this node will be at 5 minus 0.7. That means this node will be at 5 minus 5 minus 0.7. What that would be? 5 minus 0.7. It would be 4.3 volt. If both of them are on, if Q1 and Q2 are on, then this Q1 is saying that this particular node, let's just call this node as Vx. So Q1 is saying that Vx will be at 4.3 and Q2 is saying that this Vx will be at 1.8. It cannot happen, right? One time we are saying that it will be 4.3 and other time we are saying that it will be 1.8. Can it happen? No, it cannot happen. So certainly both transistors cannot be on. Both transistors cannot be on at a single time. Second, what was the first assumption? First assumption that Q1, Q2 both on. That has come out to be wrong. You have to check by your brain only. You have to apply your brain. That's it. Nothing else. Second thing. What I am assuming, Q2 is on and Q1 is off. This is what I am assuming. Q2 is on and Q1 is off. So Q2 is on. If Q2 is on, then what will happen? This will give 0.7 voltage drop. So what will be the potential here? That will be 1.8 volt. Basically, this will be 1.8 volt, right? 2.5 minus 0.7, it will be 1.8 volt. So what this potential will be? It will be 3.2 volt. They have given that VB on is 0.7. If you assume that Q2 is on and Q1 is off, you are getting that your VBE for Q1, here you are getting that your VBE for Q1 is 3.2 volt, and that will turn on this transistor. So you assume that your Q2 is on and Q1 is off. If you assume that, you analyze the circuit and got to know that my Q1 is getting on. So that means this condition is also wrong. Did you understand this point or not? I assumed my Q1 is off and Q2 is on. If Q2 is on, then this will give 0.7 volt drop here. This will be 1.8. If this is 1.8, then this will be 3.2 volt. They said that minimum VB required is 0.7 volt. It is greater than that, then Q1 is turning on. First I assumed my Q1 is off, but by its own it is turning on. By its own it is turning on. That means it is again turning on. We first assumed it to be off, but eventually after analyzing it, we got to know that it is turning on. So this condition is also wrong, right? That Q2 is on and Q2 is off. Because eventually we get to know that both are turning on. And if both are turning on, that is also not possible. So which one is left? The last condition is left, that Q1 is on and Q2 is off. Q1 is on and Q2 is off. So if Q1 is on, then what will happen? If Q1 is on, then what will happen? This node will be at 4.3. And if this node is at 4.3, then what this potential will be? This potential will be some negative potential, right? This potential will be some negative potential. 4.3 minus 2.5, that would be 1.8, minus 1.8 volt. So this is some minus 1.8, but minimum required was 0.7. So this transistor will not even turn on. That means this transistor will be turned off. So this is the correct condition. If I assume Q1 to be on and Q2 to be off. So what did I get to know? That this Vx node is going at 4.3. Vx node is going at 4.3. And if Vx is going at 4.3, this particular node Vx, if this goes at 4.3, then Q2 will be off only. So whatever the assumption that I made, that Q1 is on and Q2 is off, that is correct. So we started with the assumptions. We started with first assumption, both are on. Then Vx node was getting two values, which is not possible. Then we said that Q2 is on and Q1 is off. Then both were turning on. And now we said Q1 is on and Q2 is off. Then I got to know that my Vx node is 4.3 volt. If that is 4.3 volt, that means certainly Q2 is off only. So here Q1 was on and Q2 is off. So if two transistors are connected in this manner, then the one which is having higher potential, that will be on. The one which is having higher potential at base, that will be turned on. You can analyze it in any value. You can take 2.6 volt here. You can take 2.6 volt here. If you take 2.6 volt here, then only Q1 will be on and Q2 will be off. For both of the transistor to turn on, you have to keep both of the potential equal, 2.5 and 2.5. Only at that moment only both will be turned on. But if you want to turn on only one, then the one you which want to turn on, that should have a higher base potential. So this was having higher base potential, so this Q1 will turn on and Q2 is off. Okay, so this is the condition. So now Q2 is off. So what is the final conclusion? That Q1 is on and Q2 is off. This is the final conclusion. So if this is off, then complete 1 milliampere current will be taken by it, right? Because if this is off, that means it will act as open circuit only. This will act as open circuit. If Q2 is off, then it will act as open circuit only. So there will be no current here. This current will be 0 ampere. So what will be your V0? V0 will be 12 volt. V0 will be simply because the resistor is having 0 voltage drop, so V0 will be 12 volt. That's it. So this was the first question. Let's take the other one. B. In the other one, what they are saying that V in should be at 0 volt. This should be at 0 volt. So what do you think, which one will turn on? Which one will turn on? Q2 will turn on and Q1 will be off. How will you analyze it? If Q2 is on, then what this potential will be? 1.8. And if this is 1.8, then this is having some minus 1.8 voltage. So that will turn off this one. So this is turned off. Then other condition also you can check that if your Q1 is on, then what will happen? This will be some 0.7 voltage drop. So what this potential will be? This will be some 0.7. If this is some minus 0.7, then this will be 3.2 volt. If this is plus 3.2 volt, then this will also turn on. So both Q1 and Q2 will turn on, which is not possible. So only one has to turn on. So that is Q2 will turn on and Q1 will be off. Because if Q1 is off, then Q2 have no problem with that. Well and good. Okay, this was grounded only. So this is the final condition that Q2 is on and Q1 is off. That means this will drive all the current. This will take 0 ampere current. This will take 0 ampere current. And now this one will take all the current, that is 1 milliampere. So this is taking all the current, that is 1 milliampere. So what will be your V0? So V0 will be 12 minus 5 into 1. That would be 7 volt. So these kind of questions can be asked in your examination. This was a very, very good question. Okay. So these kind of questions you can expect from differential amplifier DC analysis of differential amplifier. Let's move to the next question. In the circuit shown below, what is the output voltage if the silicon transistor, if a silicon transistor Q and ideal op amp are used? Okay. Here you don't know whether the transistor will be on or off. You don't know that. First you have to assume the transistor is on. I am assuming my transistor is on. If my transistor is on, then there is a negative feedback, right? If my transistor is off, then negative feedback is not there. If my transistor is off, then negative feedback is not there. So what will be the current here? 5 ampere, right? Now the same 5 ampere will be flowing from here. If the same 5 ampere is flowing from here, that means the current is flowing from the upward direction, in this direction. So my assumption is correct, right? Did you understand this point or not? I have to make up one more question here. Then you will be able to understand the point more deeply. So I will make up one more question. Yeah, so this is the other question. You again have to find V0. Here just I made one change, that is this is your PNP, this was your NPN, right? So what did we say? First we assumed our transistor is on. Here I am assuming my transistor is on. So if my transistor is on, then only virtual short is valid, because then only feedback will be there. Otherwise feedback will not be there. So I am assuming my transistor is on, then feedback is present. So this node will be copied here, this node will be 0. If this node is 0, that means this is driving 5 milliampere current. 5 milliampere current. So if this is driving 5 milliampere current, then the same 5 milliampere current is flowing through this Q as well. and the direction of that current is this. So IC direction, IE direction, all are same, and this current direction is also same. So certainly Q is on. Q is on. So that is on. And if that is on, then this node is 0, this node is 0.7. This voltage drop is 0.7. So what will be your V naught? V naught will be 0 minus 0.7 volt. That would be minus 0.7 volt. 0 minus 0.7 volt. So V naught will be minus 0.7 volt. Right? What about this one? In this one, again, I am assuming Q is on. Assume Q is on. If your Q is on, this is what I am assuming. Transistor Q is on. Then virtual short will be valid. If virtual short is valid, then this 5 ampere current, 5 milliampere current will be flowing in this direction. Then the same current will be going in this direction. Now, is that possible? The current should have been this one. The current should have been this, but the current is flowing in the opposite direction. The current should have been this, but it is flowing in the opposite direction. So, what I got to know? Q1 is actually off. Did you understand this point or not? What did I do? First, I saw that there is 5 milliampere current that is flowing through this transistor. In the upper question, I am saying, in this question, the current was same, so the transistor was on. Here, I assume that in this question, I assume that my transistor is on. So, if that is on, then virtual short is valid because feedback is present. Negative feedback is present, virtual short is valid. Then there will be this 5 milliampere current that will be flowing through the transistor. But the current is in the opposite direction than the actual current. The current should have been from down to up. It is flowing from up to down. So that means my transistor is off. And if transistor is off, that means no feedback. No feedback. And if there is no feedback, then what will be the circuit? This will be a simple circuit like this. There is no feedback. This positive node is grounded. This is your V naught. This was your 5 volt. This was your 5 volt. This was your 1 kilo ohm. So this node is open circuited. So this will drive 0 ampere current. Now this is gone. This branch is gone. This branch is gone. So there is no feedback branch. So this 1 kilo ohm will drive 0 ampere current. So finally 5 volt will reach here. So what will be your V naught? V naught will be minus 15 volt. Right? V naught will be minus 15 volt. So here your V naught would have been minus 15 volt. But for this question answer was minus 0.7 volt. Did you understand this point or not? Transistor was off. If transistor was off, then this was driving 0 ampere current. 1 kilo ohm was driving 0 ampere current. So 5 volt is exposed to the negative terminal. That means output will be saturated at minus 15 here at the negative saturation. So what is the negative saturation? That is minus 15 volt. Well and good. Let's move towards the next question. So this is actually a very good question. So for this I am going to make a separate video. So in a separate video we are going to see it, but in the course I will attach that video. I will attach that particular video. So now I will end this video and I will make the other video. So in that I have to make some more points. So let's check this out. Let's check out this question. Okay then. Hi everyone. Let's solve this question. This was a very good question which was asked in written test of some IIT. Okay, it was asked in written test of some IIT for M.tech admission. So like in this question I have written that you need to determine T on such that your transistor are never entering into saturation region. Okay, never entering into saturation region. What do you understand by this line? Your transistor never enter into saturation. That means your transistor have two options. It can go into active, it can go into cutoff as well. Your transistor have two options, active and cutoff. What did they ask? They said that your transistor should never leave the active region. The same question is there, just the language difference is there. In the language they wrote that transistor never leave the active region. What do you understand by this line? Never leaving active region means it should stay in active only. It cannot go into cutoff, it cannot go into saturation. But in this particular problem, the transistor will go into cutoff region. So that was the error. So let's solve the correct question. Let's solve this one. And yeah, before starting the solution, let me clear one thing that I am not offending anyone, neither I am disrespecting anyone here. Okay, I know this question is sold by some other educators as well, and he is like very talented. I highly appreciate him as a teacher. When I was a student as well, I always appreciated him. I always appreciated his teaching. He is very good, and it is really appreciable that he is bringing these kind of questions which no one actually bring. Okay, and yeah, so and that op-amp video I made where I discussed gate 2024 question. In that as well, I did not mean to offend anyone or disrespect anyone there. Like I have great respect for all the teachers who teaches, right? So yeah, in one of the video, I saw like sir, I thought sir is taking some offense, but I never intended that. I have huge respect for him, and I also like get to learn a lot of new things from him. So yeah, so let's start the solution. And like there are some people who may claim that you are copying the solution of some educators or anything like that. No, I'm not doing it. I have solved the same kind of question in my YouTube channel 1 year back. Okay, you can see it. The same circuit I have solved 1 year back. So hopefully no one will say that I am copying. Okay, yeah. So yeah, with this, let's start the solution and let's see how we will solve these kind of questions and what was different in this question. Okay, so let's start the solution. So transistors are given, input waveform is given, your capacitor is initially charged to 5 volt. The capacitor is initially charged to 5 volt. The input to Q1 transistor is shown. Input to Q1 transistor is shown. You have to determine T on such that your transistor never enter into saturation region even after arbitrarily long time. Okay. So for this is your T equals to 0. This is your T equals to 0. Let's just call this time as T1, this time as T2. So basically T1 is equals to T on only, right? So capacitor is initially having 5 volt. So you don't need to analyze the previous stage. For T less than 0, you don't need to analyze that. Why you don't need to analyze that? Because they have given your capacitor has initial voltage of 5 volt. No matter what was happening before T less than 0, you don't need to analyze that. They have already given capacitor is having 5 volt. So we will analyze the circuit from T greater than 0 only. Generally, we start analyzing the circuit from T equals to minus infinity. But here they have given the initial condition, that is that your capacitor is having 5 volt. So we will start the circuit from there for T equals to 0 plus. So let's see what is happening at T equals to 0 plus. So this node is VC and this is having 5 volt at T equals to 0 plus. At T equals to 0 plus. What is the input? Input is 3.7 volt at T equals to 0 plus. This input is 3.7 volt. This input is 3.7 volt. What is VB potential? That is 0.7. So what will be this potential? That will be 3 volt. So what will be the current here? 1 milliampere, right? And this is P and P, from P to N. So what this potential will be? This will be 0.7. What will be the current here? This will be 8 volt. So current here would be 2 by 4. That would be 0.5 milliampere, right? Now this capacitor is charged to 5 volt. Now what is happening? From the upward direction, 0.5 milliampere current is coming, and in the downward direction there is 1 milliampere current. Beta is equals to infinity, you can take. So this same current will be flowing here and the same current will be flowing here, and this is your capacitor. This is your capacitor. This I am calling VC. From upward direction 0.5 ampere current is coming, and from the downward direction 1 milliampere current is going there. So what do you think what would be happening? 0.5 milliampere current would be flowing in this direction. Say yes or no. This capacitor would be driving 0.5 milliampere current, right? 0.5 from upward, 1 milliampere is going down. That means 0.5 would be coming from this side. Say yes or no. So what is happening at VC? VC will be charging in this direction from down to up. That means eventually VC potential is going low. Are you getting this point or not? This was 7.3, this was 0.7. So 0.5 milliampere here, 1 milliampere current is here, right? So that means capacitor is driving fixed 0.5 milliampere current. The current is fixed because this node is fixed, this node is also fixed. After t equals to t1, the input will change. The input will change, but we are not seeing that condition. We are only seeing at t equals to 0 plus. So at t equals to 0 plus, 0.5 milliampere, 1 milliampere, capacitor is having 0.5 milliampere current. So that is a fixed current. So now capacitor voltage will increase, but from the downward direction it will increase. So eventually VC is going down. So what is the equation of VC? VC would be, initially it was having 5 volt. It was having 5 volt in this direction. Initially it was having 5 volt in this direction. So what will be the VCT equation? Initial voltage was 5 volt. Then it was going down by a constant current. If the voltage goes down by the constant current, what is the voltage equation? IT by C. So what is I here? That is 0.5 milli into time t by C. Capacitance voltage is 10 nano. Right. So this is how VCT potential is going down. VCT potential is going down. From 5 to some potential it is going down. We don't know what is that potential, but it will always keep on going down until t equals to t1, which is equals to t1 only. So until t equals to t1, it will go down. From 5 to some particular potential, it will go down. Right? This is your VCT. Now let's make the BJTs. So let's do it on the next page. So upper one was your Q2. This was your P, this was your N, this was your P. This node was at how much potential? 8 volt, right? This node was at 8 volt. This node was at 7.3 volt. And this node was at how much potential? P potential. This is the potential equals to VC. This node is at VC only, right? So this is VC. What about this one? This was N, P, N. So P was at 3.7 and this was at 3 volt and this was at VC. Right? Now what is happening? VC is going down. VC is going down. VC is going down. If VC goes down, then what is the scene? This is already forward biased because P is at higher potential and is at lower potential. So your emitter junction is forward biased. Emitter junction is forward biased. You have no issue with that. Here also, this is forward bias. Forward bias. Your emitter junction is forward biased. What about the collector junction? Let's see the collector junction. This is the collector junction here. So for active region, collector junction has to be reverse biased. For active region, collector junction has to be reverse biased. This is the condition, right? We know this condition. For active region, collector junction has to be reverse biased. If VC was 5 volt, initially VC was 5 volt. So P was at 5 volt and N was at 7.3 volt. That means it was at reverse bias only. P was at 5 volt and N was at 7.3. That means N was having more potential. So it was reverse bias. Initially it was reverse bias. So initially it was working in active region. Right? So that we don't need to write. Initially it was reverse bias. What about this one? Initially VC was at 5 volt. VC was at 5 volt. If VC was at 5 volt, that means N was having more potential than P. So this was also reverse bias. So initially this was also in active region. So no doubt about it. Till this point, everything is crystal clear. Now what is happening? This particular VC is going down now. VC is going down. If VC goes down, then what will happen? N potential will go down. From 5 to it will go down to, let's just say 4. So still it is reverse bias. Let's just say from 5 to it goes down to 3.6. From 5 to it has went down to 3.6. Then what will happen? P will be having more potential, N will be having lesser potential. That means now the collector junction has become forward biased. And this is what you don't want. So if VC is going down, then who is having the problem? Q1 is having the problem. If VC is going down, that means Q1 is moving towards saturation. If VC goes down, then Q1 moves towards saturation because N potential is going down. If N potential is going down, that means forward bias is getting increased. If forward bias is getting increased, that means you are moving towards saturation. So if VC goes down, who has the problem? The problem is with Q1. That means Q1 moves towards saturation. If like here I am writing VC going down. VC going down. So if VC is going down, then Q1 moves towards saturation. What about this one? If VC is going down, that means potential at P is going down. Potential at P is going down. From 5 to it will be 4. So reverse bias is increased, no? N is at 7.3, P is at 4. So reverse bias is increasing only. If P is going down, reverse bias is increasing only. So here reverse bias is increasing. Here reverse bias is increasing. So Q2 has no problem. Q2 has no problem. That means Q2 stays in active only. Q2 stays in active. This is the thing for 0 to T1, for 0 to T1. For the time 0 to T1, this is the thing. If VC is going down, Q1 is having the problem. If VC goes down, Q1 is having the problem. If VC goes down, Q2 doesn't have any problem. So this was the analysis for 0 to T1. For 0 to till this time T1, till this time it will keep on going down. After that the input will change. After that input will change. So for 0 to T1, what will be this potential? Can you write down this potential? T1 is equals to T1 only. So VC at T equals to T1. That would be 5 minus, this is 10 to the power minus 8. This will go upward. 5 into 10 to the power 4. 5 into 10 to the power 4 T1. So this potential is 5 this is this potential, that's it. Okay. Now at T equals to T1 plus, what will happen? At T equals to T1 plus. At T equals to T1 plus. What is the input at T equals to T1 plus? Input is 0 volt now. Because this was our input. At T equals to T1 plus, input is 0 volt. Input is 0 volt. And what is your VC? VC here. This VC is somewhat this potential. This is your VC. 5 minus 5 into 10 to the power 4 into T1. This is your VC, that is 5 minus 5 into 10 to the power 4 T1. At T equals to T1 plus, and input is 0. If this is 0, what is the drop here? 0.7 volt. So what this potential will be? Minus 0.7 volt. So what will be the current? Current will be in upward direction. 0 minus 0.7 volt. Current will be in upward direction. Is that possible? No. Q1 will be off. Q1 is off. What did I do? The input is 0 volt. So 0 minus 0.7. So current will be in upward direction. So Q1 will be off. Let's get back to the question. Here what did I write? Never enter into saturation region. So cutoff is acceptable for us. Cutoff is acceptable. That Q1 is never entering into saturation. So cutoff, it is going into cutoff. Then it is acceptable. But if I had written this thing, that transistor never leave the active region, then this condition will not be acceptable, no? So question here becomes irrelevant. Because if input is 0 volt, then certainly it will go into cutoff. But here they are asking that transistor should never leave the active region. It has to leave. There is no other way. It has to leave. Okay, so that was the error in this question, that generally no one noticed this thing, but this should have been noticed, right? So Q1 is off now. If Q1 is off, 7.3 is fixed here, and this potential was 0.7. So this potential would become 8 volt. So this was driving 0.5 milliampere current. In downward direction, what is the current? 0 ampere. Why is it so? Because this was minus 0.7 volt, it would be driving current in the upward direction, which is not possible. So from here 0.5 milliampere current is coming. And this was your capacitor, which was having some initial voltage. Now this 0.5 milliampere current is charging this particular capacitor. And this node is VC. So what is happening with VC node now? VC node is going up. Because whatever the charge it was having, the more current will increase the voltage, right? The current is flowing in this direction, that will increase the voltage now. This was having this much of charge, it will increase the voltage now. So what will be your VCT? Initial voltage was 5 minus 5 into 10 to the power 4 T on. Now voltage will be increased. The current is 0.5 milliampere divided by IC. IT by C. C is 10 nano. IT by C. And T minus T1 I will write because the circuit is starting from T equals to T1. So what is happening? If I draw the graph, From 5 volt 2 it was going down, then it went down till t equals to T1, then it will go up. How much it will go up, how much it will go down, it depends on the value of T1 and T0, right? How much it goes up, how much it goes down, that we don't know. It depends on the value of T1 and the time period T. Because this much time was T1 and this time we are calling T2. This time we are calling T2. And if this much of time I am calling T1 and this much of time I am calling TO. So what will be my T2? T2 will be simply T2 will be simply T1 plus TO. T2 will be T1 plus TO. So what will be your VC? Okay, that doesn't even matter. What will be your VC at this node? That doesn't matter. Okay, even at the potential here, that doesn't matter. Now, what do you understand? From 0 to T1, VC is going down, and from T1 to T2 or T1 to T2, VC is going up. Now, if VC goes up, let's see who has the problem. So let's make the transistors now. Okay, so let's make the Q2 transistor first. This is your Q2 transistor. This node was at 8 volt. Note this is not Q2. And Q2 arrow is here because that is PNP. This was at 7.3 volt and this was at VC. Okay, it was PNP. If VC was going up, if VC goes up, then the positive potential across P is increasing. The positive potential across P is increasing. What does that mean? The forward bias is getting increased. Are you getting this point or not? Let's just say initially P was at 4 volt. So it was at reverse bias only. Now let's just say P becomes 7.4 volt. If P becomes 7.4 volt, then what is happening? If P becomes 7.4 volt, then P is having more potential than N. If it would become forward biased. I need it to be reverse biased to make it in active region. But if VC is increasing, then we are moving towards saturation, right? So if VC increases, then Q2 moves towards saturation. I am not making Q1 because Q1 is in cutoff. For this cycle, Q1 is in cutoff. So I am not making Q1 because that will stay in cutoff only. So let's not talk about Q1. So here what is the issue? The issue is Q2 moves towards saturation, right? So what was your complete characteristics? Not the characteristics. What was your VC waveform? The VC waveform was, it started from 5, then it kept going down, then after some particular time it went up. How much it went down, how much it went up, we don't know. This time was T on, then it went up to till this particular time. This window was known as T on and this window I can call T off. Okay, this time we showed by T1, this time we showed by T2. So eventually T1 is equals to T is equals to T1 plus TO. In this cycle, if VC was going down, who had the problem? Q1. Q1 moves to saturation. And if VC is going up, who has the problem? Q2 moves to saturation, right? Let's just say in this one, capacitor is discharging. Here the capacitor is discharging. And here the capacitor is charging. So let's take the first condition. What is that particular condition? That condition is, let's just say if your discharging is more than charging, discharging is more than charging. If your discharging is more, then what will happen? Your discharging is more. This is your VCT. In every cycle, it discharges more but charges less. This is what I am saying. In every cycle, it discharges more but charges less. then discharges more, and charges less. So after every cycle, what is happening? VC is eventually going down. VC is eventually going down. Here, VC is eventually going down, and if VC eventually goes down, that means Q1 will go into saturation. Are you getting this point or not? I have assumed that if my discharging was more than charging, so it was losing more but gaining lesser. So eventually VC is going down. Slowly after cycle by cycle, VC is going down. Because in the question it is written that we have to analyze for arbitrarily long time. For infinite cycle we have to analyze, not for only one cycle. For infinite cycle, that Q1 and Q2 should never go into saturation. Both of the transistors should never go into saturation. So it is going down, gain lesser, goes more down, gain lesser, goes more down, gain lesser. So eventually VC is going down. So here what did you understand? That Q1 goes into saturation, not moves towards saturation. Q1 goes into saturation. So this is not the desirable condition. Let's take the second one, that if charging is more, then what will happen? If charging is more than discharging, charging is more, then Q2 will move towards saturation, right? Q2 will go into saturation, because if charging is more, then how will your waveform go? The discharges less but charges more, discharges less but charges more, discharges less but charges more. So VC is going up. In this way your VC is going up, and if VC goes up, that means Q2 goes into saturation. Let's take the final condition. If charging and discharging are equal, if your charging and discharging is equal, is equals to discharging. If charging and discharging equal, then what will happen? This is your VCT versus time t. It discharges, let's just say it discharges by 2 volt. It started from 5, it discharges by 2 volt, that means it has reached to 3 volt. Now it charges by the same amount. It gains 2 volt again, so it will again go to 5 volt. Then again it discharges by the same amount, again it goes to 5 volt. From 5 to again 3, from 3 to again 5. So after every cycle, what is happening? After every cycle, what happens is that this particular potential will remain same, and this also will remain same, right? Whatever that he has lost, whatever the capacitor has lost, it is gaining the same potential. Are you getting this point? Whatever the capacitor has lost, it will gain the same potential, right? Then what does that mean? If it is losing same and gaining same, that means VC after every cycle, VC will remain at that potential only. VC is neither going up, neither going down. So this is the desirable condition. Here Q1 and Q2 both remains in linear. Both doesn't go into saturation. I should write both doesn't go into saturation, because both are not remaining in linear. Not linear, I should say active. So both are not remaining in active. One of them is going into cutoff, because here it is going into cutoff. So that was the error in this particular question as well. The transistor never leave the active region. No. Transistor should never enter into saturation. Okay. So here I should write both never enters into saturation. So what was the speed of charging for this capacitor? Speed of charging, it was charging with 0.5 milliampere current. It was charging with 0.5 milliampere current in t of time. In this time, in t of time, it was charging with 0.5 milliampere current. So what was the charge it was gaining? 0.5 milli into t of divided by c. And how it was discharging? It was discharging with 0.5 milliampere current as well. It was discharging with 0.5 milliampere current in the time window of t on. So 0.5 into t on by c. 0.5 milli into t on divided by C. So from here, what did you get to know? Your T on is equals to T off. So if T on is equals to T off, then complete T was given. T was given as 1 micro. So what would be your T on? T on would be 1 by 2 microsecond. So this would be the answer of this particular question. Okay. Now we will do one interesting thing, that is very interesting thing. Now what I want to do is that I don't want to change the theory of this question. I want to keep the theory of the question as it is. The transistor never leave the active region. So what changes I should do? What changes I should do in the circuit? In the circuit, what changes I should do? I don't want to change the theory. So what changes I should do in the circuit? Instead of this ground, I should apply some potential Vx, and that potential should be, when it is T on, this potential, let's just say this Vx is minus 1.4 volt. This Vx is minus 1.4 volt. Better I should make it with red pen. So I am making one Vx potential as well. What is this Vx potential? For time window T on, it is minus 1.4, and for time window T off, it is 0. Are you getting this point? For this window of T on, it is minus 1.4 volt. For time T off, it is 0 volt. Then minus 1.4, 0. So what will happen in this one? What will happen? When Vin is equals to 3.7 volt, when Vin is equals to 3.7 volt, at that time what will happen? The capacitor will discharge with 0.5 milliampere current, right? 0.5 milliampere current. And when Vin is equals to 0 volt, when Vin is equals to 0 volt, when this potential is 0 volt, so what will happen at that time? If this potential is at 0 volt, wait a second. Okay, sorry. This waveform I made it wrong. Sorry. Initially it should be 0, then it should be minus 1.4. 0 and minus 1.4. 0 and minus 1.4. So 0, this is 0, and then minus 1.4. 0 and minus 1.4. Initially it should be 0 volt, and after that it should be minus 1.4 volt. This is your T on, this is your T off. For 0 to T on, it should be 0 volt. 0 to T on, this Vx potential I am talking about. So if it is 0 volt, then 3.7 minus 0.7, that means here it will be 3 volt. It will drive 1 ampere current, and capacitor will discharge with 0.5 milliampere current only, right? And when Vin is equals to 0 volt, when Vin is 0 volt, at that time what will happen? At that time, when Vin is equals to 0 volt, this time window will be 1.4 volt. Okay. This window is T off. This window is T on actually. After T on, when Vin is equals to 0 volt, at that time, this input would become minus 1.4 volt. So here you are having minus 0.7 potential, and here you are having minus 1.4 volt. So this current would be 0.7 by 3 milliampere, right? So what would be happening in the capacitor? From upward direction, 1 milliampere current, not 1 milliampere. Yeah, from upward direction, 0.5 milliampere current is coming. And in the downward direction, you are having 0.7 by 3 milliampere current. So rest of the current would be going in the capacitor. Rest of the current would be going in the capacitor in this direction. Right? In the capacitor, the current would be going in this direction. That current would have been 0.5 minus 0.7 by 3 milliampere. So the capacitor would have been getting charged with this current and getting discharged with 0.5 milliampere. So for never leaving the active region, here it is not going into cutoff. It is in active region only. Here it is not going into cutoff. So for never leaving the active region, the speed of charging and discharging should be same. So 0.5 milliampere. This was happening for T on time. This circuit was there for T on time, right? for T on time. 0.5 milliampere into T on by C, that would be equals to 0.5 minus 0.7 by 3. So it would be in 0.8 by 3. 0.8 milliampere by 3 into T of by C. Right, so from here what do you get? 1.5 by 0.8 into T1 is equals to T off, and the total time window is 1 micro. So what you will get? T1 plus 15 by 8 into T1 is equals to 1 micro. So answer would have been, T1 would have been 8 by 23 micro. What is the answer of 8 by 23? By 23, that is 0.35, approximately 0.35, not 0.35, you can write 0.347. so T should be 0.347 microsecond. So this would become a more interesting problem if they had framed it correctly, but there was one error, that was a common error, that they should have changed the language. If they don't want to change the language, then they can change the circuit. In the circuit they have to make the change that instead of that ground they have to give a square wave input from 0 to minus 1.4. when T on time it should be 0, at that time transistor will be turning on, and for T off time it should be at minus 1.4 volts, so that the current flows there. If the current is flowing, then the transistor is in active region only, and we have to maintain that particular region. For that, what we are going to do? For that, we have to check that the speed of charging and discharging should be similar. This was the speed of discharging, and that was the speed of charging. Okay, discharging and charging speed is equal. So from there we get to know that T on timing. So this question would have become more interesting, right? And this was the given question. For the given question, answer would have been this one only. So in the examination, if this particular circuitry is given and the same kind of circuitry is coming, and they have written transistor never leave the active region. If it comes in gate, it will be MTA. But if it is coming in some written test of IITs, then you should be thinking never leave the active region. That means even if it is going in cutoff, it's fine. Even if it is going in cutoff, it's fine. You shouldn't go into saturation region. Okay, well and good, understood everything. So I hope you liked the lecture. Okay, then let's meet you in the next lecture. Thank you. Hi everyone. So in this video we are going to study current mirror circuits, but using BJTs this time. We have already studied current mirror circuit using MOS. Now we are going to study it using BJTs. Okay, so why do we use current mirror? For mirroring the current. We have a golden current source that we get from BGR circuit. We have a golden current source that I have to mirror in different transistor. So for that we use the current mirror circuit. So all these things we already know, right? So now we will just see the concept how it is mirroring the current. Okay, so this particular circuitry is given. Along with that, it will be written, what will be written, that both Q1 and Q2 are matched. Both Q1 and Q2 are matched. Other thing, both Q1 and Q2 are in active region. Are in active region. So this is very important. Both are in active region, and this is also important that both are matched. What do you mean by matching? Matching means actually two things, that is IS1 is equals to IS2 is equals to IS. This is the thing. Sometimes it can be meaning that beta 1 is equals to beta 2 is equals to beta. If different values of beta are mentioned, then you can take different values of beta. If it is not mentioned, then you need to consider that both the beta values are same. Nothing else. Matching means VB1 equals to VB2. No, it doesn't mean that VB1 is equals to VB2. It can be equal, it cannot be equal as well. So if they are saying that transistors are matched, does that mean that your VB value will be same? No, it can be same as well, it can be different as well. So this you need to take care. Okay. So here we know two things, that both are matched and both are in active region. This is also important thing, because in the when we studied most current mirror, what was the condition there? That both should be in saturation region. Here the condition is both should be in active region. If I write down this current IC1, because our target is to find this I out, which is actually equals to IC2, the collector current in this one. If I write down the equation of IC1, what will be that equation? IC1 would be equals to IS1 exponential VBE. This is the VBE. Now this same VBE, this is VB1, this is VB2, right? So can you see here, VB1 is equals to VB2 is equals to VB. In this particular circuitry, both are having the same VB potential. It cannot happen that both can have the different VB potential. Can you make both of them having the different VB potential? Nah, we cannot make. Why is it so? Because if let's just say if this is 0, and let's just say we take it to be 2 volt. So what is the VB? What is VB1 here? 2 volt only. And what is VB2? It is also 2 volt. So both are having the same VB potential. So VB1 is equals to VB2 is equals to VBE. So both are having same VBE potential. If I connect a resistor here, let's just say I connect a resistance R here. So you know the drop here. What will be your VB1? That will be 2 volt. But do you know VB2 now? Nah. You don't know VB2, because this will not be VB2. VB2 will be this. VB2 will be this. Base to emitter potential. Base to emitter potential. You don't know the drop across this resistance. If you don't know the drop across this resistance, you cannot tell what will be your VB2. Are you getting this point? Here, if I connect a resistance, then VB1 and VB2 will be different, because you don't know what is the drop across this resistance. Here VB1 is 2 volt, but here what is VB2? You don't know that. So that is not the condition here. Here this is the condition that both are same. Why it is same, you must have understood, right? So IC1 is equals to IS1 exponential VB1 by eta VT. You can write. Also, what we are considering? We are taking VA to be infinity. Okay, if VA is infinity, then this term 1 plus VC by VA, that is not coming. That is infinity, that is gone. So we are considering VA to be infinity. In the MOS amplifier as well, we consider lambda to be 0, right? In MOS amplifier, we consider lambda to be 0, so that 1 plus lambda VDS term doesn't come in action. So here also that term is not coming into action. So this is your IC1. What about your IC2? What will be your IC2? That would be IC2 is equals to I out, that is equals to IS2 exponential VB2 by eta VT. What do you know here? Here IS1 is equals to IS2 and VB1 is equals to VB2. So these currents are same and these are same. Then the expression are similar only, no? Complete expression is similar now. IC1 is simply equals to IC2. IS1 is equals to IS2 and VB1 is equals to VB2. If you divide both of the equation, what you will get? IC1 is equals to IC2. IC1 is equals to IC2 is equals to I out. So what did you understand? If your both of the transistors are having the same VB potential and they are matched, what do you mean by matched? That means both are having the same reverse saturation current. Then these collector currents will be copied. If both are having the same reverse saturation current and both are having the same VB potential, then this collector current will be the same. So I out is equals to IC1. But you need to write down I out in terms of IREF, because this is the current you know. You don't know IC1 value. You don't know IC1 value, but you know the IREF value. You know IREF value. This is some known current. So you need to write down your I out in terms of IREF. So what will be your IREF? What do you think? What is this current? IB1, right? And what is this current? IB2. In case of MOSFET, IREF would be equals to IC1 only, because there was zero gate current, right? But in case of BJTs, there is some base current. So if there is some base current, then certainly it cannot be, IREF cannot be equals to IC1. So there will be some values, right? What will be this current now? This side is driving IB1 current, this side is driving IB2 current. So what will be this current? IB1 plus IB2. Say yes or no. So what is your IREF is equals to? IREF, this is equation 1. I ref is equals to IC1 plus I ref is equals to IC1 plus IB1 plus IB2 plus IB1 plus IB2. Understood? This is equation 2. What will be your IB1? IB1 will simply be IC1 by beta 1. And what will be your IB2? IB2 will simply be IC2 divided by beta 2, right? IB1 will be IC1 by beta 1, IB2 will be IC2 by beta 2. What do you know? Here we know IC1 is equals to IC2. This is what we proved here. IC1 is equals to IC2. IC1 is equals to IC2. And in the question it is given that both are having the same beta value. Both are having the same beta value. Beta 1 is equals to beta 2 is equals to beta. Both are having the same IC value and both are having the same beta value. So here what did you understand? If IC is same and beta is same, that means IB1 is equals to IB2 is equals to IB. Did you understand this point? Both are having the same collector current and both are having the same beta value. That means both are having the same base current. So what you can write? I ref is equals to IC1 plus 2 IB1. Or you can write IC1 plus 2 IC1 by beta is equals to I ref. And IC1 is equals to I out only. So I ref is equals to 1 plus 2 by beta into I out. So what will be your I out by I ref? I out by I ref would be beta upon beta plus 2, or simply what is your I out? I out is beta upon beta plus 2 times of I ref. There you go. This is the final answer. What is your I out? I out is beta upon beta plus 2 into I ref. Well and good. So this was the complete analysis of our current mirror circuit. In the examination you will do it very quickly, although you can remember this expression as well, this final expression, because this is a very standard circuit. We are not going to solve standard circuit now. This is the standard circuit. What is the standard circuit? What are the conditions? First condition, VA is equals to infinity. Both are matched. That means both are having the same IS current. Both are having the same beta value and both are in active region. Here you got to know that both are having the same VB value. Both are having the same IS value. That means collector current will be same. If collector current is same and beta is same, that means collector and beta both are same. That means base current will also be same. So this is your IB, this is your IB2. That means from here 2 IB current would be coming. And this is your IC current, which will be copied at the output. Well and good. So I ref will be equals to IC plus 2 IB. I ref will be equals to IC plus 2 IB. So like quickly, if you need to analyze in the examination, if you need to do it quickly, how will you do it? So just as a conclusion, we can write down all the things. Beta same, IS same, both active, VA infinity. So beta is same, IS is same. What does that mean? And beta is same, IS is same. Also, here we got to know that both are having the same VBA also. Both are having the same VBA also. So beta, IS and VBE same. What does that mean? IC, IB same. IC, IB same. So if this you are calling I out, if this current you are calling I out, then this current will also be I out only, right? And here what will be the current coming? 2 IB. Here the current would be coming, that is 2 IB. 2 into IB. What is IB? IB is I out by beta. So simply your I ref is equals to, in one step only we can write down I out plus 2 I out by beta. So what will be your I out? I out will simply be beta upon beta plus 2 into I ref. That's it. This is your I out. This is the way to remember the things. This is a very standard circuit. If the exactly the same circuit is coming, then you can write down your answer very quickly. Well and good. Let's see some different kind of questions now. Now we will solve a lot of question. Now all the concept will be clear to you. Here both of the transistors are having different beta values, 10 and 20. And both are having that different cross section area. I don't remember if I told you this thing, that your reverse saturation current is proportional to the reverse saturation, is proportional to the cross section area. Okay, you need to remember this thing. Your reverse saturation current is proportional to the cross section area. So AQ2 divided by AQ1 is given. What does that mean? IS2 divided by IS1 is given. That is equals to 2. And beta 1 is 10 or 20? 10. And beta 2 is 20. So you just need to analyze the circuit now. Like no expression, you don't know anything. You just know the concept. What is the concept you know? This is your VB potential. This is your VB potential. Both are having the same VB potential. Both are having the same VB potential. Can you write down this current IC1? Yeah, you can write down. So what will be your IC1? IC1 would be equals to IS1 exponential VB by eta VT, right? Because VB is the same for both of them. What will be your IC2, which is equals to I out only? This is your I out and it is equals to IC2 only. What will be your IC2? IC2 will be IS2 exponential VB by eta VT, right? If you divide IC2 by, if you divide equation 1 by 2, 1 by 2, what you are doing? 2 divided by 1. So IC2 by IC1 would be 2. That means your IC2 would be equals to 2 IC1. So both are, like all this derivation you don't need to do in the examination. In the examination you will just see that both are having the same VB potential. The ratio of the reverse saturation current is twice. That means IC2 will be twice of the IC1. That's it. Are you getting this point? Both are having the same VB potential and both are having the ratio of 2 in the reverse saturation current. So one which is having high reverse saturation current, that will have the high collector current. So if this is IC, this will be 2 IC. That's it. Well and good. What will be the current here? IB2. And what will be the current here? IB1. So what will be the current here? IB2 plus IB1. Say yes or no. This current is IB2, this current is IB1. So what will be the current upward? IB2 plus IB1. So IREF is equals to, what will be your IREF equals to? IC1 plus, always your target is to write down the final current in terms of IREF. That's it. IC2 is equals to 2 IC1, or you can write, what is your IC2? IC2 is equals to I out only. IC2 is equals to I out. IC2 is equals to I out. So I out is equals to 2 IC1, right? So here I can write IREF is equals to IC1 plus IB2 plus IB1. IC1 plus IB2 plus IB1. IC1 plus, what will be IB2? IB2 will be IC2 divided by beta 2. IC2 divided by beta 2. And what will be IB1? IB1 will be IC1 divided by beta 1. Say yes or no. IB2 will be IC2 divided by beta 2. IB1 will be IC1 divided by beta 1. This is equals to IREF, right? Now your IC2 is equals to I out, but IC1 is equals to I out by 2. So IREF. What can be replaced? IC1 can be replaced with I out by 2. IC1 can be replaced with I out by 2. I out by 2. In the examination, we will do it very quickly. Here I need to explain you. That's why I need to write all the steps. And IC2 is equals to I out only. I out by beta 2. Plus IC1 is equals to I out by 2 beta 1. I out by 2 beta 1. I out by 2 beta 1. Well and good. So everything is there. What we need to find? We need to find I out by IREF. I out by IREF. This is your IREF divided by I out by 2 plus I out by beta 2. What is beta 2? Beta 2 is 10 or 20. Beta 2 is 20 divided by 20 plus I out 2 into beta 1. Beta 1 was 10. So divided by 20. So IREF would be equals to 1 plus 2 plus 1 by 10. 6 by 10. Is that correct? 2 by 20. So 1 by 2 plus 1 by 10, 6 by 10, yeah, 6 by 10 into I out. What will be your I out by I ref? I out by I ref would be 10 by 6. What that would be? 6 1 are 6, 1.67. So the ratio is 1.67. So this was the question. You could have solved it very quickly as well, because you would get to know that this current would be double, so this current would be half of that. So I out by 2 you could have written, then you could have written the base current here, then you could have written the base current here, and then simply I ref is equals to those values, right? You could have solved it very quickly. What I would have done in the examination, because I would know that both are having the ratio of 2, that means this would be I out by 2. So I know from upward direction I ref is coming. Here my current would be I out by 2. In this direction, what would be the current? Base current of this one, that would be I out by 2 by beta 1 plus base current of this one, that would be I out by beta 2. That's it. The question is complete. I ref is equals to addition of these currents. Directly I would have reached to this step, final this step. Are you getting this point? In the examination, we are not going to do these steps. Once we have the practice, we will get to know both the currents, what will be the relation between the both currents, what will be the relation between the base currents. Then finally, I need to equate it with I ref. Okay. So this was the second question. Let's solve more questions, because we just need to solve problems here, nothing else. Now this is the question. All the transistors are matched, all are having the same beta value. Okay. All are having the same beta value. You need to find the values of I out 1, I out 2 and I out n in terms of I ref. Okay. Do you remember this connection? We made this connection in MOSFET. What do you mean by this connection? Do you remember this connection in MOSFET? That means gate of all these are connected all together. Gate of all these are connected all together. Right? Gate of all these are connected. So here what are connected? Base are connected. Here base are connected. Are you getting this point? So let's copy this circuit so that you guys get more comfortable. So the actual scene is, what is the actual scene? If I remove these connections, is Q2, Q3 and Qn. N transistors are there here, right? If I remove these connections, what does that mean? That this is connected like this, from here to here. Another connection is, since this is the nth transistor, so I have to make a dotted line as well. Well and good. So if this is driving your, let's just say, IB2 current, what this will be driving? IB3 current. IB3 current. Here some IB4 current will also be there. This will be driving some IBN current. All currents will be same, because all are having the same VB potential. All are having the same VB potential. This is your VB, this is your VB. Look, emitter is grounded. This is the base. This is the base. Base is going here. This is the base. Base is going here. So all are having the same VB potential. All are having the same VB potential. All have the same IS current. IS is same. IS equals to same. VB is equals to same. And beta is equals to same. What does that mean? That means that IS, IC and IC and IB, IC and IB both will be same. Say yes or no, right? So this I out 1, I out 2, I out n all will be same. And if I call this current as IC1, so what do you understand? That your IC1 is equals to I out 1 is equals to I out 2 is equals to I out 3 till the point I out n. I out n. So all the currents are same. Well and good. So here I wrote IB2, IB3. Instead of that, I can write IB1, IB2 and IB3. Sorry. Instead of that, I can write IB. All will be IB. All will be IB. All will be IB. Right? What this current will be? Instead of this IC1, I can write IC only. And all these current will be equals to IC. Are you getting this point? All are symmetric. Everything is symmetric. VB is the same, beta is same, IS is same. So all the currents are same only, no? Tell me how much. This was your IB current. Tell me how much current will be this? Can anyone tell? What will be the value of this current in terms of IB? Look, here there is IB current. Here there is again IB current. Here also, like, so what will be this current? How many transistors are these? How many transistors are these? This is some third transistor. This is some nth transistor, right? This is some third transistor. This is some nth transistor. From 1 to n, how many transistors are there? If you count from 1 to n, n transistors are there. If you count from 2 to n, that means n minus 1 transistors are there. If you count from 3 to n, that means n minus 2 transistors are there. What do I mean? 1 to n. That means I have 1, 2, 3 transistors. So how many transistors I have? 1, 2, 3, 3 transistors. So if I count from 1 to n, I have n transistors. If I am counting from 2 to n, I have n minus 1 transistor. If I am counting from 3 to n, that means I am having n minus 1 transistor here. Say yes or no. So IB, 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 all will be added n minus 1 times. So this will be n minus 1 into IB. Say yes or no. This current was your IB only. IB, IB, IB was driven. All the transistors were taking IB, IB, IB base current. Now the number of transistors here was n minus 1. So how much current will be here? IB plus IB plus IB plus IB n minus 1 times. That means this current would be n minus 1 IB. And this current is IB. So how much this current will be? Wait, sorry. These are not n minus 1. These are n minus 2 transistors. I am really sorry. These are n minus 2 transistors. These are n minus 2 transistors. Because we are counting from 3 to n. 3 to n, there will be n minus 2 transistors. So this current will be n minus 2. This current would be n minus 2. N minus 2 IB plus IB. What this current would be? N minus 1 IB. This current is n minus 1 IB. And this current is IB. So how much this current will be? N IB. Say yes or no. Did you understand this point or not? Did you understand this whole point? First you got to know that all the base currents are same. Then we need to write how much base current you are getting from here. So there are total n minus 1 transistor. Here these are total n minus 1 transistor. These total are n minus 1 transistor. So all are driving IB current. So how much will be the total current coming here? N minus 1 into IB. Understood? All these are n minus 1 transistor. From 2 to n minus 1 transistor are there. All are driving IB current. So this will be the total current n minus 1 into IB. N minus 1 into IB. And here IB current is there. So this current would be NIB. That's it. So what is your IREF equals to? What is your IREF equals to? From here your IREF is equals to IC plus NIB. Right? IC plus NIB. IC plus NIB. IC plus, what will be IB? IB will be IC by beta. And what is your IC equals to? IC is equals to I out. Right? IC is equals to I out. Because all are equals to I out. Is equals to IC is equals to I out. All the currents will be same. Right? Is equals to I out and I out by beta. Equals to IREF. What will be your I out equals to? I out will be equals to IREF into beta upon beta plus n. That's it. This is the answer. I out is equals to IREF into beta upon beta plus n. This is the answer. Right? Understood this point? So when we studied this configuration only, there what was the value of n? 2. The value of n was 2 only. When we studied this configuration, in the previous question we studied this configuration, not in the previous question, in this concept we studied this configuration where the value of n was 2. So what was the answer? Beta upon beta plus 2. Similarly here, what is the answer? Beta upon beta plus n. That means n is equals to 2 only. So you can check the answer from here. And if beta is equals to infinity, and these currents are equals to I out 1 is equals to I out 2 is equals to I out n. And if beta is equals to infinity, then I out will be equals to I ref only, and that would be equals to I out 1 is equals to I out 2 is equals to I out n. That's it. Well and good. If beta is equals to infinity, without even deriving, you can check it, because if beta is infinity, all the base current will be 0. All these base currents will be 0. So this current will also be 0. If beta is infinity, these currents are 0. This current is also 0. All these currents are 0 only, right? So this current will also be 0. So IREF will be simply equals to IC. This complete IREF will be flowing like this. IREF will be simply equals to IC, and the same current will be copied everywhere, because VB value are same. VB value are same, and IS value is also same. Are you getting this point? So directly you can also understand, if beta is infinity, then base currents are 0, then IREF is simply equals to IC, and that will be copied. That's it. So everything is crystal clear. So these kind of questions are asked in the examination. So these are very famous questions. Again and again these questions are asked. So you should have the practice, right? How you will write the equation in the current mirror. In the current mirror using BJT, you should have a concept clear, rather than knowing what is the final answer. Because in the examination there is very rare chance that they will ask you a standard circuit. They will give you a different kind of circuit, and they will ask you to analyze. So for that we will solve a lot of problems. So you will be developing a very good habit of solving the current mirror circuit using BJT. So let's solve this question now. So in this question, what is given is that Q1 and Q2 are matched. Both Q1 and Q2 transistors are matched. No information given about Q3. Q3 is not matched to Q1 and Q2. Okay. All are having the same VB potential of 0.7. So this is 0.7. All are having the same VB. This is your VB. This is your VB. And this will be your VB. Right. This will also be 0.7. So this is 0.7 volt. And this is also 0.7 volt. So this is 0, this is 0.7, this will be 1.4. This will be 1.4. 0, 0.7, 0.7, this will be 1.4. So how much current is flowing here? 10 by 100, that would be 0.1 ampere. So the current here is 0.1 ampere from upward direction. 0.1 ampere current is flowing. All transistors are working in active mode. Beta 1, beta 2 values are given. VB1 is 0.7. You need to find this I out. Okay, I naught you need to find. This I naught you need to find. If this is I naught, what this value will be? I naught by beta 2. But let's just not write it. What we know, one thing we know, that your VB1, VB is same for transistor Q1 and Q2. I am writing for Q1 and Q2. For Q1 and Q2. What is the same? VB is same. Okay. Transistors are matched, that means IS is same. Okay. And beta is also same. Beta is also same. So what does that mean? That means that IC, IB will be same. That means IC1 is equals to IC2 is equals to IC, and IB1 is equals to IB2 is equals to IB. So IC, IB will be same. This is your IC. So this will be I naught by beta. Say yes or no. I naught by beta, where beta is beta 1 is equals to beta 2 is equals to beta is equals to 100. This is your I naught. So what this will be? This will be I naught by beta. And what this will be? This will also be I naught by beta. So what will be the current here? This will be 2 I naught by beta. This is I naught, this is I naught by beta, this is I naught by beta. So the upward current would be 2 I naught by beta. Okay. What this current will be? IC currents are same, so this current will be I naught only. Now what will be this current? Let's just call this current as I1. So what will be the value of I1? Can you tell? For this Q3 transistor, look at this Q3 transistor. You need to find the value of I1. If you know the value of I1, everything will be crystal clear. The question will be solved. So what will be I1? I1 will be, this is the collector current. This is the collector current of Q3. Collector current of Q3. So collector current divided by beta plus 1. What is that? That is equals to base current. I1 is the base current. I1 is the base current of Q3. That would be equals to collector current of Q3 divided by beta 3 plus 1. What is the collector current of Q3? Collector current of Q3 is 2 I naught by beta into beta 3 plus 1. That's it. This is equation number 1. Right? So what is your 0.1 milliampere? Sorry, 0.1 ampere. 0.1 ampere is equals to what? 0.1 ampere is equals to I naught plus I1. I naught plus I1. And what is your I naught? You need to write I1 in terms of I naught, and that we have done. That is 2 I naught upon beta 3 plus 1. What is beta 3? Beta 3 is 99. Beta 3 is 99 and beta is 100. So what that would be? 0.1 is equals to I naught into 1 plus 2 by beta is 100, beta 3 is 99, so it would also be 100. And from here you can get to know the I naught value. Right? You can solve it on your own. Let's see what we get. So this would be 1000, okay, divided by 1002. So this is coming out to be, this was 100 milliampere, so this is 99.98 milliampere. This is 99.98 milliampere. So actually there is a very good matching, right? The matching is very good. Here, let's just say I had a reference current of 0.1 mil. I had a reference current of 0.1 ampere, and I had to match it. I had to match it here. If I used only these two transistors, then what would be the answer? Answer would have been beta upon beta plus 2 into 0.1. So that would come out to be 0.1 into, that would come out to be 98 milliampere. It would be somewhat 98 milliampere. So there was an error of 2 milliampere. What is the error here? Here the error is 0.02 milliampere. So I used this configuration. When I used this configuration, I got a very good matching of current. That is 99.98 milliampere. That means there is 0.02 milliampere error only. But here there would have been 2 milliampere error if I had used only this configuration, the standard one. If I had used this one, I would have got the error of 2 milliampere. But I smartly connected one more transistor which is not even matched. This is not matched with these two. This is not matched. Even if it is not matched, still you are getting a very good here. Still you are getting a very good, like very less error, right? So this configuration is known as buffered current mirror, but that is of no use. This configuration is known as buffered current mirror. But no one will ask you what is the name of this particular configuration, but they can ask you the questions, right? They can give this circuitry and they can ask you anything. They can ask you I out value, they can ask you this resistance value, or they can ask you the reference current value. So this is how you need to solve. Everything is given. You just need to write down. You just need to know what is your final target. You just need to know what do you know. You know that there is 0.1 ampere current is coming. You know the current in the downward Q1. You just need to write the current here. That's it. So this was your I out. If this was I out, this was I out. This was I out by beta. This would have been I out by beta. So this would have been 2 I naught by beta. If this is 2 I naught by beta, then this current would have been 2 I naught by beta upon beta 3 plus 1. So 0.1 ampere is equals to 2 I naught by beta upon beta 3 plus 1 plus I naught. That's it. From there, I could get the value of I naught, that is 99.98 milliampere. Well and good. Let's solve the next question. Okay, this is actually a very good question. You need to solve it on your own. So all the transistors are working in active mode of operation. Cross-section area of the transistor is shown by AQ. So if this is having 1x area, then this is having 2x area. And all these areas are same. AQ3 is equals to AQ2. Okay. This is also 2x. And this is also 2x, because AQ3 is equals to AQ2 is equals to AQ4. So this is also 2x. This is what is given. This is given in the question. You need to find I out by I ref. Did you understand what did I do? AQ2 is 2 times of AQ1. So if I am considering this 1x, this would be 2x, this would be 2x, and this would also be 2x. Well and good. And all transistors are working in active mode of operation. Cross section area is shown. Beta values are same for everyone. For everyone, beta value is same. Tell me one thing, if this is I out, what this will be? I out by beta. Why this direction? Because this is I, the base current direction will be this. Base current will be this direction. This would be I out by beta. I out by beta. Now tell me one thing, both are having the same cross section area. Both are having the same VEB potential as well. Both are having the same VEB potential as well. For Q3 and Q4. For Q3 and Q4. Cross section area is same. Cross section area is same. What does that mean? That your IS3 is equals to IS4. Right? Cross section area is same. Also VEB is equals to VEB4. VEB3 is equals to VEB3. This potential is also same. Right? Beta is same. All these are same. What does that mean? That your IC3 is equals to IC4 is equals to I out. That is shown. This was your I out, and your IB3 is equals to IB4, and that would be equals to I out by beta. Right? So if this is I out by beta, what this will be? This will also be I out by beta. What is the current here? This current is I out only. So what will be the current here? I out by beta here, I out by beta here. So the direction will be in this direction. In this direction, you will be having 2 I out by beta. So what will be the current coming here? That current would have been 2 I out by beta plus I out. So this current, let's just call this current as I1. So I1 is equals to, what is your I1? I1 is equals to, combined I can call it equation 1. So I1 is equals to I out plus 2 I out by beta. Because my target is to write all the current in terms of known currents. In terms of known current or the current that I need to find. I need to find I out current, so everything I will write in terms of I out only. This is the target. This is equation number 2. This current is I1. Well and good. Now, both are having the same VB potential. VB potential. Both are having the same VB potential. Both are having same VB potential. Both are having the same beta value as well. But the IS current is doubled. Say yes or no. The IS current is doubled. This was driving I1 current. So how much current this will drive? Can you tell me? If this is having IC2 is equals to IC1, sorry, IC2 is equals to I1, then what will be the value of IC1? Can you tell me? Directly, without even writing any equation. Because cross section area is doubled. This current is doubled. Then this current will be half, I1 by 2. If you don't understand, what is your I1? What is your I1? I1 would be I1, this I am calling I1. So it is some I1 is equals to IC2. I1 is equals to IC2, and that is equals to IS2 exponential VB by VT. And what will be your IC1? IC1 would be equals to IS1 exponential VB by VT. What is given? AQ2 divided by AQ1 is equals to 2. AQ2 divided by AQ1 is equals to 2. Or you can say IS2 by IS1. Because cross section area is equals to the reverse saturation current. So IC2 by IC2 would be equals to IC2 by IC1 would be equals to 2. So I1 is doubled of 2 IC1 because IC2 is equals to I1 only. IC2 is equals to I1 only. So IC2 is doubled. So what is your IC1? IC1 is I1 by 2. But in the examination, you are not going to do all these things. In the examination, you will just see, okay, the area is doubled, so this current must have been doubled. So this current would be half. That's it. And if this current is half, what will be this whole? What will be this current? This current would be I1 by 2 beta. Right? And what is this current? This current is I1 by beta. So what will be this current? This would be 3 by 2 I1 by beta. So what will be your IREF? IREF would be I1 plus 3 by 2 I1 by beta. And what is your I1? I1 is equals to, we will write down I1 later on, but let's find the value of I1 first. This is your I1. So IREF is equals to this much. IREF is equals to this much. Beta value is given. Beta value is given as 100. IREF 1 plus 3 by 2 beta into I1. What is the value of I1 from this equation? From equation 2, that is equals to I out plus 2 I out by beta. 2 I out by beta. This is the value of your I1 from equation 2, right? So your IREF is equals to 2 beta plus 3 upon 2 beta into beta plus 2 divided by beta into I out. Beta value I can put because I need to find I out by IREF. I out by IREF I need to find. Value of beta is 100. So 200 by 3 into 200 into 202 divided by 200. Sorry, beta value is 100. No, so 200 by 3 into 200. Beta value is 100. So it would be 102 divided by 100. This is your IREF into I out. So what will be your I out by IREF? I out by IREF. That I can solve in the calculator. So 200 into 100 divided by 203 divided by 102, 0.965. 0.965. That's it. So this is the final answer. In these kind of questions, huge amount of calculations are used. So you should check back your calculations. So if this was I1, this was I1 by 2. So this would have been I1 by 2 beta. This would have been I1 by beta. So 1 plus 1 by 2, 3 by 2, I1 by beta. 3 by 2, I1 by beta. So IREF is equals to, from here you can see IREF is equals to I1 plus 3 by 2, I1 by beta. So 1 plus 3 by 2 into I1. What is your I1? For I1, you can get to know that these currents will be the same. I out. This current would have been I out by beta. This would have been I out by beta. This would have been 2 I out by beta. So I out plus 2 I out by beta. So 1 plus 2 beta, 1 plus 2 by beta into I out. So beta value is 100. So 203 divided by 200, 102, 100. I out by IREF is this much. So this is the final answer. This is correct. Okay, well and good. So these kind of questions can be asked in the examination. These are not tough. Okay, if you consider it tough, this is certainly not tough. Tough was MOSFET. In the MOSFET, anything can be asked. In this one, you just need to write VB potential, VEB potential. Just simple thing you need to write, and just you need to equate. So intelligent thing is there. This is just an aptitude. I out by beta, I out by beta, 2 I out by beta, 2 I out. This current is coming here. Then what will be this current? What will be this current? Then simply the final answer. That's it. Nothing else. So these kind of questions can certainly be asked in the examination. Well and good. Let's move towards next question. Yeah, so small error here. I was thinking only there is something wrong. This is I1 by 2. This would IREF is equals to I1 by 2 plus 3 by 2 I1 by beta. So I forgot to put 1 by 2 here. So this would change now. Let's say 2 beta into beta plus 3, right? 2 beta will be common. So beta will come here. Beta plus 3 into beta plus 2. Yeah, so beta plus 3, this will be 103. This will be 103. Now this answer will change. So 200 into 100 divided by 103 divided by 102. That would be 1.90. 1.90. 1.90. So this is the correct answer. Actually, how did I get to know this is wrong? Because let's just consider if beta is infinity. Then what will happen? This IREF, the area here, the cross section area is doubled. So this will be 2 IREF. And then simply this current will be copied. So I out is approximately, if I take the approximation, that would be equals to 2 IRF. So I out by RF should be nearly equals to 2. But here you are getting 0.98. At that time we were getting 0.96 or 95. So that is not the approximate one, no? What did I mean to say? If I take beta equals to infinity, I just consider this as a MOS. If this question was in the MOS, what would have been the answer? IREF area is doubled, then current is doubled here, then double current is simply copied. So I out is equals to 2 IREF. IREF doubled is copied. Doubled was flowing from this and that would have been copied. So answer would be nearly equals to 2. But when we solved it, we were getting 0.95. So that surprises me. Then I checked back, then I got to know that I forgot 1 by 2 here. But in the examination, they will expect this answer. If they are asking in, what do we say? If they are asking in case of NET, if they are asking numerical answer type, then they will give these options, this range. Okay, then they will give this range. So in this range, your answer must be there. If you write 2, that would be wrong. So you cannot write approximate answer. You have to find the exact expression in the examination. Okay. So yeah, that's it. That's it about this lecture. In the next lecture, we are going to solve this assignment 19. So there are a lot of questions which we will be solving in the next class. Okay. So you can solve it on your own. You can try solving on your own. You can try solving all these questions on your own. In the next class, we are going to discuss everything. That's it. These are the questions. In the next class, we will discuss it. Okay. Thank you. Hi everyone. So in the last lecture, we have studied about current mirror circuit. Now we are going to solve assignments. So this is the first question, which is not based on current mirror circuit. It is a simple BJT biasing question, and there is a Zener diode connected. So you need to find the value of beta and the VC potential. These two things you need to find. So see one thing in this question. In this question, this Zener is given. So Zener can have three possibility. Either it can be forward biased, or reverse biased, or it can be in breakdown, right? Now this Zener is driving some current from N to P. It is driving some current from N to P. Is that possible? No. Is this possible? No. This is the possible thing. Say yes or no. Here you can see that the current is driven from N to P. If that is possible, that is the only case possible when the Zener is working in breakdown region, right? So it is certainly in breakdown region. So if it is working in breakdown region, what will happen? It will be replaced by a battery of 6 volt in this direction. So what this node will be? This node will be 6 volt only. If this node is 6 volt, 10 minus 4, this is 10 minus 6. 10 minus 6 divided by 4. So how much current will be here? 1 milliampere. So here you will have 1 milliampere current. Now this is 1 milliampere, this is 0.5 milliampere. That means 0.5 milliampere current would have been flowing here. Right? Now this is 6 volt. I can show 0.5 milliampere later on. This is 6 volt. How much is this potential? 0.7. VB is 0.7. So what will be your IE current? Can you write down your IE current? So your IE current would be 6 minus 0.7, 5.3 divided by 530. So how much it would be? 10 milliampere, right? It would be 10 milliampere. This current is 10 milliampere. And how much was IB current? 1 milliampere current coming from upward, 0.5 is going downward. That means here 0.5 milliampere current would have been there. So IB is 0.5 milliampere. So can you find the value of beta? Yes, we can find the value of beta. That would be 0.10 milliampere would be equals to 10 milliampere would be equals to beta plus 1 into IB, right? So beta would have been 90. So beta value is 90. So this is the value of beta, and you need to find the VCE potential. Now if you see VCE potential, what do you see? There is a huge gap, right? There is huge gap between the options. So you can take IC equals to IE. Approximately you can take IC equals to IE. So what is this potential? This potential is 5.3. 6 minus 4, this potential is 5.3 volt. How much current is flowing? This is some 10 milliampere. So you can take this current can also be nearly 10 milliampere. So how much voltage drop it will give? 2 volt. So what will be this potential? This potential will be 8 volt. So what will be your VCE? Now 10 milliampere, same 10 milliampere current is flowing from upward direction. So this drop will be 2 volts. So VCE potential would be 10 minus 2, VC would be 8 and E is at 5.3. So 8 minus 5.3, it would be 2.7, right? 2.7 volt. Nearly around 2.8 volt. So that would be the answer. So 2.8 and 19. 2.8 and 19. This would be the correct answer. Let's move towards the next question now. In this question, three transistors in the circuits below are identical. VB value is given, beta is 100. You need to find VC potential. Again, VC potential is having huge gap, right? In the options, you can see there is huge gap. That's why I picked the option here. Otherwise, I would have only picked this much of question. But you see the options, there are huge gap there, right? If there is huge gap, you can take beta equals to infinity. So what we are going to do? All are having the same VB potential, no? All are having the same VB potential. All have the same VB potential. You can check. If this is 0, this will be V. 0, V. All are having the same VB potential. So what can you say? That the IC current can be mirrored. The current IC can be mirrored. And now we are taking base current to be equals to 0. Options are far. Options far. Take beta equals to infinity. If you are taking beta equals to infinity, then what will happen? This is 0.7 volt, right? This is 0.7 volt. So this node will also be 0.7. So how much this current would be? 1.3 milliampere. Now base is driving 0 ampere current. Base is driving 0 ampere current. All are driving 0 ampere current. So this 1.3 milliampere would have been flowing from here. Right? Now this 1.3 milliampere. If you are having VB equals to 0.7, your BJT will drive 1.3 milliampere current. This is the scene. If you are having VB equals to 0.7 volt, your BJT will drive 1.3 milliampere current. So again, here also you are having 0.7 milliampere current, 0.7 volt. That means it will also drive 1.3 milliampere and it will also drive 1.3 milliampere. Are you getting this point or not? First thing is that we are considering all of them to be in active region. Then only the current will be copied, right? If all of them are in active region, then the current would be copied. All are having the same VB potential. VB equals to 0.7, VB equals to 0.7, VB equals to 0.7. We know one of the BJT is driving 1.3 milliampere current. So rest two BJT would also be driving 1.3 milliampere current, no? 1.3, 1.3. So how much current is flowing from here? 2.6 milliampere. So what will be your VC? VC would simply be 10 volt minus 2.6 into 1 kilo. 2.6 milli into 1 kilo. That would be 7.4 volt. But this should not be the final answer. You need to check, because what did you do? You considered both of them to be in active region. Here base and collector are shorted. So this is in active region, no doubt about it. But let's check about these two transistors. We do not know about these two transistors. So what is the scene in those transistors? In those transistors, this is at 0. This was at 0.7 and this came out to be 7.4. So you can see this is forward biased because this is PN and this is also N. This is forward bias and this is reverse bias. So this is in active region. So the assumption that you made that both are in active region, that is correct. So always you need to check. Your current mirror concept is only applicable, that current IC equals to IS to the power VB by VT. That is only applicable if and only if your transistor are working in active region. Then only the current will be copied. They are not, if they were not active, if they were not acting, if they were not biased in active region, then what would have happened? You need to solve something different, that we will see in the upcoming questions. But here they are working in active region, so the current can be copied. Well and good. Let's move towards the next question. This one. Both transistors are working in active region, that is given. Beta is 10, so you need to find I out volt. You need to find I out current. So how will you solve? This node is at -5. This node is at -5. This is -5. What this would be? -4.3. Say yes or no. Right? If this is -5 plus 0.7, that would be -4.3. So how much current would be here? 0 minus 4.3, that would be 4.3 milliampere. Right? This is a very standard circuit. From upward direction, 4.3 milliampere current is coming. So what will be your I out? I out is simply beta upon beta plus 2 into the reference current, that is 4.3. If you don't remember, you can derive it as well. IB. So this would be 2 IB. And this current is simply equals to I out only, because both of them are having the same VP. So from here also you can derive it. or you can directly remember it beta upon beta plus 2 into the reference current. So what answer you would get? That would be your final answer. 10 by 12 into 4.3. 10 by 12 into 4.3. 3.58. 3.58 milliampere. Very straightforward question. Next question, you should do it on your own. Try doing it on your own. It is a similar kind of question, nothing different. What this node will be? Minus 4.3, right? Similar, minus 4.3 volt. But the diode is having cut-in voltage of 0.7. Apply open circuit test. If you apply open circuit test, what P will have? P will have 0 voltage and N will have minus 4.3. That means diode will turn on. If diode turns on, then how much voltage drop it will give you? It will give you a voltage drop of 0.7 in this direction, right? So minus 4.3 plus 0.7. What will be this potential? Minus 4.3 plus 0.7. What this potential will be? Minus 3.7, right? So this potential will be minus 3.7 volt. Did you get this point or not? Minus 5 plus 0.7 minus 4.3. If you turn on this diode, this will be replaced with the battery of 0.7. So minus 4.3 plus 0.7. What that would be? Minus 3.7. So what will be the current? 0 minus 3.7 divided by 1 kilo ohm. That would be 3.7 milliampere current. So from the upward direction, 3.7 milliampere current is coming. Since beta is infinity, the current will be copied. So what will be your I out? I out will be 3.7 milliampere. Since beta is infinity, so the current is copied. Well and good. Did you understand this point or not? What did we do? We just need to check if the diode is on or off. So you can apply open circuit test as well. You can apply short circuit test as well. If you apply short circuit test, what will happen? You will replace the diode with a battery of 0.7. Then you will see the direction of current. What was the direction of current? From P to N only. That means diode was on. If diode was on, then that node would go to minus 3.7. So 0 minus of minus 3.7. That means 3.7 milliampere current is flowing in the diode from P to N. That's it. And that same current will be copied since beta is infinity. So the same current will be copied. Well and good. Let's move towards the next question. So for the circuit shown in the figure, transistor has beta equals to this much, VB equals to this much, voltage across the Zener diode is 15. This is 15. Voltage across the Zener is 15. You need to find the current through Zener. You need to find current through Zener. Okay. So if they are asking the current through Zener, again Zener has three options. It can be forward biased, it can be reverse biased, or it can go into breakdown. Now we have to take an intelligent guess whether it will be in breakdown, reverse bias or forward bias. Take an intelligent guess. If I apply open circuit test here, then what will be the potential across Zener? That will be 30 minus, if I am applying open circuit test, then this will be the base current, right? Base current will be flowing through the 330 ohm resistance. If I apply open circuit test, then there will be no current here. That means the base current will be flowing through this 330 ohm resistance only. So what will be the drop here? That drop will be 30 minus 330 ohm into IB, right? Now IB can be in some microamperes or some 0.1 milliamperes, whatever it is. Let's just say IB is 0.1 milliampere. 0.1 milliampere. Okay. So what will be the voltage drop across Zener? That would be 30 minus 0.33 into some 0.1. Or even take IB is 1 milliampere. Let's just take IB is 1 milliampere. Or even you can take 10 milliampere. Even IB is 10 milliampere. 0.33 I have written because I am taking it 10 to the power 3. 0.33. 0.33 into 10 to the power 3. If your IB is 10 milliampere, let's just say it is 10 milliampere, which is not that much typically high. We have solved a lot of problems there. We did not see that IB would be that much of high. But we are assuming a value. Let's just say if it is 10 milliampere, still what will be the voltage drop? 30 minus 3.3. It will be nearly around 26.7. So here you will be having 26.7, and that is enough to make this diode go into breakdown. So what we did, we tried to take an intelligent guess whether it will be in breakdown or not. So we got to know that if I apply open circuit test, the voltage across the Zener is coming out to be 30 minus 330 into IB. IB will be some milliamperes. So the drop across the Zener would be very high. It would be certainly greater than 15 volt. So the guess is it should go into breakdown. This is the guess. Then we will solve the problem and then we can check if it is going into breakdown or it is in reverse bias or it is in forward bias. So our first guess is it should go into breakdown. Okay, so this was the intelligent guess that we took. So our guess is Jenner probably will go into breakdown. This is the assumption, or you can say guess, assuming. So if it goes into breakdown, then what will happen? This has a Jenner voltage of 15 volts, so this will be replaced with the battery of 15 volt. At N you will have positive, and at P you will have negative. This is how you will replace it. That will be a battery of 15 volt. So this node will be 15 volt. Now you cannot say that this current will be the same, that IB current will be the same as this current. No, no, no. Because the Jenner has been replaced with the battery now. That can also drive some current. The battery can also drive some current. Okay. So Jenner has been replaced with the battery. So Jenner can also drive some current. Well and good. So 30 minus 15, 15 by 330. So how much current will be here? 15 by 330. 15 by 330 into 1000. So 45.45. This current would be, because this node is 15, this node is 30. So it is driving 45.45. 45.45 milliampere current. So this current is 45.45 milliampere current. What is your target? You need to find the current through Jenner. So this current you need to find. If you know the base current, then your target will be completed, right? If you have the base current, you know the current from coming from this direction. You need to find the current going into Jenner. If you know the base current, then your target will be completed. So my target is to find base current. How I can find that? This node is 15. What this node will be? This node is 15. 15. What is this drop? From P to N, in the direction of arrow, from P to N, this drop is 0.7. So what this voltage will be? 15 minus 0.7, this voltage will be 14.3. Right? This voltage will be 14.3. 15 minus 0.7, 14.3 divided by 100. So this will drive 143 milliampere current. 143 milliampere current. Now, whatever the current that is going into this resistance, the same current will be here as well, right? Because this is an open end. This is an open end. So same current will be flowing like this. So this current would be 143 milliampere. So what did you get to know? Your IE current is 143 milliampere. So what will be your IB current? Your base current would be, what is the beta value? Beta value is 40. So 143 divided by 41. 143 divided by 41. That would be 3.48. 3.48 milliampere. So your base current is in upward direction, 3.48 milliampere. 3.48 milliampere. So 45.45 is coming here. 3.48 is going upward. So what will be your Jenner current? Your Jenner current would simply be 45.45 is coming from upward. 3.48 is the base current. Subtraction would be the Jenner current, and that would be minus 45.45. That would be 41.96. 41.96 milliampere. Well and good. So this was the answer. Now we assumed that it was in breakdown region. So that assumption was correct, because the current is flowing from N to P, and that is only possible when it is in breakdown region. The current that we saw, that is flowing from N to P, and it is possible only in breakdown region. If the current was flowing from P to N, then our assumption would have been wrong. Then we needed to solve the problem right from the beginning. That we will consider that Jenner to be in forward bias. Then we would have solved the problem. So these kind of question also we will see in the upcoming in this lecture only, in the upcoming questions. So let's move towards the next question now. This is the question. This is also a very interesting question. So you need to find the V1 minus V2 potential. These things are given, and here very interesting thing is written that VC sat is 0.1 volt. VC sat for this transistor is 0.1 volt. V1 value is high enough to put that transistor T3 in saturation. So T3 is in saturation. If T3 is in saturation, then this much potential is 0.1 volt. So what will be this potential? 9 minus 0.1, that would be 8.9 volt. Right? Now let's check other things. This this much is 0.7. T1, T2 are identical transistor. T1 is in active region, that everyone knows. T1 is working in active mode of operation. We don't know about T2. So for T2 we will find it out. So if this is 0.7, this node will also be 0.7. 9 minus 0.7, 8, this node is 9. So 9 minus 0.7 divided by 5. So 8.3 divided by 5. So 1.66. So this current is 1.66 milliampere. 1.66 milliampere. This current is 1.66 milliampere. Now this 1.66 milliampere current, if I consider T2 be in, to be in, so active region. So what I am going to consider, assuming T2 in active. So if T2 is in active, then current will be copied. This current will be copied. So this current would be 1.66 milliampere. This current is copied, that is 1.66 milliampere. So what will be the drop here in this direction? 1.66 milliampere into 3. So that drop will be 4.98. This drop will be 4.98 volt. 4.98 volt. Now this node was 8.9. This drop is 4.98. So what will be the V2 potential? V2 potential will be minus 8.9. So V2 potential will be 3.92 volt. V2 potential will be 3.92 volt. If this is 3.92 volt, tell me one thing. What about the BJT that we consider to be in active region? This was 0, this was 0.7, and this is coming out to be 3.92. That means it is certainly working in active region, right? You can check. This will be reverse bias, this will be forward bias. So it is certainly working in active region. So our assumption is correct. Assumption is correct. So V2 is 3.92 volt. What about V1? If this was 8.9, this would have been 0.7, because irrespective of the region of operation, VB will always be 0.7 only. So this was 8.9. What will be V1? So V1 will simply be 8.9 minus plus, this is 8.9 plus 0.7. So that would be 9.6 volt. So V1 will be 9.6 volt. So what did they ask? They asked V1 minus V2. V1 minus V2. So that would be 9.6 minus 3.92. So 5.68. This is the final answer. 5.68 volt. This is the answer. So this is how you needed to solve this problem. Well and good. Did you understand this point? Okay. Now let's copy this circuit. I will change the question now. I will change the question. So what I will do is that I can change this resistance value. How much should I put? What was the current flowing here? 1.66. If I do 1.66 into 6, 9.96. Okay. So now I'm going to change it to 6 kilo ohm. This resistance is 6 kilo ohm now. This resistance is 6 kilo ohm. Okay. And VCE given hai. This is given. VCE set for T2 is also 0.1 volt. Okay. VCE set for T2 is also 0.1 volt. Then again you need to find V1 minus V2. So this is given. This thing is given here. VCE set for T2 is given. Now this is the question. So what will happen? What would be the answer? Try doing it on your own, then you can recheck your answer. Okay. So this was 9. This would be 0.7. There is no doubt about it. This is 0.7. So what was the current flowing here? That was 1.66 milliampere. So no doubt about it. 1.66 milliampere. And in the question it is said that it is enough to drive it to saturation region. So this would be 0.1 volt. So this node would certainly be 8.9 volt. There is no doubt about it. Okay. Now if I consider T2 be in T2 be in active. If I consider, this is what I consider, T2 to be in active. T2 active. This is the assumption. Then what will happen? Both are having the same VB. If it is working in active as well, then this current will be copied. This current will be copied here. So this current would be 1.66 milliampere, that is copied. So what will be your V2 potential? V2 potential would be 8.9 minus 1.66 into 6. What that would be? 1.66 into 6 minus 8.9. So that would be minus 1.06. It is coming out to be minus 1.06. So was your assumption correct? No, your assumption was not correct. Why it was not correct? Because this node was at 0.7. This node was at 0.7. This was grounded, and this node was at minus 1.06. So this is becoming forward biased, and this was also forward biased. So it is going into saturation. So it is actually going into saturation. So if it is actually going into saturation, then what will be the potential? This potential will be 0.1. So what will be the V2 potential? That would be 0.1 volt. If it is going into saturation, V2 potential will be 0.1 volt. So what would be the answer? V2 will be 0.1 volt. And what will be V1? V1 doesn't have any effect. 8.9 plus 0.7. 8.9 plus 0.7. That would be 9.6 volt. So what will be your, what they asked? V1 minus V2. So V1 minus V2 would be 9.6 minus 0.1. That would be 9.5 volt. So that would have been the final answer, 9.5 volt. Okay. So always you need to check the region of operation. If you are solving the BJT current mirror or you are solving the MOSFET current mirror, always check the region of operation. In case of MOSFET, you need to bias it into saturation region. In case of BJT, you need to bias it into active region. Well and good. Let's move towards the next question. The next question is based on the same concept only. Beta is given this or that. VC set is also given, that is 0.7. We need to find I out. Well and good. So for I out, this would be 0.7, that is given. So 11.3 divided by 10K. So 1.13 milliampere current is flowing here, because this node will also be 0.7. So 11.3 divided by 10K. So 1.13 milliampere current is flowing. Now, what will be your I out? Depending on RC value. So we will do it one by one. A, if RC equals to 10 kilo, if RC is equals to 10 kilo. So again, we are always considering Q2 being active. If Q2 is in active, then what will be your I out? I out will simply be beta upon beta plus 2. Beta upon beta plus 2. 100 by 102 into 1.13. 100 by 102 into 1.13. So 100 by 102 into 1.13. 1.107 something we are getting. So 1.1 milliampere we can say. This is your I out, right? So let's find this node. Let's just call this node as VC, because we assumed it to be active. Assumption. It was assumption. It was the assumption, right? But let's find out the actual potential of VC now. So what will be your VC? VC would be 50 minus 1.1 milli into 10K. So 50 minus 11 into 50, it is very obvious. I don't know why I am doing this calculation. Yeah, 50 minus 11, that is very obvious. 50 minus 11. कितना होता है भाई 50 minus 11? 39 volt. Okay, so yeah, 50 minus 11 is 39 volt. So you can see your BJT. If you see your BJT, this is grounded, this is 0.7 volt, and this is 39 volt. Certainly it is in active region. So assumption was correct, and this was the correct answer. Let's see the next question. You need to take RC equals to 50 kilo. If you take RC equals to 50 kilo and again you assume Q2 to be inactive. If you assume Q2 to be inactive, then you know what will be your I out. I out will simply be beta upon beta plus 2 into 1.13. That would come out to be 1.1 milliampere only. 1.1 milliampere only. This would be your I out. But is that correct? Let's check that out. If RC is 50, then what will be your VC? VC will be 50 minus 1.1 into 50. because this is 50 kilo ohm. Basically 50 minus 1.1 into the 50 kilo ohm resistance, 1.1 into 50 kilo ohm resistance, so that would be minus 5 volt. So your VC will be minus 5 volt. This was your BJT. One end is grounded, this is having 0.7, and now this has become minus 5 volt. So this is forward biased here, and which is not required, right? Not required. So it is going into saturation. If it is going into saturation, then this is wrong, right? So what will be the current? Because VC set is given 0.7 volt, so this node will be 0.7 volt only. VC set is given 0.7 volt, so VC will come to 0.7. Basically the scene is, I can copy this circuit. The scene is that here 1.13 milliampere current is there. This was 50 kilo ohm. This was 50 kilo ohm. Now we go to know that it is going into saturation. If it is going into saturation, then this node will become 0.7 volt, because VC set is given 0.7 volt. So if this node is 0.7, 50 minus 0.7, so what will be this current? I out. That would be 50 minus 0.7, 49.3. 49.3 divided by 50k. 49.3 divided by 50k. Some 0.98 milliampere. The current is some 0.98 milliampere, not your 1.1 milliampere. Okay, so this is the correct answer. Well and good. So this is how you always need to check if your device is, if your BJT is working in active region or not. If it is working in saturation region, then you cannot apply the concept of current mirror. Well and good. Let's move towards the next question. So this is a very standard circuit. Okay, very standard question. It is a very standard question. I am writing very standard and very important. If something is coming in your examination from current mirror, I guess this would be coming. Here they are not giving VB same. Okay, the potential VBE is not same here. Why it is not same here? For this VB is this one, VBE1. For this is the VBE, no? If R2 was 0, if R2 was grounded, then you could have said that both VBE are same. But not here, both VBE are not same. Are you getting this point? Here both VBE are not same. So this is VBE1, so this would be VBE2. What did they ask? They asked the value of R2 such that your I2 is 100 microampere. Okay, I1 is 1 milliampere, I2 is 100 microampere. This is what they are taking, and VCC is 6 volt, thermal voltage is that is given. Okay, so beta value is high. The current again is very high. Beta is given infinity. Beta is given infinity. So one thing you know, IC equals to IE. IC equals to IE. This is given, no doubt about it. IC equals to IE. So what do you see here? IE equals to 1 milliampere. This is I1. This particular current is I1. This particular current is I1. So this is the way to solve always. So it's not that I'm asking you to remember the method, but this is a very standard circuit, so you should be able to solve it in the examination very quickly. Otherwise, you can use your brain as well and you can solve. So what is written? Both are Q1 and Q2 are perfectly matched. Q1 and Q2 are perfectly matched. What do you understand by that? Both are having same what? Reverse saturation current. I told you. What do you mean by perfectly matched? The same reverse saturation current. That's it. It doesn't comment on the VB potential. It doesn't comment on anything else. If they are saying perfectly matched, what does that mean? Both are having the same reverse saturation current. That's it. So what will be your I1? I1 will be reverse saturation current Ix exponential VB1 by VT, right? VB1 by VT or eta VT you can say. Eta value they have given. If eta value they have not given, you can take eta value equals to 1. Okay. If they haven't mentioned eta value, you can take it to be 1. So I am taking it to be 1. What will be your I2? I2 will also be some reverse saturation current exponential VB2 divided by VT. Right? This is equation 1 and this is equation 2. Why I am writing this equation? Because what I can do is that I can apply KVL in this loop, in the lower loop. Can you apply KVL in the lower loop? This node is grounded, this node is 0. 0 plus VB1 minus VB2 divided by R2 is equals to I2. Do you agree to this point? What I am saying is that 0 plus VB1 minus VB2. I am working from here to here, minus VB2 divided by R2 is equals to I2, current coming from upward. Say yes or no. 0 plus VB1 minus VB2 divided by R2 is equals to I2. So VB1 minus VB2. Basically, you need to find the R2 value, no? You need to find R2 value. So what will be your answer? VB1 minus VB2 divided by VB1 minus VB2 divided by I2 is equals to R2. That's it. I2 value you know? Yeah, I2 value I know. What is the value of I2? 100 microampere. VB minus V2, I need to find VB minus VB2. This is my target. So what I will do? I will divide equation 1 by 2. What I will do? I will divide equation 1 by 2. If I divide the equations, what I will get? I1 by I2 is equals to I1 by I2 would be equals to, if I am saying this is exponential VB by VT, so what I can write? E to the power VB1 by VT divided by e to the power VB2 by VT. So I1 by I2, this is I2. I2 is 100 micro or 0.1. So I1 by I2 would be 10. I1 by I2 would be 10. 10 would be equals to exponential VBE1 minus VBE2 divided by VT. So VBE1 minus VBE2 would be what? VBE1 minus VBE2 would be, what is the value of VT? VT is 26 millivolt. So ln would come here. So 26 millivolt into ln 10. So 10 ln into 0.026. So it is some 59.8 millivolt. VB1 minus VB2. This is the potential of VB1 minus VB2. This we have got from equation 3. From equation 3. What will be your R2? 59.8 millivolt divided by I2. What is the I2 current? That is 0.1 milliampere. So what will be your R2 value? That would be 598 ohm approximately, or you can write 598.67. 598.67 ohm. Well, this was 59.867. So R2 would be 598.67 ohm. 598.67 ohm. This is the value of R2. Very easy question. So this is a very standard question. Okay. From one relation you will find by the exponential equation, other relation you will find by writing KVL in the loop. That's it. Tell me one thing. If instead of this ground here minus 5 volt was there, then what would be the KVL? Instead of this ground minus 5 was there. This equation would change or not? Pause the video and tell your answer. This equation would change or not if instead of ground there was minus 5 volt? No, it will not change. Why? Start writing KVL. Minus 5 plus VB1 minus VB2. And what is the node potential here? Minus 5 only, no? So minus of minus 5 divided by R2 is equals to I2. So this would be cancelled. So VB1 minus VB2 divided by R2 is equals to I2. Or you can say you are applying the equation in the loop. This minus 5 will not even come in action. You just apply the equation in the loop. VB1 minus VB2 divided by R2 is equals to I2. Or you can say VB1 minus VB2 minus I2 R2 is equals to 0. You just walked around the loop. So many people sometimes get the confusion that, sir, if here minus 5 is there, then something different will be there. Nah, nothing different will be there. You just need to walk around the loop. That's it. Well and good. So yeah, this was the one thing that I wanted to tell. And let's see the next question. I'm really hopeful that in the gate examination these kind of questions are coming, like about to come in the next year. If they want to frame a easy question which people generally ignore, because people generally ignore these kind of questions, so they can ask these kind of question in the upcoming examination. Well and good, let's move towards this question. Very easy question, you can solve it on your own. What you need to find, you need to find the V naught potential. Okay, so negative feedback is there, certainly negative feedback is there, so this 1 volt will be copied here, this 1 volt will be copied here. VB is given 0.7 volt, this is 0.7 volt. 1, this is 1.7. This was 1, this was 1 volt, this was 0.7, so this would have been 1.7, 1.7 volt. So how much current would be coming from here? 5 minus 1.7, that would be 3.3. 5 minus 1.7, that would be 3.3 divided by 33. 3.3 divided by 33, that would be 0.1 milliampere, right? The base current would be 0.1 milliampere. Can I apply IE equals to, because I need to find this current, IE current. Now the same current will be flowing through this one, right? Because input of op-amp will not drive any current. So what will be your V naught? V naught will simply be 1 minus 100 into IE. Say yes or no? Because here you are having IE current. So what will be the drop here? 100 IE. So 1 minus 100 IE, that will be your V naught. Are you getting this point or not? If you know the IE current, that same current would be flowing through the 100 ohm resistance, and your V naught would be 1 volt minus 100 IE. That's it. Op-amp you have already studied. So can you find IE current? You have the IB current. IB current is 0.1 milliampere. So can I apply this formula? IE equals to beta plus 1 IB. Yes, you can apply this formula only if it is working in active region. Only if this transistor is working in active region. Is it working in active region? This node was 1.7. 1.7 and 5 reverse biased. This is what? Reverse biased. So certainly it is working in active region. If it is working in active region, you can certainly apply this equation. You can certainly apply this equation. So beta is 99. So 100 IB. So 100 into 0.1, that would be 10 milliampere. The current is 10 milliampere. So 1 volt minus 100 into 10 milli. So 1 minus 1, 0 volt. So V naught is 0 volt. C is the correct answer. Well and good. So it was a very simple question. 0.7, 1.7, 3.3 divided by 33, 0.1 milliampere into 100. That would be 10 milliampere. 10 milliampere current would be flowing through the 100 ohm resistance. So 1 volt is here, and 100 into 10 milli, that would be 1 volt. So V naught will be 0 volt. Now a lot of times people don't check whether it is working in active region or not, but I always recommend to check if it is working in active region or not. Then only you can apply these equations. So always whenever you are solving a BJT biasing question or current mirror question, always you need to check the region of operation. Always keep it in mind. Okay, well and good. Let's move towards the next question. You have to find the value of V naught, and also you need to find the power dissipated in the BJT circuit. Power dissipated in BJT. So what is power dissipated in BJT that you need to remember? Power dissipated in BJT. If in the question sometimes they are asking power dissipated in BJT. So what you need to do, you need to multiply VCE into IC. So your target would be to find VCE into IC. Very important formula. Power dissipated in BJT would be VCE into IC. This is what you need to find. VCE into IC. Well and good. Okay then. Now, is this a negative feedback? We need to check if this op-amp is working in negative feedback or not. We need to check. So if this node goes high, then what will happen to this node? It is, you can consider it as an NMOS only. Consider it as an NMOS. This is NMOS only, no? So if gate is going high, what will happen to source? From gate to source, if this node goes high, this node goes low, and this node goes high, right? From here to here there is 0-degree inversion. You remember it from NMOS, we have already studied. So basically, if this node goes high, then this node will also go high. If this node is going high, this is simply potential divider, so certainly this node is going high. This node is going high, it is negative, so certainly this node is going low. So there is a negative feedback. So very easily we can check, because we have studied op-amp in a very in-depth manner, right? What did I do? Again, I can check. I increase my output. If my output goes high, this node goes high. If this node goes high, this will also go high. If this goes high, this is negative, so this will go low. So if I increase my output is eventually going low. That means there is a negative feedback. So if there is a negative feedback, this can be copied here. This would be 6 volts. So what do you think? What will be your V0? What do you think? What will be your V0? For V0, what you can see? You can apply simply potential divider. Why you can apply simply potential divider? Because current is same. In 8 kilo ohm and in 2 kilo ohm, the current will be same. What is the value of current? You don't know. Or you can, you know as well. This will be 3 milliampere. This will be 3 milliampere. But it will be same because this will drive 0 ampere current. This will drive 0 ampere current. So you can simply apply potential divider. So what will be your 6 volt will be equals to 6 volt would be equals to what? 2 V0 divided by 10, right? 2 into V0 divided by 10 is equals to 6 volt. So V0 is equals to 30. Your answer is V0 is equals to 30. So if V0 is equals to 30, then what will be your VCE? So answer of this particular question is 30. That is correct. But what is your VCE now? VCE is capacitor voltage is not capacitor voltage. Collector voltage is 40. Emitter voltage is 30. This voltage, emitter voltage is coming out to be 30. This voltage is coming out to be 30. Right? So that is 10 volt. This is 10 volt. But you need to find IC. So what do you think? What will be your IC? 30 by 10 is equals to 3 milliampere. That is your this current. Say yes or no. 30, this node is 30, or you can say this node is 6. 6 by 2, 3 milliampere current. 6 by 2, 3 milliampere current. The same current is flowing through this 8 kilo ohm resistance as well. This will be 3 milliampere. This is an open node. This is not a network here. This is an open node. So the same 3 milliampere current would be flowing here. And beta value I have given, that is infinity. So I is equals to IC. So this is also 3 milliampere current. Did you get to know? 6, 3 milliampere current. The same 3 milliampere current is flowing through 8 kilo ohm resistance. That means this current will also be copied here, and same current is flowing through collector as well, because IC is equals to IE because beta is infinity. So IC is 3 milliampere. If IC is 3 milliampere, then what will be the power dissipated? Power dissipated. IC into VCE, 10 into 3 milli, that would be 30 milliwatt. This is the final answer. So these two are the final answers, this one and this one. Power dissipated it is VCE into IC. Well and good. Let's move towards the next question. This one, very easy question. This 1 milliampere current is coming. What do you need to find? We need to find the IS current and you need to find the output voltage. 1 milliampere current is coming. This kind of question we have already solved in the design problem in current mirror. This 1 milliampere will be divided into these two MOS. I hope both of them are having the same area, are meshed. Okay, both of them are having the same area. So these two are meshed. So this 1 milliampere current is coming. It will see two MOSes, this MOS and this MOS, because this 1 milliampere node is connected to two MOS, right? So this will be 0.5 and this will also be 0.5 milliampere. 1 milliampere current is divided into two MOS, right? Well and good. Now these are in current mirror, so this will simply be copied here. 0.5 milliampere. 1 milliampere will not be copied. 1 milliampere we divided it into two MOS, 0.5 and then 0.5 is copied. We solved a design problem where I asked you to do that. You have a golden current source of 200 microampere and you need to load it to 100 microampere without even changing the WIL ratio. This is the same concept here. All are having the same WIL ratio. The guy was having 3 transistors. All were having the same WIL ratio. He had a golden current source of 1 milliampere. What did he do? Divided into 2 and copied. That's it. 1 milliampere divided into 2 and copied. 0.5. So IS is 0.5 milliampere. Now this current is 0.5 milliampere. Now you need to check the operating condition of diode. So you can you apply open circuit test here? If you apply open circuit test, then this will be open-ended. This will also be open-ended. And since this is an ideal diode, this cannot drive any current. This will be driving 0 ampere current, right? This will be open. This will be open. So where will this 0.5 milliampere current go? So both cannot be off. If I say D1 and D2 both are off, then that is wrong. Why it is wrong? Because where will this 0.5 milliampere current go? So that is wrong. Both cannot be off. Now if I say my D1 is on and D2 is off, if I say my D1 is on and D2 is off, is that possible? Let's check that out. If I say D1 is on and D2 is off, D1 on and D2 off. If D1 is on and D2 is off, then where will this 0.5 milliampere current go? From D1 only. And that current will flow in this direction. You are saying your D1 is on, but the current is flowing from N to P. Is that possible? No. Right? Are you getting this point or not? You are saying that your D1 is on and D2 is off. Then the current has to flow from D1 only. And the current is flowing from N to P. That is not possible. So D1 cannot be on. Now if I say D1, D2 both on, is that possible? That is also not possible. Why is it not possible? If I say D1, D2 both on, D1, D2 both are on. So if both are on, then this will be replaced with the 0.7 volt battery. Yeah, this will be replaced with the 0.7 volt battery. This is 0 volt only. This is 0 volt, no doubt about it. This will be 0.7 volt minus 0.7 volt, because this will be replaced with the battery of 0.7. So this will be minus 0.7 and this would be minus 0.7 and minus of minus 0.7. Minus 0.7 minus of 0.7. So this will be 1.4 volt. So what this will drive? This will drive 1.4 milliampere current. So 1 kilo ohm resistance will drive 1.4 milliampere current, and here there is 0.5 milliampere current. That means this diode has to drive some current in this direction. Did you understand this point or not? And that current would be 1.9 milliampere, which is not possible. What did I do here? I considered D1 and D2 both to be on. So if D1 is on and D2 is on, then what will happen? This will be replaced with the battery of 0.7. So if this node is 0, this node will be minus 0.7. This is also replaced with the battery of 0.7. This node will be minus 1.4 and this node is 0. So that means this 1 kilo ohm resistance will drive 1.4 milliampere current in this direction. And here there is 0.5 milliampere current. This current, this IS current, that is 0.5 milliampere current is here. So what amount of current would be coming from here? 1.4 upward, 0.5 downward. So what amount of current is coming? 1.9 milliampere. In this diode, 1.9 milliampere current is coming in this direction, which is not possible because you have considered both to be on. D1 cannot drive current from N to P. So there is something certainly wrong. So this is also not a possible case. So what is the final case that is possible? IS, basically this was your IS. You shouldn't be getting confused. This is your IS, that is 0.5 milliampere. This is the same IS that would be flowing here. So what is the final case possible? That is D1 is on and D2 is off. Sorry, D2 is on and D1 is off. D2 is on and D1 is off. So what will happen? This 0.5 milliampere current will flow from this, like this. 0.5 milliampere current will flow like this, and this will be open-ended. This will be open-ended. So 0.5 milliampere current will flow like this, right? So this node is 0. What will be this drop? This drop will be 0.5 volt. What will be this drop? This will be replaced with the battery of 0.7. So from 0 to 0.5 plus 0.7, what will be your V0? V0 will be 0 plus 0.5 plus 0.7. That would be 1.2 volt. So A is the correct answer. So D1 is on, D2 is off. So 0.5 milliampere current is flowing through D2, right? And your V0 potential is also coming 1.2. So here you are getting 1.2 and this node is 0. So certainly D1 is off. So that you can recheck as well. You recheck that if I consider D2 to be on, my V0 is coming to be 1.2. So for D1 at N you are having 1.2, at P you are having 0. That means D1 is certainly off. If D1 is off and D2 is on, that is the final condition. If D2 is on, that will drive 0.5 milliampere current. 1 kilo ohm will also drive 0.5 milliampere current. This particular node is grounded. This will be 0.5 volt. 0.5 plus 0.7, that would be 1.2. So correct answer is 1.2. Well and good. So this is how you can do in the examination. In the examination, you will be quickly able to think which diode will be on, which diode will be off. right? It will not take that much of time in the examination. Why it will not take that much of time? Because it is clearly seen that if it is driving 0.5 milliampere current, then D1 has to drive some current in this direction, which is not possible. So it has to be off, and D2 can take up that current from P to N. So that will be on only. So this is how you will be able to do it in the examination. Okay then. So let's move towards the next question. Okay, this one, this solution is like everywhere I have seen, every single place I have seen this question to be wrong. Okay, so let's try doing it on our own. You need to find the I naught potential, I naught current. Okay, tell me one thing, whether this diode is whether this op amp is working in negative feedback or positive feedback. Which feedback is there? So what we will do, we will increase this one. If this is increasing, then what will happen to this node? This node will go down, right? Because you can take it as a common source amplifier. If this node increases, then this node goes down, because there is 180-degree inversion, right? So if this node is increasing, that means this node is going down. If this node is going down, then this node is also going down. If this node is going down, then this node will increase only. Negative 1 is going down. Negative potential is going down. So if negative potential is going down, that means output will increase. So you increase the output and eventually your output is increasing. That means this op amp is in positive feedback. It is not even in negative feedback. It is in positive feedback. So the, like what people usually do, okay, negative sign is there, so it is a negative feedback. So this will be 2 volt. Absolutely wrong. Okay, this is in negative feedback. This is in positive feedback, not in negative feedback. Because if this increases, this will decrease. If this decreases, this will also decrease. If this decreases, this will increase. So this is in positive feedback. If this is in positive feedback, so if I call this node as V node dash, so only V node dash has 2 possible output. That would be either minus V set or plus V set. You have only 2 possible output, either minus V set or plus V set. If your output is minus V set, then your diode will, then your BJT will be off. Say yes or no. If your output is minus V set, at base you are having negative potential. At base you are having negative potential. Minus V set can be some minus 5 volt or anything like that. Now you cannot say that, sir, here also we will have some, let's just say this is 0.7 volt, okay, and V set is minus 5. So what this node will be? Minus 5.7. And then there is this Z is connected. So that will drive current in the upward direction, which is not possible in case of BJT. Are you getting this point? If your V node dash is minus V set, then this node will be some negative potential, minus 5.7 you can take. So this ZL will say that I will drive the current in the upward direction, because this is 0, this is minus 5.7. So the current will flow in the upward direction. Is that possible? No. In case of NP and BJT, the current can flow in only in downward direction. So BJT will be off. And if it is plus V set, then it can drive some current in the upward direction. Because if it is plus V set, then this will be some 4.3. So this can drive some current. So then BJT can be on. So you have 2 options, whether V naught will be plus V set or minus V set. If I say my V naught dash is plus V set, if I say if V naught dash is plus V set, if I am saying V naught dash is plus V set, then what will be your V negative potential? V negative potential cannot determine. Why you cannot determine? Because you don't know the current here. Do you know the current here? You don't know the current here. So what will be your V negative potential? You cannot determine. So you are not coming to any conclusion here. What did I do? I assumed, I got to know that this is in positive feedback, so I have 2 options. Either my output will be minus V set or plus V set. If I assume my output to be plus V set, then BJT will be on. BJT will be on. BJT will be on. Now I need to check if the assumption is correct or not. I assumed V naught dash to be plus V set, if that assumption is correct or not. So I need to check the V negative potential. I need to check the V negative potential. What will be your V negative potential? You don't even know. Let's just say I get to know my V negative potential is 3 volt. So V positive is 2 volt, V negative is at 3 volt. That means my output will go to minus V set. So my assumption was wrong. If it was 1 volt, then my output would go to plus V set. My assumption was correct. But you don't even know what is your V negative, because you don't even know the current here. You don't even know the current here. So you don't know what is your V negative. So you cannot come to any conclusion. Right? Well and good. Then I have to assume the other output. So here I am writing BJT is on, but what is my V negative? Cannot determine. If I can't determine that, I cannot come to any conclusion. No conclusion. No conclusion. Now if I take my V naught dash to be minus V set. If I take my V naught dash to be minus V set. If this is minus V set, then what will happen? BJT will be off. If BJT is off, BJT is off. This is driving 0 ampere current. BJT is also driving 0 ampere current. This will also drive 0 ampere current. If BJT is off, this 10.5 kilo ohm will also drive 0 ampere current. Then what will happen? What will be your V negative? BJT is off, and this 10.5 kilo ohm is driving 0 ampere current. So this 5 volt will simply be copied to V negative. V negative will be 5 volt. If V negative is 5 volt, V naught dash would be again minus V set only. Because at V negative we are having more potential, V positive we are having lesser potential, so your V naught dash will go to minus V set. That means assumption was correct. Here the assumption that you made, that came out to be correct. If that is correct, that means you assumed your V naught to be minus V set, that was correct. So this condition was correct. Here you did not come to any conclusion, but when you assumed V naught dash to be minus V set, then you got to know that your BJT is off. If it is off, it will drive 0 ampere current, so 5 volt will simply be copied and V naught dash would be minus V set only. If that is minus V set only, that means this I naught current is actually 0 only. So that means your final answer is I naught current is 0 ampere. So this is the correct solution of this particular question, which was a very good question asked in the GATE examination, but everyone solved it wrong. Some will applying some open circuit test, and I don't know what they were doing. So this is the exact solution. What is the solution? First we need to check whether our op-amp is working in negative feedback or not. There we got to know that it is working in positive feedback because there is already 180 degree phase shift. So there are two 180 degree phase shifts. So total phase shift is 360 degree. That means it is in positive feedback. If it is in positive feedback, then what does that mean? If it is in positive feedback, that means your output can be plus V set or minus V set. If my output is plus V set, I cannot come to any conclusion. If I assume my output to be minus V set, I get to know that my BJT is off. If that is off, that means that is driving 0 ampere current. So from 10.5 kilo ampere resistance, 0 ampere current is flowing. So V negative node will go to 5 volt and your V node dash would be minus V set. So the assumption that we made that my output can be minus V set, that is correct, and your I node will be 0 ampere. Well and good. So this was the correct solution. Let's move towards the next question. This was asked in GATE 2023, which is one of the best question as per me of BJT. Okay, one of the best question. The Zener diode in the circuit has a breakdown voltage of 5 volt. Your current gain beta of the transistor in active region is 99. Ignore base to emitter voltage drop. Okay, they have written line ignore base to emitter voltage drop. What do you understand by this line? Because people will generally see the circuit and they will say VB is equals to 0.7. They are saying ignore base to emitter voltage drop. That means they are asking you to take VB equals to 0 volt. Okay, this is what you need to take. This is what they gave in the question. So you should have been attentive in the examination. When I solved this question for the first time, I also did the same mistake. I also took VB equals to 0.7 volt. Okay, so question should be like you should read the question thoroughly. Now the current through that 20 ohm resistance in milliampere. This is what they are asking. Current through that 20 ohm resistance in milliampere. Now the question is on this genre whether it will go into breakdown or not. What do you think? Whether it will go into breakdown or not? Let's just say the current here is some 100 milliampere. I don't know. This is some 100 milliampere current. I am again applying open circuit test here. In the genre, again I am applying open circuit test. If this is some 100 milliampere current, some 100 milliampere, so what will be the voltage drop here? 2 volt. If this is some 100 milliampere with beta value of 99, right? This would be some 1 milliampere. And the same current will be flowing here as well. This would be some 1 milliampere. So this would be 25 minus 7. This would be this potential is 25 and this base current would be 1 milliampere because I am applying open circuit test. So collector current is 100 milliampere. So base current would be 1 milliampere. So here it will give a voltage drop of 7. So this node will go to 25 minus 7. This node will go to how much potential? 25 minus 7, that is 18 volt. So 18 minus 2, this is very higher than 5. So on the first glance, it seems like that it is having a it is having a reverse bias of 16 volt. So it should go into breakdown. On the first glance, it will look, and if I had been the aspirant in the examination, I would have certainly taken it to be in breakdown. Okay, because it seems like that, because I just took a rough value that if 20 ohm is driving 100 milliampere current, let's just say, then the drop across this node will be 2 volt, and if it is driving 100 milliampere current, that is the same as IE current. So what will be the base current? That will be 1 milliampere. So approximate drop here would come 15 minus 7 volt, 18 volt. So 18 here to here. It feels like that it will go into breakdown, but when I solve the problem, I get to know that it is not in breakdown region. Okay, so this was the beauty of the question, and if you consider it in breakdown and then you solve it, it will take a lot of time, and then you will realize that it is not even going into breakdown, it is in reverse bias. Okay, so shall I consider it to be in breakdown? Should I solve that, or you can do it on your own? You should be able to do it on your own. Why is it so? Because what you will do, you will consider it to be in breakdown. So this will be 5 volt. The same 5 volt will be copied here, right? If this is in breakdown, same 5 volt will be copied here. Why so? Because this node is 0 volt. So the same 5 volt is copied here. So how much current this will drive? This will drive 5 by 10. This is 0.5 ampere. This will drive 0.5 ampere, which is a very high current. Okay, 0.5 ampere is a very high current. So can you come to any conclusion here? If this is driving 0.5 ampere current, now again we cannot come to any conclusion. Then we need to find IE current and IB current, right? Then what I would have done? Okay, I will just solve it. Okay, for you guys, I will just solve it. I will just completely solve it. At first, I will consider Jenner to be in breakdown. I will consider Jenner to be in breakdown. So let Jenner to be in breakdown. Let Jenner goes into breakdown. So I will have to draw the circuit now. Or can I copy? Let's copy. So if Jenner goes into breakdown, then what will happen? This will be replaced with the battery of 5 volt. This will be a battery of 5 volt. Smart move. Battery of 5 volt. Now VB is 0, so same 5 volt will be copied here. If this same 5 volt is copied here, this is driving 0.5 ampere current. I don't know whether it will be used or not, but let's just say it is driving 0.5 milliampere current. Okay, 0.5 ampere current. Okay, then what else do you know? Do you know the current here? Now, what if I take this node is 25 volt? I don't know this node, but I know one thing. This is my IE current, that is 0.5 ampere. IE current is 0.5 ampere. What will be my IB current now? IB current would be 0.5 divided by 100. So you can say 5 milliampere. So this current is 5 milliampere. 5 milliampere. This was actually 500 milliampere. Okay, then anything else you know? You can determine this current as well, which will be nearly 500 milliampere. Now let's just assume this node is V. This node is V. So what will be this node? V plus 5. So this will be 495 milliampere actually. This will be 495 milliampere. Because this is 500 milliampere, this is 5 milliampere, so this will be 495 milliampere. This is V plus 5. So I can write down the current in this one. Okay. I can write down the current here. That would be, yeah. So I will have the relation now. So I can write the current in this direction, that would be 25 minus V minus 5, that would be 20 minus V by 7 milliampere. 25 minus V minus 5. So 20 minus V by 7 milliampere. From here 5 milliampere current is going, so what will be this current? This current would be 20 minus V by 7 minus 5. And all these are milliampere current. And this current is 0.5 ampere, or you can say 500 milliampere. 500 milliampere. So this current plus this current is equals to V by 20. Basically, what is the current? 20 by 7 minus 5 minus V by 7 plus 500. All these are milliampere current divided by V by 20. This would be ampere current. This would be some ampere current. You need to convert it into milliampere. Are you getting this point? These currents I have written, these are all are milliampere current. 25 minus V minus 5. So basically 20 minus V by 7 milliampere, then 5 milliampere. So this current is 20 by 7 minus V by 7 minus 5 plus 500. All these are milliampere current, right? So here there is 10 to the power minus 3. So you have to multiply 10 to the power 3 here. 10 to the power 3. Are you getting this point? Now I will solve this equation and we'll see what is the answer of V we get. Okay. So by solving, this is the value of V we get. Okay. This is the value of V we get. Okay. Now we need to check what is the current in the Jenner. Let's check the current in the Jenner, because everything is roaming around Jenner only. So let's check the current in the Jenner. What is the current you will get? 20 minus V by 7. 20 minus V by 7. So 20 minus 9.92 divided by 7 minus 5 minus 3.56 milliampere. Minus 3.56 milliampere. Do you think is it possible? You are saying that this current is minus 3.56 milliampere. That means from here 3.56 milliampere current is flowing. First you were saying that your Jenner is in breakdown. Now you are saying that the current is flowing from P to N. Is that possible? No. Certainly Jenner is not going into breakdown. That's for sure. The Jenner is not going into breakdown. That's for sure. Are you getting this point or not? Your Jenner didn't go into breakdown region. Well and good. So here we got to know that Jenner is not in breakdown. Jenner, wait a second. Jenner not in breakdown. Okay. So now what I would do, I would apply the open circuit test and I will see the operating condition of Jenner now. Okay. This is how I would be doing in the examination. Okay. I am telling you the way I would be approaching in the examination, because in the first glance, it would look like that this will go into breakdown. But then I checked, it is not going into breakdown. Okay. In the first glance, everyone would think this would go into breakdown. I am pretty sure every student would have thought in the same way. But now I need to apply open circuit test. I got to know that it is not in breakdown region. So now I am going to apply open circuit test and I will check the operating condition of this Jenner. So I will again copy the same circuit. I am going to apply open circuit test now. So this will be my open circuited path now. This is open circuited. Okay. This is open circuited. I need to check what is the potential I will get. Everything I will see, and we will see if it is going into forward bias or reverse bias. So let's just assume this potential is V. So what this potential will be, this is also having 0 voltage drop. So this potential will also be V. So what this potential will be? 2V by 3. Say yes or no. So across Jenner you are having V and 2V by 3. V and 2V by 3. How was your Jenner looking? Like this. Here you are having V, here you are having 2V by 3. So it is again not going into forward bias unless your V is negative. Unless your V is negative, it is not going into forward bias, that's for sure. Unless your V is negative. Let's just say V is positive. So this node will be 1, this node will be 2 by 3. So it will be in reverse bias only. If V is negative, then this will be minus 1, this will be minus 2 by 3. Then something can happen. So let's find out the value of V. So we have applied open circuit test. If we have applied open circuit test, then what this current will be? 25 minus V by 7K, right? This current would be IB. And what this current would be? This current would be IE. That would be 2V by 3 divided by 20K. That would be V by 60K. Sorry, V by 30K. V by 30K. This current is V, not K, K is not there. 2V by 3 divided by 20, V by 30. This current is V by 30 and this current is 25 minus V divided by 7K. So what you can write? Beta value is 99. So 25 minus V divided by 7000 into 100 is equals to V by 30. So this and this got cancelled, 0 and 0 got cancelled. So what you will get? 75 minus 3V is equals to 7V. Say yes or no. This and this 0, 0, okay. 75 minus 3V is equals to 7V. So 10V is equals to 75. So V is equals to 7.5 we are getting. V is equals to 7.5 volt. V is equals to 7.5 volt. So what about the Jenner now? This is 7.5 volt and the other one is 7.5 into 2 by 3, 5 volt. And VZ was 5 volt. This is having only reverse bias of 2.5. Reverse bias of 2.5. So it is going into reverse bias. And if it goes into reverse bias, then the open circuit test was applicable. So what will be the current in 20 ohm resistance? So your answer I. Now what will be the current in 20 ohm resistance? This current I, that would be V by 30. V by 30. 7.5 by 30. That would be 2V by 3 divided by 20. Or you can say V by 30. 7.5 by 30. 7.5 by 30. That would be 0.25, or you can say 2 into 7.5, so 50 by 60. I answer is 250 milliampere. This was a very good question. I just showed how you would be doing in the examination, because in the examination it will feel like that it will certainly go into breakdown. But when we solved, we got to know that it is not going into breakdown. So in the examination, how you would be solving, that I did here. Okay. Otherwise, I could have directly come to this tab that will not go into breakdown, and I could have solved it and I could have shown you that this is 2.5, so it is not going into breakdown. This is reverse biased. But in the examination, certainly if I had been the student, if I had been there in your place, I would have also taken it to be in breakdown, because it seems like that. But they framed the question so smartly that even your assumption is wrong. And for that you need to do this very complex calculation. I'm pretty sure this calculation is not that straightforward. You need to think like what current I should write. So this calculation is not that straightforward, and I hope I did the calculation correct. I will check it. So here I got to know that it is not going into breakdown. So then I did this thing, it is going into reverse bias. Well and good. Let me check the calculation, then we will solve this question. So for some time you can try doing it on your own. Pause the video, try doing it on your own, then we will solve this question. Okay then. So let me check the calculation and then we will solve. Yeah, so let's solve this question. This is one of the finest question of current mirror circuit. I will say the finest question of the current mirror circuit that is asked in the gate examination. Okay, so we need to find the V out potential here. Now what is the line given? Transistor Q1, Q2 and Q32 are identical in all aspect. So all these are identical. I told you one thing, identical means matched. All these are matched. I told you one thing, matching means only the reverse saturation current is same. Okay, it doesn't mean VB value is same. It doesn't mean VB value is same. VB can be different. This is the most important line. Many students mess it up here, that if they see matched word or they see this identical word, they assume that VB value is also same. Nah, VB value is not same. They are having VP value as VB. For these transistor, VB value is VP. But for this transistor, VB value can be different. So let's assume this potential is Vx. So for this transistor, VB value is Vx. So here VB1, if I say, that is Vx, and from VB2 to VB32, from VB2 to VB3 to VB32, that is equals to Vp and that is equals to 0.7. This is what you know. This is the op-amp which is working in negative feedback because some part of output is coming towards the negative side. This is working in negative feedback. That means if this node is Vx, this node will certainly be Vx. This node will certainly be Vx. One thing also I can see, all are having the same VB potential. All are biased in active region. So that means all will drive the same current. This is I, this is I. So this will also be I. So this will drive 31 I current. Better I should call I dash. I dash. This is also I dash, I dash. So this will drive 30 I dash current. Right? Both are having different VB. This VB and this VB different. So this transistor Q1 will not drive I current. That's for sure. This will drive some I current. This will not drive some I dash current. Are you getting this point? Q1 and Q2 are having different VB voltage. So they will not drive same current. They have the same reverse saturation voltage. They have the same VT value as well, but they have the different VBE. So that means they will drive different currents. So let's just assume this is driving I ampere current. What is current I? Current I would be IS exponential VBE. What is VBE? Vx by Vt. Right? And what will be your I dash? I dash would be IS, it would be same because they are matched, exponential. What is VB? VB2 you can write, or VP, because here what is the VB potential, that is equals to VP only, divided by VT. This will be your I dash, right? Now this is current I, and this will drive 0 ampere current because this is the input of op-amp. This will drive 0 ampere current. So this current will also be I. Say yes or no. Well and good. If this potential is Vx, then what will be this potential? This voltage drop will be in this direction. So this potential would be Vx plus 20I. I can say I am assuming I to be in milliampere. I am assuming this current to be in milliampere. So I can write this would be Vx plus 20I. So this node is Vx plus 20I. Vx plus 20I. This node is Vx plus 20I. So what will be the current here? Vx plus 20I minus Vx divided by 20. So this current will be I only. Say yes or no. Let's just call this current is some I double dash. So what will be the value of I double dash? I double dash would be Vx plus 20I minus Vx, because this node is copied here, divided by 20. That would be equals to I only. So this I double dash is equals to I only. Now this I current is flowing here as well, because input of non-inverting terminal will drive 0 ampere current. So what are you getting here? That your I is equals to 31 I dash. This is what we got here. Did you understand this point or not? I is equals to 31 I dash. Understood this point? We started from here, we got to know that VB potential are not same. So this I assumed Vx potential. If this is Vx potential, this would be Vx plus 20I. Then I can see something that Vx can be copied here. So I got to know that I can derive some relation in the current. Certainly I can derive some relation in the current. So the relation is coming out to be, this current is I and the lower current is 31 I dash. So I is equals to 31 I dash. This is the relation I came up to. I is equals to 31 I dash. What was your I? I was IS exponential Vs by Vt. And what is your I dash? I dash is 31 Ix exponential Vp by Vt. Vp is given, that is 0.7 by Vt. Vt neta value is given or not? If neta is not given, I will take neta equals to 1. So I don't think any neta is given there. Okay. So if I solve this, what I will get? My target is to find Vx potential. Exponential Vx minus 0.7 divided by Vt is equals to 31. Just I took this one here, nothing else. So ln 31 ln into 0.026, because Vt value is given 25 or 26. So ln 31 into 0.026 plus 0.7, that is coming out to be 0.789. So my Vx potential is coming out to be 0.789 volt. This is my Vx potential which I have found. So this was 0.7, this was 0.789. This was 0.789. So what I got to know, between this 5 kilo ohm resistance, this is my 5 kilo ohm resistance. One node of this 5 kilo ohm resistance is Vp. This node is Vp, that is 0.7. And the other node is Vx, that is 0.789 volt. Other node is Vx, that is 0.789 volt. And this is your 5 kilo ohm. Right? Above this 0.789 kilo ohm, what is connected? Above this, there is 20 kilo ohm resistance connected. This is 0.789. This is some 20 kilo ohm resistance that is connected here. 20 kilo ohm resistance, and this node is connected to V node. 20 kilo ohm, and this node is connected to V node. What I can do, I can find out this current and simply multiply it with 20, and I will get V node. So what will be my V node? Let's just say this current is I. So what will be my V node? V node will be 0.789 plus 20k into I. That's it. And what will be my I? That would be 0.789 plus 20. I would be 0.789 minus 0.7 divided by 5. That would be the final answer. 0.789 minus 0.7 divided by 5 into 20 plus 0.789. So 1.15. 1.15 volt. This is your V naught. That's it. So these kind of questions doesn't click that quickly in the examination. So in the examination, you just need to think that what is different, Vx is different. So I need to write down some equation now. I need to write down I need to relate the current, and here I can see both resistance are same. So certainly there will be some relation coming. So if I assume there is I current, so that would be Vx plus 20I. So here Vx node is there, so this current would be I only. So this I is equals to 31 I dash. So I dash and I, there is certain relation between I dash and I as well. Then I can find out my Vx potential. If I have found out my Vx potential, then my path is very easy. Because if this Vx I know, this Vp I know, then I know this current. If I know this current, the same current will be flowing through this 20 kilo ohm, then I can get the V node potential. So V node potential will simply be 0.789 plus the current flowing into 20k. That's it. So this was the final answer, and this is the best approach of solving this particular problem. Okay then, thank you. So this was it. This was the complete solution of our assignment. So I hope now you are comfortable with the DC biasing part, current mirror, Jenner diode, whatever they can include. I hope you are very much comfortable with all these things. In the next video, what we are going to cover, we are going to cover the small signal analysis of BJT amplifiers. So now we are moving to small signal analysis. Okay then, thank you. Hi everyone. So now we are going to study the small signal analysis of MOSFET amplifier. So first we will draw the model, then we will see how to analyze the amplifier. Well and good. Now this is our BJT. Simple VB is there, VC is there, IC current is there, IB current is there. In which region we need to bias the BJT for amplification? In active region. Why active region? Because in the active region, your output current is IC. This output current is not depending on output voltage. Here your IC current is not depending on output voltage. What is this? This is VC. This is VC. In active region, even if your VC is increasing, your current is constant, and this is what you want. Your output current should not depend on the output voltage. This was the same case in case of MOSFET as well. ID versus VDS curve, ID versus VDS. So in this region we biased it, right? So your output current should not depend on, IC is not a function of output voltage. That's why we bias it in active region. Well and good. So these are the equations of IC. Actually, it doesn't depend on output voltage, but sometimes it does depend. Practically, it depends on output voltage by this factor 1 plus VC by VA. This thing we have already seen in the biasing part. So this is the ideal equation. IC equals to IS exponential VB by eta VT. But practically, this is the equation that there is a finite slope as well. Practically, there is a finite slope. This finite slope is there, but ideally, this is the equation. And one more thing we already know, in active region, IB equals to IC by beta. This is applicable. Now, how did we replace our MOS? If you remember, there was an input resistance which was infinite, then there was a current GM VGS, then there was output resistance R0. This was your MOS, right? From input side there was infinite resistance, 0 ampere current was there, infinite resistance, then there was a current source which was depending on this voltage, VGS voltage, GM VGS, and then R0 resistance was there in between these two nodes. So this node was drain, this node was source, sorry, this node was drain, yeah, this node was source, this node was source, and this node was gate. Between gate to source, whatever the potential was coming, that was multiplied with the GM, and this current would have been flowing here, and at the output you were having R0 resistance. The same thing we are going to do with the BJT. So at the input side, here the resistance is not infinite, here the resistance is finite. That is the only difference between MOS and BJT, that here this particular resistance is finite. Why is it finite? Why this resistance is finite? Because IB current is not zero. This IB current is not zero. So this resistance is finite, and then whatever the potential that is coming across base to emitter, VBE, that will be amplified with the factor of GM, and that would make a current source. This is the current source, this IC current source that will flow from collector to emitter. You know the direction, this will be the direction. So basically, whatever the voltage that is coming here, that will be multiplied with the factor of GM, and that much current will flow from here. Are you getting this point? Let's just say BJT is there. So what you will do, what voltage is coming? Multiplied by GM, that much current will be flowing here, and then there is a resistance R0. That's it. Did you understand this point? This is the model. Whatever the voltage is coming, this much of current is flowing, and there is a resistance R0 connected. The only difference is, in MOSFET, what do we used to say? That in MOSFET we used to say there is 0 ampere current, right? And 1 by GM resistance is there. But here, the voltage that is coming, that would be across R pi. Are you getting this point? Between base to emitter, between base and emitter, there is R pi resistance connected. Between base and emitter, there is R pi resistance connected. Did you understand this point or not? We will see more examples. The model will be more clear to you. You don't need to stress much on this. We will solve the examples. It will be more clear to you. No worries about it. Okay. When we solve the example, it will be more clear to you. For now, let's find out this GM value, this R0 value, and this R pi value. So what will be your GM? GM will be output current divided by input voltage, del IC upon del VB. This will be your GM, right? Del IC upon del VB. So what is your IC? IC is IS exponential VBE by eta VT into 1 plus VCE by VA. This is your IC. So what will be your del IC upon del VB? That would be IS as it is e to the power x. What is the e to the power x by eta VT? What is the differentiation? It would be e to the power x by eta VT divided by eta VT. That would come exponential VBE by eta VT divided by eta VT, and this is a constant term that will come as it is. What is coming? Del IC by del VB. What is that? That is equals to GM, and that is equals to this much of expression is equals to IC only. Say yes or no. This much of expression is equals to IC by eta VT. That's it. So this is the expression of GM that you need to remember. Like in MOSFET, we need to remember the expression of GM, that was root 2 mu n CUX W by L into ID. This is what we used to remember. But here also you need to remember that GM expression, that is IC upon eta VT. Whenever I say GM, you need to tell IC upon eta VT. And if eta is equals to 1, then GM would be equals to IC by VT. So this is what you need to remember. It should click to you as just as I say, what is your GM value? IC by VT. That's it. Well and good. Let's find the other thing, that is, let's find R0 now. So what will be your R0? R0 will be output resistance. R0 is output resistance. So it would be 1 upon del IC upon del VC, or I can say del VC upon del IC, right? Difference change in output voltage with respect to change in collector current, del IC upon del VC, or I can say 1 by del IC upon del VC, del IC upon del VC. What is your IC? IC is IS exponential VBE by eta VT into 1 plus VCE by VA. What you need to do? Del IC upon del VCE. So this much value is constant only. So IS exponential VBE by eta VT. Differentiation of this with respect to VCE, this value with respect to VCE, it would be 1 by VA. So what will be your 1 by R naught? 1 by R naught would be IC ideal, I can say IC ideal, because this is the IC ideal, right? IC ideal divided by VA. So what will be your R naught? So R naught will be VA upon IC. So whenever I say what is R naught, you should remember R naught is VA upon IC. So these things you need to, this is also you need to remember, and this is also you need to remember. When I say what is R naught is VA upon IC, and if VA is infinity, then R naught is also infinity. Let's find the other thing, that is the last thing, R pi. Let's find R pi. So what will be your R pi? R pi is the input resistance, so that would be del VB upon del IB. R pi would be del VB upon del IB, or I can say 1 upon del IB upon del VB. Simple derivation is there. If you have any device, you can find out these parameters for any particular device, for any device. It's not that it is necessary to be BJT, MOSFET, diode. They can give any random device, you can find all these parameters: input resistance, GM, and output resistance, right? So yeah, del IB upon del VB we need to find. So what is IB? IB is IC by beta. Say yes or no, right? So what will be your del IB upon del VB? That would be 1 by beta del IC upon del VB. And what is del IC upon del VB? What is del IC upon del VB? Del IC upon del VB. This is GM, right? Del IC upon del VB is GM. And this is 1 by R pi. 1 by R pi is GM by beta. So what will be your R pi? R pi is beta upon GM. R pi is beta upon GM. And if beta is infinity, then R pi is also infinity. So these three values you need to remember. R pi equals to beta upon GM. If I say what is R pi, you just need to say R pi equals to beta upon GM. If I say what is R naught is VA upon IC. And what is GM? IC by VT. So these three you should mug it up. Okay. I don't usually ask you to mug up things, but if you just remember these things, R naught is equals to VA upon IC, R pi equals to beta upon GM, and GM is IC by VT. So if you remember these things, your calculation will be very, very shortened. Now let's see. So these are the parameters, and then we will put it here, and we can find anything, input resistance, small signal gain, anything. Let's just see one more important point that will help to reduce our calculation. What do you know? This current would be small signal current I am talking about. This current would be IB, right? This current would be IC, and this current would be IE. Say yes or no. You know this thing. From emitter, IE current would be flowing. This current would be IE. There is no doubt about it, right? Now this current is IB. So what I am saying, listen to my line very carefully. Whatever the current that is flowing through R pi always IB current will flow, because base is directly connected to R pi. No one can change this thing. Between base and emitter there will always be R pi resistance. So in R pi there will be always IB current. So whatever the current that is flowing through R pi, multiply by beta will be the collector current. That means this will be beta IV. So my target would be to find the current in R pi, whatever the current that is flowing in R pi into beta will be this current flowing from this side. Whatever the current that is flowing through R pi into beta will be this current. Why I am telling you these two models? Because this is what we are going to use. When I use it in the examples, you will get to know what I am doing. This I am going to use when I directly see what is applied across base to emitter potential. Directly what is applied to base to emitter potential. If I know this thing, then I will simply multiply it with GM and I will get this current. Always my target will be getting this current, this output current. This would be my target. So how will I get there? The second thing is, let's just say if there is some source resistance connected. So finding VB would be a tough task now, right? Because input will be there with respect to ground. Input will be there with respect to ground. So finding VB would be a tough task. So for that, what I need to do, finding VB will be a tough task. So for that, I will find the current in R pi, multiply by beta will be the collector current. That's it. And then my problem will be shortened. So let's see the questions. You need to find the voltage gain in this one. VA is not equals to infinity. If VA is not equals to infinity, that means here you are having R0 resistance, right? This is the R0 resistance. If VA is not equals to infinity, you are having R0 resistance. Can you tell what is the VBE potential here? VBE, base to emitter potential. Directly I can say it is Vin. Directly I can see it is Vin from base to emitter potential. Base is at Vin, emitter is at 0. So I know base to emitter potential is Vin. So what will be the current here? That would be Gm into Vin, no doubt about it. And the same current is flowing through R0. So what will be your V0? V0 will be minus Gm into R0 into Vin. So what is the voltage gain? Voltage gain is minus Gm R0. No doubt about it. Very easy. Tell me what will be the input impedance if they ask you what is the input impedance. Is it infinite? No. From base, how much resistance do you see? R pi. Input resistance is R pi. What is the output resistance? If you say what is the output resistance? For finding output resistance, this should be shorted. If this is shorted, then VBE is gone. VBE is gone. If VBE is gone, then R0 will be equals to R0 only. That's it. Very easy thing. Very, very easy thing. No doubt about it. Well and good. What will be the current gain? This is the input current. This is the input current. Just a second. Yeah. So let's find the expression of current gain. If this is I in, this I am calling I0. So what will be my I in? I in will be 0. No, I in will not be 0. Why is it so? Because I know from V in to emitter is grounded. So from V in to ground, there is R pi connected. From V in to ground, there is R pi. So my I in is equals to IB only. So what is my I in? My I in is V in by R pi. Say yes or no. This is my I in. What is my I out? I out is V0 by R0. Right? So what do I need to find? I out by I in. So my I out by I in would be V0 by R0 into R pi by V in. What is V0 by V in? V0 by V in is minus Gm R0 into R pi by R0. So minus Gm into R pi. This is the current gain. I0 by I in is minus Gm into R pi. And what do you remember? What is beta? Beta is, I don't remember beta. I remember one thing, R pi equals to beta upon Gm. This is what I remember. R pi equals to beta upon Gm. So what will be your beta? Beta will be Gm into R pi. So what will be the current gain here? Current gain will be minus beta. So this is the final answer. Current gain is minus beta. Also you can see one more thing. What is your I out current? I out current. What is I out current? How did I write Gm into R pi equals to beta? Here you can see. Beta equals to, what is beta? Beta is equals to, sorry, R pi is equals to beta upon Gm. This is what I remember. R pi equals to beta upon Gm. So I will just write, I need to remember what? R pi equals to beta upon Gm, R naught is equals to Va upon Ic, and Gm is equals to Ic by eta Vt, and eta will be 1 in most of the cases. So these three formulas I have to remember. From there I can change my expressions. So your current gain is minus beta. Also what you can see, what is your II? That is your base current, IB. What is your I naught? I naught is the negative of, I naught is negative of IC, because this will be your IC. So negative of IC. So what will be your current gain? Minus IC by IB. What that would be? Minus beta. That's it. This is how you would find the current gain. Very easy, very simple thing. This is the complete analysis of common source amplifier. That's it. In one question only, we have done the complete analysis of common source amplifier. We have found everything: voltage gain, input resistance, output resistance, current gain. Let's see another question. I am not going to deal common source. Sorry, did I say common source? It is common emitter. Sorry, not common source, because emitter is common. Common emitter. So what kind of amplifiers can be there? Common emitter, common base, and common collector. In common emitter, what we will do? You will connect your input at base, collect your output at collector. In common base, what you will do? You will connect your input at emitter and you will collect your output at collector. In common collector, what you will do? You will connect your input at base and you will collect your output at emitter. Well and good. So we are not going to specifically see all these kind of amplifiers, but we will solve a lot of problems. In the next video, you will see there will be assignment. There will be a lot of problems there. So with that, you will be able to understand every single thing. So it is the same as MOSFET amplifier only. I am telling you again and again, and I will also tell you how they will ask the question. Like, it is very rare chance, I am telling you. Look, if I tell it before, you will not be interested in learning this this particular concept. But this concept is interesting, you can learn. But there is 0.1% chance that they will ask you anything on BJT amplifier. But 0.1% chance is also good. With 1% of chance, RCB qualified for the playoffs. So there is 1% chance that there can be 2 marks question from BJTs. So you shouldn't skip. In the minimum time, I will tell you everything that is required, and whatever that I tell, apart from that, nothing will be coming. I can write it on paper and I can sign it. Okay, every subject I am teaching, apart from that, whatever I teach, nothing will come in your examination. Okay, nothing. So yeah, in the minimum time span, I will tell you whatever that is required. Now this is the question. This is some VCC potential you can give, or whatever it is. Some VCC you can give, and you can say VA is equals to infinity. Now you need to find this input resistance. This is your question. Find the input resistance. What do you think? What will be your answer? R pi plus RE. R pi plus RE. Is that the answer? Yes, sir. From here to here, from base to emitter, I see R pi, and from emitter to ground, I am seeing RE. So R pi plus RE. This is the answer. No. Why is it so? Because I told you how much current is flowing in R pi. This node is V in, base is V in. Okay. From base to emitter, what do you see? R pi. There is no doubt about it. This is R pi. This is emitter. From emitter to ground, what do you see? RE. From emitter to ground, what do you see? That is RE. Tell me one thing. How much current is flowing through R pi? That is IB. IB, right? This will also be IB. So eventually, what is your R in? That is V in upon IB. This is your R in. This is your target. V in upon IB you need to find. How much current is flowing through this RE? How much current is flowing through this RE? This is my question. This resistance RE is connected to directly emitter. So it is driving IE current. Say yes or no. So that's why I was again and again saying through R pi there is always IB current. Through R pi there is always IB current. R pi is having IB current, base current. But this RE is having collector current, which can be replaced with beta plus 1 into IB. Say yes or no. So in this loop you can apply KVL, right? In this loop you can apply KVL. So what will be your V in? V in will be equals to IB into R pi plus beta plus 1 into IB into RE. So what will be your V in upon IB? that is equals to R in, that is equals to R pi plus beta plus 1 RE. R pi plus beta plus 1 RE. R pi plus beta plus 1 RE. This is the final answer. Okay, R pi plus beta plus 1 RE. Well and good. What did you do? From base to emitter, I know I see R pi. From emitter to ground, I am seeing RE. But there is one thing that R pi is driving IB current, but RE is driving IE current. So IE current is beta plus 1 into IB. My target was to find V in by IB, so that would be R pi plus beta plus 1 into RE. Let's move towards the next question. You have to find small signal voltage gain. VA is infinity again. You have to find small signal voltage gain. So how much current is flowing through this RL? IC current is flowing, right? IC current is flowing. Now, I have the one way, that is I find the potential here and then simply multiplied with GM and then this resistance. What do I mean to say? I find the potential here, that is VBE. Then GM into VBE current will be flowing here and V0 will be minus GM into RL into VBE. Now tell me one thing, finding VB is that much easy or it is difficult? Like directly just by seeing the circuit. It is not that straightforward, because in MOSFET what we used to do, that we used to say, sir, this is 1 by GM and this is RE. This is 1 by GM and this is RE. And this was your VE. And this used to be our VGS. This would be our VGS, right? This would be our VGS. Now I can simply divide the potential, because I know that 1 by GM and RE both are driving the same current. 1 by GM and RE both are driving the same current. So if I need to find VGS, that would be simply 1 by GM upon 1 by GM plus RE into VE. So simply 1 plus GM RE into 1 into VE. That would be the current. And that current would be flowing through RL. That would be my final answer. And there also we need, remember the answer, that is GM RL upon 1 plus GM RS. Actually this is source resistance, or we can replace it GM RE. But here the thing is, what is the thing? That V from V to emitter, you see R pi, then you see RE, and both are driving different current. So you cannot even apply potential divider here. Both are driving different current, so you cannot even apply potential divider here. So how will you solve it? Let's check that out. So this is the way I use. You can also try finding VB, and you can also do in this manner as well. You can find VB and then simply V0 would be equals to GM into VB into RL and negative sign. So this is also you can do, but what I usually do, that is that this is your V in. From V in, from base to collector, what do you see? R pi. Sorry, from base to emitter, what do you see? R pi. From emitter to ground, what do you see? RE. What will be my V0? My V0 will simply be minus IC into RL. My target is to find IC, that's it. If I know IC, that would be it. In terms of known things, so this is my R pi, this is my RE. How much current this will drive? IB. How much current this will drive? IE. So what I can write? V in is equals to IB into R pi plus beta plus 1 into RE, beta plus 1 into RE into IB, because this can be replaced with beta plus 1 into IB. So what will be my IB? IB will be V in upon R pi plus beta plus 1 into RE. IB is V in by R pi, V in by R pi plus beta plus 1 into RE. What will be IC? If this is IB, so what will be my IC? Here I can write IC will be beta IB, and that would be beta into V in R pi plus beta plus 1 RE, right? This is your IC. So what will be your V0? V0 is minus IC into RL. So minus beta RL upon R pi plus beta plus 1 into RE into VE. So this is your voltage gain, that's it. V0 by V in. On the next page I can write my V0 by V in is coming out to be minus beta RL upon R pi plus beta plus 1 RE. This is what we are getting. Well and good. Now we can approximate it. How we can approximate it? Let's take R pi common from here. So this is the gain. This can be one of the expression. Minus beta RL upon R pi plus beta plus 1 RE. I do not recommend to remember this expression. I do not recommend to remember this expression because you would be able to derive it there, right? You would be able to derive it. You would know that there is R pi, there is IB current, there is IE current. Then V in by IB would be simply R pi plus beta plus 1 into RE. So that would, from there I can directly write IC current as well. If I know IC current, then I can simply write my V naught. That's it. So it is very, very easy. Once you have enough practice, you will be able to solve these kind of problems very, very quickly. So no worries about that. You don't need to remember it. But we can write down other expression as well. What I am going to do, I am going to take R pi as common. Beta upon R pi divided by 1 plus beta plus 1 divided by R pi is upon RE. R pi is equals to beta upon GM. R pi is equals to beta upon GM. This is what I remember. So beta upon R pi is GM. So from here, beta upon R pi is GM. So this could be replaced with minus GM RL upon 1 plus beta plus 1 upon R pi. So what I can assume is that this was also in bracket only. So I can assume is that beta plus 1 is approximately equals to beta only. Beta plus 1 is approximately equals to beta because beta is generally very high. So beta upon R pi will be GM only. So isn't it being the same expression? Minus GM RL upon 1 plus GM RE. Minus GM RL upon 1 plus GM RE. Minus GM RL upon 1 plus GM RS. Isn't it being the same expression? The only thing is I have to take an approximation here. In the examination, if they are asking these kind of questions, which they will not ask, they will give beta value to be very low. Let's just say they will give beta value to be 9. So that the assumption that you made here, beta plus 1 is almost equals to beta. So 9 plus 1, 10 is not almost equal to 9. Okay. If beta is 100, then you can say 101 is almost equals to 100. But 10 is not almost equals to 9. So these kind of things they can do in the examination. So you should have the clear idea. Not that you should remember only this formula. You should have the clear idea. Whatever the assumption that we are taking. This was without any assumption. But here there is one assumption, that is beta plus 1 is equals to almost beta. But this expression we got without any assumption. Well and good. Let's move towards the next thing. So these kind of questions can be asked in the examination. In 2017 and lastly in 2020, these kind of questions were asked where they give beta equals to infinity. If they have given beta equals to infinity, your BJT can simply be replaced with MOS. That's it. If they are giving beta equals to infinity, your BJT can be replaced with MOS and the small signal analysis will be as it is. Just you need to remember few things. Yeah, so what I was saying, if beta is equals to infinity, R pi would be equals to infinity. So small signal analysis of MOS will be equivalent to the small signal analysis of BJT. So your BJT can simply be replaced with MOS. So if it is NPN, this can simply be replaced with the NMOS. And if it is PNP, it can simply be replaced with PMOS. Right? So, yeah, so really sorry for the interruption. Actually, a call came in between. So another one. Yeah, so again, sorry for the interruption. So we will solve the problems now. What did I say? I will tell it in the conclusion that if beta is equals to infinity, then your BJT will be replaced with the MOS only. Your NPN will be replaced with NMOS and PNP can be replaced with PMOS. Well and good. We will solve the problem. Just remember one thing, that GM value will not be same as PMOS. Okay, those parameters GM are not these parameters GM, R naught and R pi. Where are those parameters? GM, R naught and R pi. They will be of BJT only, but the small signal analysis will be same. Here I have written small signal. Small signal model will be same. AC analysis will be different. Sorry, DC analysis will be different. AC analysis will be same. So let's solve some problem. So this question was given. This was asked in GATE 2020 or 2017. I don't remember. You need to find Q1 and Q2 are biased with 2.6 milliampere current. This is 2.6 milliampere current. Okay, you need to find the small signal voltage gain. So this is V naught, this is V in, and beta is equals to infinity. Beta is equals to infinity. That is given. Beta is equals to infinity. So tell me one thing, what you will see from here, from downward direction. I will copy the circuit. I will just copy the circuit on the next page. Then we can analyze it. So this current is 2.6 milliampere. That is a DC current. So what will be your GM value? First tell me. Both of them are having the same current. So what is GM? GM is IC by VT. If both of them are having the same current, that means both of them will have the same GM value as well. So 2.6 milli divided by VT, 26. That would be 1 by 10. So GM is 1 by 10. GM is 1 by 10. Now this collector will be shorted in AC analysis. Collector will be shorted. So this is the thing we did in DC analysis. DC analysis is done. That's it. This much was required. We just needed to find GM potential. And VA is equals to infinity. So R naught will be infinity. R naught is equals to VA by IC. IC is some finite, but VA is infinity. So it would be infinity. Right. So this will be shorted. So this node will come to ground. If this node is coming to ground, so from downward direction, what do you see? 1 by GM. Right. So, and this 5 volt will also be shorted. So how will my equivalent circuit look like? In the downward direction, you are having 1 by GM. 1 by GM means 10 ohm. This is V in, and this is your V naught. This is what? 1 kilo. This is the scene, right? V naught by V in. Beta is equals to infinity. I can simply call this transistor as common source amplifier with degeneration. Say yes or no. Common source amplifier with degeneration. Do you remember the gain? Gain is minus GM. Did I put minus sign here? Okay, yeah. So the gain would be minus GM RL upon 1 plus GM RS. This was the gain. Common source amplifier with degeneration, minus GM RL into 1 upon GM RS. So what is the GM value? 1 by 10. So minus 1 by 10 into 1000. So it would be minus 100 divided by 1 plus GM RS. GM is 1 by 10 and it would be 1 only. So gain would be 50. So AV is 50. That's it. Very easy question, very straightforward. No doubt about it. What did we do? We replaced it with 1 by GM. 1 by GM was 10 because GM was 1 by 10. So 1 by GM was 10. So this was replaced with 10 ohm resistance. This was 1 kilo ohm. So simply it was replaced with 10 ohm resistance. So what was your V naught by V in? V naught by V in was simply minus GM RL upon 1 plus GM RS. So GM was 1 by 10, RL was 1000. So it would be minus 100 divided by 1 plus GM RS. So what was GM? GM was 1 by 10 and RS was also 10. So it will be simply 50. Well and good. No doubt about it. Is there anything wrong? No, nothing is wrong. So AV is minus 50. Well and good. Let's see this problem. So in this question, capacitor are shorted at signal frequency. Again, beta is equals to infinity. VB is equals to 0.7. VT is given. You need to find the small signal voltage gain. So if they are asking the small signal voltage gain, certainly you would require GM value. And for finding GM value, you have to do the DC analysis. So let's just do the DC analysis first. I will copy this circuit and I will have to do the DC analysis because I need to find GM value. So let's do the DC analysis. So in DC analysis, these will be open circuited. These will be open circuited. This will also be open circuited. So this 10 kilo ohm will not even come in action. Let's remove that. And here only small signal input is given. So small signal input will also be gone. That will be grounded. So if this is 0, this will be 0.7. This node will be minus 0.7. So how much current will be here? This current I can call IE. That would be equals to IC only. and that would be equals to 9.3 divided by 20k. So whatever we get, 9.3 divided by 20k, very easy calculation, but I will do it with calculator. Okay, because I don't believe in much calculations. We are engineers, not mathematicians. 9.3 by 20, 0.465 milliampere. And if I need to find GM, because I needed IC value only, so what will be my GM? GM will be IC by VT. So 0.465 milli divided by 26 milli or 25. VT value is 26. That would be the GM value. 0.017. So 17.88 milli. 17.88 milli. 17.88 milli maho. This is the GM value you are having. Now what you need to find? You need to find small signal voltage gain. So now you will do AC analysis. Now I am going to do AC analysis. For AC analysis, what will happen? This will be shorted. This will be shorted. If this is shorted, this will also be shorted. Capacitor will also be shorted. So capacitor is shorted. So this is gone now. This thing is gone. And this will also be shorted. And this will also be shorted. This 10 volt will also be shorted. So from V0 to ground you see 10 kilo ohm. From V0 to ground you see 10 kilo ohm. So 10 and 10 will come in parallel, and effectively it will be 5 kilo ohm. This will be effectively 5 kilo ohm. Effectively it will be 5 kilo ohm. And this node is also shorted, so this can be ignored. This much can be ignored. So simply it is a very simple circuit now, right? What will be the gain? VB potential. This node is already grounded. This is grounded, so this is gone. And what about this one? What is the VB potential you are having here? That is V in. So what will be the current here? GM into V in. So what will be your V0? V0 would be minus GM into 5 kilo ohm. So only different thing here was you just needed to calculate the GM value. Minus 17.88 into 5. 17.88 into 5. 17.88 into 5. That would be 89.4 into V in. So your gain is 89.4. Very easy question, very straightforward. These kind of questions you cannot miss in the examination. It may feel like that, okay, we haven't studied BJT, they are asking small signal gain of BJT, but what did they ask? They only asked, what did they ask? They asked the DC analysis of BJT. Here they asked the DC analysis. By doing the DC analysis, you get to know that this is the IC potential, this is the IISC current. From there you could get to know the GM value, and after that they asked the AC analysis. That's it. This is what they asked. It is not the question on BJT, it's the question on BJT biasing and MOSFET amplifier. Well and good. In the next video, we are going to solve assignment. We are going to solve every possible question that is asked or can be asked in the GATE examination, or even in the interview or written test. It is very rare that they will ask these kind of questions, but still we are going to solve an assignment so that you would be comfortable with everything that can be asked. Very rare they will ask the question from MOSFET amplifier considering BJT. Amplifier using BJT, they will certainly ask MOSFET amplifier. Certainly there will be 1 or 2 questions from MOSFET amplifier in the GATE examination. No one can stop it. But from BJT amplifier, it is very rare. But still we will do it. We will be very comfortable with all kind of analysis. So in the next video, in one assignment only, we will be solving these questions. So you will be very comfortable. You don't know, currently you don't know what is as HFE or what are these things. In the next video, I will tell you what do you mean by HFE. If you want to try it on your own, so basically HFE is beta. HFE is beta. HI is R pi. And HO is 1 by R naught. Okay. HFE is beta, HIE is R pi, and HOE is 1 by R naught. So you can try these questions. Like these questions came in some 1999, okay, 1998 or 2003, 2004. At that time, BJT, okay, like some people would use BJT for amplification purpose. But now no one is using, so you cannot expect these questions to be coming in the examination. But still, we are going to solve this question. So these questions you can try. Current gain you need to find. This is a good question. Darlington pair. These kind of questions can come. This is a good question. Now simple voltage gain, again this is also a good question. You can say this is also a good question. Here Millers will be used. This you can see. So as many good questions I had, I picked those questions and simply we are going to solve all these ones. Okay, so let's meet you in the next lecture. We will solve the assignment. Okay, thank you. Hi everyone. So let's solve our assignment 20. So in this one, you need to find the voltage gain when emitter resistance RE is bypassed by the capacitor CE and to when it is not bypassed. Do you understand the meaning of bypassed? Bypassed means this capacitor C is in action, and not bypassed means this capacitor C is not in action. That's it. Are you getting this point? Bypassed means this C is in action, and not bypassed means this C is not in action. So I will tell you what do you mean by bypass and not bypassed. So when RE is bypassed, basically these capacitors will be shorted. This will also be shorted. This Vin will come here as it is. This Vin will come here as it is. Now this is shorted, this is gone. If RE is bypassed, that means this will also be shorted. This is also shorted. This is also gone. So what will be the gain? From here to here you see V in, so gain would simply be minus GM into RC. That's it. And what is GM? I told you these things: HFE, HIE, HOE. So there is no GM in the options, so I need to replace GM. GM would be, what do I remember? R pi equals to beta upon GM. So GM would be beta upon R pi, beta upon R pi. So minus beta upon R pi into RC. So what is beta? Beta is known as HFE divided by HIE into RC. That is your V naught by V in. This is V in. V naught by V in, or you can say this is your gain AV. You can call it AV1 when it is bypassed, when RE is bypassed. Now, second case, when RE is not bypassed, so simply this will be open circuited. When RE is not bypassed. Do I have another page? No. When RE is not bypassed, then this will be open circuited. There is no use of this R1, R2. This is only to bias the transistor because this Vin is directly exposed here. So there is no use of this R1, R2. This was just to bias the transistor when RE is not bypassed. If it is not bypassed, then it is open circuited. This Vin is directly coming here. So what will be the gain? Do you remember the gain? If you don't remember the gain, we can simply derive it from Vin. From Vin, what do you see? There is a R pi resistance, then there is a RE. Certainly VCC will be shorted in both of the questions. There is this R pi resistance, then there is this RE. We are moving a bit faster in BJT because we have studied MOSFET amplifier in a very in-depth manner. That's why we are moving faster. If you go to the MOSFET amplifier videos, you can see how slowly I moved there. Because I knew if I go in BJT, it will be easier for you. So what will be your V in? That would be equals to R pi into IB plus beta plus 1 into RE. This we have already seen in the previous video. So what will be your IC value? Because I needed to find this IC current. This IC current I need to find because here I don't directly see VB. So that's why I am using this method. So what will be my IC? IC will be beta into V in upon R pi plus beta plus 1 into RE. This is your IC. So what will be your V naught? V naught will be minus beta into RC. V naught will be minus IC into RC. I can write minus IC into RC. Minus IC into RC. So it would be minus beta into RC into V in divided by R pi plus beta plus 1 RE. Or you can say V in goes here, so this will be your AV2. This is your AV2. What did they ask you to find? When emitter resistance is bypassed to the, when it is not bypassed. So AV1 by AV2 you need to find. AV1 by AV2. AV1 by AV2. So what that would be? Beta RC and beta RC will be cancelled. Beta RC and beta RC will be cancelled. So R pi would come upward. R pi plus beta plus 1 into RC. I am just dividing this by this, nothing else. This R pi will remain there as it is, divided by R pi. So this would be 1 plus beta plus 1 divided by R pi into RC. Or you can call it 1 plus, what is beta? Beta is HFE plus 1. What is R pi? R pi is HIE into RC. So this is my final answer. That's it. 1 plus HFE plus 1 divided by HIE into RC. So I am not spending all these things in these H parameters, because in your whole life you are not going to use it. In your whole life, I can say, even if you become an analog designer or whatever you become, in your whole life you are not going to use these H parameters ever. So that's why I am not spending much time. I just told you what do you mean by HFE, what do you mean by HIE, what do you mean by HOE. That's it. Well and good. Let's move toward the next question. You have to find small signal voltage gain. Again, you need to find small signal voltage gain. Beta is infinity given, R pi is equals to 1 kilo ohm. R pi is equals to 1 kilo ohm. अरे यार ये कैसे हो सकता है? Beta is infinity, R pi is 1 kilo ohm. Beta is not infinity यार. Okay. If beta is infinity, then R pi would be infinity, no? Because R pi is equals to beta upon GM. So beta is not infinity. VA is infinity. R pi already given 1 kilo ohm. So let's solve this problem. So in this problem, what will happen? Shall I do it on next page, because I did not give the space. So what will happen? You know, this will be shorted, so this V in will come here. Is there any doubt? V in will directly come here. We just need to do the DC AC analysis. We need to find small signal voltage gain. We already have the R pi value. We already have R pi value. So if you have R pi value, V is infinity. Do you have GM value? No. Beta value should have been given, I guess. Let's solve it, then I will check if beta value is required or not. I guess it is required. So this is your V in. From V in to emitter you are having R pi, and then you are having, this is your V naught. So from V naught to ground you are having 0.66 kilo ohm. Well and good. R pi is 1 kilo ohm. Look, from V in to V naught you are having R pi. R pi is 1 kilo ohm, and I told you always in R pi there will be IV current, and here it will be IE current. So my V naught is, what is my V naught? V naught is 0.66 K into IE. This is my V naught, 0.66 K into IE. So I need to find IE now. So what will be my IE? IE would be V in equals to 1 K into IB plus 0.66 1 K into IB plus 0.66 K into IE. Right? So V in would be, what do I need to find? I need to find IE. So I am taking beta value equals to 99, because here beta is required. So I am taking beta is equals to 99. It is given that beta is equals to 99. So if beta is 99, then what it would be? 1K divided by 100. So it would be 10 IE plus 660 IE. Did you understand this point or not? What did I do here? This was 1K. I replaced IB with IE by 100. Say yes or no. IE by 100. Because beta is 99 I am taking. So IE by 100. I replace it with that. So it would be 10 IE plus 0.66 into K, that would be 660. So 660 IE. So IE is V in by 670. V in by 670, that I can replace here. So what will be your V naught? V naught will be 660 into V in by 670. So what will be your gain? 660 by 670. So that I can calculate 660 by 670. 660 by 670. 0.985. 0.985. So beta value should have been given, that was 99. Well and good. Look, we did nothing. It was very simple problem. Very straightforward. Very straightforward problem. Why it is very straightforward? You just need to find V naught potential in terms of V in. I know one thing, V naught is IE into 0.66K or 660 into IE. So my target is to find IE now. So from here I will get IE. This is my equation 1. From here I can get IE. How will I get IE? I know from 1 kilo ohm IB current is flowing. From R pi always IB current flows. Yeah, so from R pi there is always IB current. So V in is equals to R pi into IB plus 0.66K into IE. So I needed to get the IE potential, IE current. I need to find IE current. So I replaced IB with IE. That would be IE by 100. So I replaced it. So there I got 10 IE plus 660 IE. So my IE is V in by 670. So here I replaced V in by 670 and 0.66K can be replaced with 660. 0.985. Well and good. Let's move towards the next question. The same circuit is given. You need to find the small signal output resistance. HOE is given 0. That means R0 is given infinity. Because HOE is HOE. What is HOE? Where did I tell you? HOE is 1 by R0. So R0 is infinity. R0 is infinity. Beta is 99. HFE is beta. And R pi is 2 kilo. This is what is given. So again, let's what we need to find? We need to find R0 from here. So can I say one thing? Okay, let's just not say anything. Let's just find the value. So VS is grounded. VS is grounded. Then there is this 20 kilo ohm. There is this 20 kilo ohm. From here to here, what you will see? R pi. R pi, that is 2 kilo ohm. And then there is 0.66 kilo ohm. This is your V naught. This is where you need to find R naught. If I call this resistance as Rx, so what will be my R naught? R naught will be 660 parallel with Rx. Is there any doubt? 660 parallel with Rx. 660 parallel with Rx. Here I need to find 660 parallel with this resistance, whatever that provides. And R naught is already infinity. So it is not even coming in action. So from here to here, I replace it with R pi. But one thing I know, what is the current here? The current is IB. Say yes or no. Right? But very interesting thing will come here. I need to add a page. Very interesting thing will come. Now you need to calculate this Rx. From here you are calculating Rx. So what do you think what you can write as Rx? What will be your Rx? If I make the diagram, this was your some 20 ohm resistance, no? 20 kilo ohm resistance. This was some 20 kilo ohm resistance. And they are asking you to find this one, this Rx you need to find. So what do you think, what will be my Rx? If I apply Vx potential here, I will get Ix current out of it. So my Rx will be Vx by Ix. And what is Ix? Ix is IE, or you can say minus IE, but in small signal direction wouldn't matter much. In small signal, we will not look at the direction. Ix is minus IE. Do you understand this point or not? Ix is minus IE. So your Rx is minus Vx by IE, not Vx by IB. Are you getting this point? Here it may look like that, sir. I am calculating from here, so it would be Vx by IB. Nah. Look from here. This is 0.66K, no one can change it. But from this direction, IE current is flowing, no? You know, in R pi, IB current is there. Between base to emitter, you can replace the resistance R pi, and from that IB current is there, but you need to find Vx by IE, not IB. So what do you know? This is your Vx. This is your Vx. This is your Vx, and this was the scene. This is your Vx. This is your R pi. Vx. What was your R pi? R pi was 2 kilo ohm. This was 20 kilo ohm. And from here IB current was flowing. So can I say one thing, that Vx is equals to minus 22k into IB, because this potential plus this potential from here to here, that is equals to Vx. So Vx is 22k into IB, because from 20 kilo ohm there is IB current, from this R pi 2 kilo ohm there is IB current, and that is equals to Vx. But from Vx, what is the current flowing? That is IE. So this is the beauty of BJT amplifier. Are you able to understand this point or not? It may feel like that, sir, this IB will be flowing from Vx. But if you see the structure, from Vx, how much current will flow? IE current will flow. This is just the model. Did you understand this point or not? We are not going into complex model. We are just looking by the resistances. 20 kilo ohm and 2 kilo ohm. So Vx is equals to minus 20k into IB. What else I can write? Minus 20k into, if I need to replace IE here. So IE by beta plus 1. What is beta? Beta is 99. So IE by 100. Right? So what will be your Vx? Vx would be minus 220 IE. So Vx minus Vx by IE, that is your Rx. That would be 220 ohm. So Rx is 220 ohm. If you see from here, that would be 220 ohm. Or you can directly see this two are in series, so it will be 22 kilo ohm. But IB current is flowing, so divided by 100, beta plus 1. So that would be 220 only. That's it. This is how you could have solved if you have enough practice. If you have enough practice, you will see that, sir, okay, 20 kilo ohm and this 2 kilo ohm, both will, in both of the resistance, IB current will be flowing. In both of the resistance, IB current is flowing. That means from Vx you will see 220 kilo ohm, but from Vx IE current is flowing. So with respect to IB, if I need to write, so I have to divide it with the 100. So 220 ohm is there. So what will be your R naught now? R naught will simply be 220 ohm parallel with 660 ohm. So 660 plus 220 reciprocal into 660 into 220, 165. This is the third question. So let me recheck the calculation. This we are getting as 165 ohm. This R naught is 165 ohm. So everything was correct in this one. So I hope you are understanding how to find the resistances, all those things in case of BJT amplifier. You should have a good practice and you should have good eyes as well, that how much current is flowing from what. So I told you very simple thing. If you can see directly VB, then GMVB is the IC current. That's it. If you cannot see direct VB, you need to know from R pi always there will be IB current. For R pi, from R pi there is always will be IB current. Well and good. You need to find the input impedance in this particular question. Input impedance you need to find, then you need to find current gain as well. So there are two questions. So input impedance you need to find. So what will be your input impedance? Let's just say here there is VE and there is IE. So what will be your input impedance? Input impedance would be V in by I. But let's see it with good amount of patience. This is your V in. From V in to here, what do you see? R pi. From V in to here you see R pi. And this R pi is driving how much current? No values I mentioned here. I forgot to mention the beta value as well. I should have mentioned those values, beta and R pi. I'm really sorry. I will check the values and will mention it. So these values are given. Beta is 50, R pi is 1 kilo ohm. So this is R pi. And from V in there is I in current. From here to here you see R pi, that is gone. Now this particular branch is coming. So from here to here you will see another R pi, another R pi. And from R pi to ground you see 1 kilo ohm resistance. Now which one is driving how much current, that you need to see. By network analysis, if you see, you will say, sir, I in current is flowing from all the transistor. Is that so? No, this is not that so. What is the scene? This R pi will take base current of this one. Is there any doubt about it? This R pi will take base current of this one, because this is how I replay it. R pi will take base current of this one. What is the base current of this one? That is I in only. No doubt about it. This R pi will take, this R pi will take base current of this one. What is the base current of this? Base current of this is beta plus 1 into IE. Beta plus 1 into II. Say yes or no. Let's just say this is Q1 and this is Q2. Both of the transistors are having same beta value, same R pi value. So base current of this will be the collector current of Q1. Base current of Q2 is collector current of Q1. And in R pi there is always base current. So what is the base current of this? That is beta plus 1 into II. Beta plus 1 into II. Now what this will have? This I naught. What this will have? What this will have? This will have the collector current of Q2. So what will be the collector current of Q2? That would be beta plus 1 into II, base current into beta plus 1. Say yes or no. So this will have beta plus 1 whole square into II. So what is your V in? V in is equals to R pi into II plus R pi into beta plus 1 into II plus beta plus 1 whole square into II. So what is your R in? R in is R pi plus R pi into beta plus 1 plus beta plus 1 whole square. So this is the input resistance, which you don't need to remember, but if you remember that is good, but you don't need to remember because you will eventually forget it. Beta plus 1 whole square. What did we do? We needed to find Vi by II. There is no doubt about it. Then we started replacing. From base to emitter I can make R pi resistance, but I know one thing, it will drive base current of this one. So II is the base current. Then from here to here I can replace another R pi, but this will drive the emitter current of Q2. Base current of Q2, and base current of Q2 is the emitter current of Q1. So that is beta plus 1 into II. And what this will drive? This will drive emitter current of Q2. So what is the emitter current of Q2? That is base current of Q2 into beta plus 1. So base current of Q2 is beta plus 1 into II into beta plus 1. So that will be beta plus 1 whole square into II. So Vin is equals to II into R pi plus beta plus 1 into II into R pi plus beta plus 1 whole square into II into 1 kilo ohm. Into 1 kilo ohm. Let's just call this as RE. This as RE into RE. So into RE will also come into 1 kilo ohm. So let's find out what is your RI. RI is R pi is 1 kilo ohm. R pi is 1 kilo ohm plus another R pi that is 1 kilo ohm, and beta is 99. Beta is 50. So beta is 50. So it would be 51 kilo ohm. If beta is 50, so it would be 51 whole square into 1 kilo ohm. RE is also 1 kilo ohm. So let's find it out. 51 whole square plus 51 whole square plus 51 plus 1, 2.653 mega ohm. 2.653 mega ohm. So very high input impedance we have made. This is the input impedance. Let's find out the current gain. So what is the current gain? I naught is equals to what? I naught is equals to beta plus 1 whole square into II. This was your I naught. I naught is beta plus 1 into II. This we have already derived. From here II current is there. This will be beta plus 1 into II, and this would be beta plus 1 whole square into II. So what is your current gain? I naught by II. That is 51 whole square. And what was 51 whole square? 51 whole square was 2601. So very high current gain you are having. So this particular configuration is known as Darlington pair. So this was what? Darlington pair. Darlington pair. Here two common collector are cascaded. Common collector are cascaded. Two common collector and common collector. This is also common collector. Collector is common. This is also common collector. So two common collector are cascaded. So this is known as Darlington pair, which you can remember because this is a standard circuit and this is a very good circuit as well. Like here intuitions are used. I feel like that IE current beta plus 1 II, then beta plus 1 whole square II. So it feels like they can frame good question from it. So this is known as Darlington pair and two common collector are connected in cascade. Output of this one is fed to the input of this one, right? Let's move toward the next question. This is common emitter. This is also common emitter. Two common emitter are cascaded. Nothing else. Common emitter and this is also common emitter. Well and good. Two common emitter are cascaded. But this is a very, very interesting problem. Like a lot of guys can mess it up. How they will mess it up? Try solving it on your own, then see the solution. Okay. Yeah, so let's start solving this problem. We would absolutely need the beta value, GM value as well, so we can find the GM value. What do I remember? R pi equals to beta upon GM. So GM is beta upon R pi. GM is beta upon R pi. GM is beta upon R pi. Beta is 100 upon R pi is 1 kilo. R pi is 1 kilo, 1000 you can take. GM is 0.1 or you can say 100 milli. This is your GM, 100 milli mho. Now from here GM/Vs current is flowing. That is for sure. There is no doubt about it. GM/Vs current is flowing because here I can directly see what is my VB. VB is Vs, so GM/Vs current is flowing. Now this same GM/Vs current is flowing here. Is that correct or not? This current is GM/Vs. Is that correct or not? This is wrong. This would be correct in case of MOSFETs because this would drive 0 ampere current. Because from here you would see infinite resistance, but here there is no infinite resistance. If you see this side, there will be R pi. The input resistance of this common source amplifier is what? R pi. So what this GM/VGS will see? From this node to ground you see you have 5 kilo ohm. From this node to ground you see you have 1 kilo ohm. Are you getting this point? So the input resistance here is, the resistance here is 1 kilo ohm. The resistance here is 1 kilo ohm. So there is this GM/Vs resistance, sorry, not GM/Vs resistance, there is this resistance that is 5 kilo ohm. Then there is this current, you can make a current that is GM/Vs. This is grounded and from this node to ground there is 1 kilo ohm. Now you need to find this particular potential. Let's just call this potential as V dash. You need to find this V dash potential. So what that V dash would be? So that V dash would be GM into Vs into 1 kilo ohm parallel with 5 kilo ohm. That would be 5 by 6 kilo. So GM is 100 milli into 5 by 6 kilo into Vs. So what is your V dash? V dash is 50 by 500 by 6. I can write 500 by 6 Vs. So this potential is 500 by 6 Vs. So here you know this potential 506 by Vs. Is there any page there or I need to add it? I need to add it. So for the second amplifier, you know this potential that is 506 by Vs. So 500 by 6 into Vs, 500 by 6 into Vs. And this particular resistance is 5 kilo ohm. You need to find this V0. So what that would be? GM into this potential, that's it. GM into 500 by 6 into Vs. So what will be your V0? Also there will be negative sign. I forgot this negative sign. This is a common source amplifier, so there will be a negative sign. There will be a negative sign. Everywhere there will be a negative sign. There will be a negative sign. So negative and negative both will be positive now, because this will also give drop in negative direction. So GM into 5 kilo ohm into 500 by 6 Vs. So GM is 100 milli. 100 milli into 5 into 500 by 6. This is your V0 by Vs. What is your AV? 500 square by 6. So by solving that you will get 41,666.67. This will be the final answer. 41,666.67. So what did you understand? First, I needed to calculate the gain of this one. In this one, the important thing was, if this was MOSFET, then the gate would drive 0 ampere current. But this is what? This is BJT. So here there is R pi resistance. So 5 kilo ohm will come in parallel to 1 kilo ohm. That would be 5 by 6 kilo ohm. So V dash is minus 500 by 6 into Vs. Now this potential into Gm would be the current here, and into 5 kilo ohm, that would be your V naught. This potential Gm 500 by 6 into Vs into 5 kilo ohm is your V naught. So this is your final answer. 41,666.67. This is your gain. Well and good. Let's move to. So let's solve this question now. In this, you need to find the small signal voltage gain, V naught by Vs, and beta value is given. Everything is given. You need to find the small signal voltage gain. Options are mentioned as well. So first, what we need to do? We need to do the DC analysis, because certainly we would require the value of R pi and or Gm. Like beta value is given. If I had the value of R pi, then I could find the value of Gm, right? Or if I had the value of Gm, I could find out the value of R pi, because I know R pi is equals to beta upon Gm. But now there are two unknowns, Gm and R pi. You have only value of beta, so you have to do the DC analysis, and from there you can find out the value of R pi and Gm. So let's do the DC analysis that I have already written, so that you don't waste, so that your time doesn't get wasted. Simply, this is the circuit. This capacitor will be open circuited. This current will be IE, because this is IC and this is IB. So this current would be IE. So from here you can apply KVL. 13.7 is equals to 12k into IE plus 100k into IB plus 0.7. From there you could get the value of IB and IC. From there you could get the value of Gm. So Gm is IC by Vt, that is this one, and R pi is beta upon Gm. So this is your R pi. So let's not just waste our time here, and we have found the value of Gm and R pi. This is very, very simple. Anyone can do it if they are studying BJT from the beginning. Now we need to do the AC analysis, right? We need to do the AC analysis now. So I have seen the solution of this particular problem at many places, and what I have seen is that they will apply Miller's theorem. They will apply Miller's theorem here, then they will make some approximations. Here they will consider some resistance, here they will consider some resistance, they will make some approximation, and then they get the answer. And while making the approximation, I don't think there was any satisfactory explanation. I also tried doing it Miller's theorem, but what I found is that there is no satisfactory explanation for making those assumptions, because I told you Miller's theorem is not that straightforward. For applying the Miller's theorem, the condition is, if you are writing gain from here to here, this should drive 0 ampere current. That means your gain should be independent of this one. If your gain is dependent on this one, let's just say if it is driving some finite current, if this 100 kilo ohm resistance is driving some finite current, some good amount of current if it is driving, then your gain V naught by from here to here, this gain will depend on this RF resistance. So certainly it will be a very complex theorem to apply here. So better when we should apply the theorem, at that time when this and this is independent of this one. So what do I mean is that, you know, here if voltage V is there, this potential will be minus AV, independent of this resistance. Even if you change this resistance, if this is V, if this is V and this gain is minus A, so this will be minus AV. So directly you can apply Miller's theorem here. But here there is a risk. Depending on this 100 kilo ohm resistance, certainly the gain can change, because this can drive some current. So I prefer not to apply Miller's theorem here, but I will solve it with the complete analysis. Even if you apply Miller's theorem, even if you don't apply Miller's theorem, the calculation will be complex in both of the cases. In both of the cases, the calculation is going to be complex. So rather than applying Miller's theorem, I would prefer doing it with the complete analysis rather than applying Miller's theorem. I can do it with complete analysis. How I will do it? I can assume a potential V here. So I will apply nodal here. What will be the nodal? V minus V in by 10k plus V minus V naught by 100k plus there is some current here as well. What is that current? If this node is V, VB potential is V only. VBE is V. So what will be this current? GMV. Do you agree? Collector current will be GMV. Are you agreeing to this point? collector current will be GMV. If this node is V, so VBE is V only. VBE, base to emitter potential, is V. So this current would be GMV. What will be this current? This current is the base current. Directly you can see it is V by R pi. V from base to emitter, how much resistance do you see? R pi. So it is V by R pi only. V by R pi. Simply V by R pi plus V by R pi is equals to 0. So from here I can write V by 10k plus V by 100k plus V by R pi. R pi was 2.5k, almost 2.5k. Here I calculated 2.52, almost 2.5k is equals to V in by 10k plus V naught by 100k. This is my equation 1. Now my target is to eradicate this V. That's it. If I can eradicate this V, my problem will be solved. So for that I need to apply another nodal analysis that I can apply here. So what I can apply? V naught minus V by 100k. V naught minus V by 100k plus V naught by 12k, because 27 volt will be shorted. We are doing the AC analysis, plus GMV is equals to 0, right? So V naught by 100k plus V naught by 10k, or it is 10k or 12k, V naught by 12k plus V naught by 12k is equals to V by 100k V by 100k minus V by 100k is going here, minus V by minus GMV. So what you can write? V upon 1 by GM. V upon 1 by GM, right? Well and good. What is the value of 1 by GM? 1 by GM is approximately 25. 1 by GM is approximately 25. 1 by GM, here you can see it is approximately 25, because IC upon VT, IC is approximately 1 milliampere, VT is 25. So it is 1 by 25. So here what you can write? V by 100k minus V by 25. 100k is very large. That means this value will be very, very low. Say yes or no? V by 100k. V is common in both of them. This value will be very low. V by 100k will be very low. So you can approximately take it to equals to 0. You can approximately take it to be 0. So what you will get? V naught by 100k parallel 12k. Right? I can write it. Minus V by 25. How did I write it? We studied it in MOS amplifier. V naught by R1 plus V naught by R2. What you can write? V naught by R1 parallel R2. We have studied it in MOSFET amplifier. So by 25. So I just need to find the value of V, right? V in terms of V naught. V in terms of V naught. So if I do that, have I written anywhere? So I can find it directly. 0.71k, 25 by 10.71, 2.23, 25 by 10.71 minus 2.33 milli V naught. This is equation 1. This is equation 2. This is the value of V you are getting, minus 2.33 V naught. So 100k parallel 12k is 10.71, or 25 by 10.71 minus 2.33 milli V naught. Okay. Now by equation 1 and 2. So V by equation 1 and 2. So what do you get? V by 10k parallel with 100k parallel with 2.5k. 10k parallel with 100k parallel with 2.5k is equals to V in by 10k plus V naught by 100k. We need to solve it with the patience. Now you can replace V with this particular potential, that is minus 2.33 milli V naught, right? Now you need to find the parallel combination of 10k parallel with 10k parallel with 100k parallel with 2.5k. So I will do it. So if you solve it, you are getting approximately equals to 0.972 into 10 to the power minus 6 V naught. And this V naught will come here, that would be V naught into 10 to the power minus 5 will be equals to V naught by V in by 10k, right? If you solve this one, what you will get? Minus 1 point, this I need to make 10 to the power minus 5, so I can multiply it with 10 and divide by 10. 0.09 minus 1 is there, 0.0972 into 10 to the power minus 5 V naught is equals to V in by 10k. So the calculation is a bit complex. I wouldn't say it is very easy. It is a bit complex, but yeah, you should be able to do it. 10 to the power minus 1. So 0.01972 reciprocal. It is coming out to be some 9.1. 0.1 9.1 approximately it is coming out to be 9.1 minus 9.1. From here if you solve it, it is approximately coming out to be minus 9.1. So the gain is approximately equals to 10, because approximate answer is there. The options mentioned is approximate answer is equals to 10. So that applying Miller's theorem, I don't find that is that much what do I say, satisfactory. Okay, that is not that much satisfactory. I don't find that much satisfactory that you can apply Miller's theorem here. Why is it so? Because if you consider V here, this would be some minus 10V. The gain is not that high. It's not that you cannot say that this will not drive some current. This will drive some current. This will certainly drive some current. So I don't think applying Miller's theorem, then taking so much of approximation. What I have seen is that the people will remove this one and then they will write the gain, that is GM into RL 12k parallel with 100k. And they are saying that this particular resistance is coming in load, and that is 100 by 1 minus 1 by A. So I can approximately take it to be 100k. So, but how did you say that this potential will be equals to V in only? Like from here to here, if you are writing the gain, from here to here, if you are writing the gain, they can do it as well. Okay. Now I am agree that from here to here we are writing the gain, from here to here we are writing the gain. So you can apply Miller's theorem as well. Considering that we have to consider that the gain A would be very high. This is the thing that we are considering. Then only it would be applicable, right? So you can do it applying Miller's theorem as well. Approximately you will get the same answer. Previously I thought we shouldn't apply Miller's theorem, but we are writing gain from here to here. From here to here, what would be the gain? The gain would be minus GM into RL, that is 12k. Parallel with this 100 will be broken into two parts. One at this side, other one at that side, but that this side one is not of our interest, because that would be 100 upon 1 minus A. That is not of the interest, because we need to find gain from here to here. So my gain would be minus GM into RL. RL is 12 kilo ohm parallel with 100 kilo ohm, because this can be replaced approximately equals to 100 kilo ohm. So there is also approximation. So yeah, you can do it in this manner as well. So you will get the same answer. So you can solve it using Miller's theorem as well. Okay then, yeah. So let's move to the next question. These kind of questions will not come in the examination now, because this is requiring a lot of calculations, and in the examination they will not expect that much of calculation from your side. So these kind of questions you shouldn't expect in the examination now. These kind of questions can come. This larger range of RE is small, is large, sorry. So what they are saying, which condition would ensure a nearly constant gain for a large range of RE? First tell me what is the gain here. What is the gain? Do you remember? If you don't remember, you can derive it. IE into RE. The gain is V naught is IE into RE. I need to find IE. So what IE would be? V in would be equals to R pi into IE by beta plus 1 plus RE into IE. From here you can write V naught is RE into R pi upon beta plus 1 IE I need to find, sorry. Let's add a page here. Okay, the page is already given. V in is equals to, now I need to replace IE only. So IE is V in by, so V naught is equals to, IE is V in by R pi upon beta plus 1 plus RE into RE. So what would be the gain? Gain would be gain AV, that would be RE upon R pi upon beta. You can approximately take it to be 1, right? Okay, let's take R pi upon beta plus 1 plus RE. That would be the gain. Now if you need a constant gain, let me check the gain expression. Yeah, so the gain expression is correct. So now if you need a constant gain, then what should be the condition for constant gain? If you need a constant gain, then your R pi upon beta plus 1 should be very less than RE, right? Because if RE is very large, then this will be replaced with RE only. And if that is replaced with RE, then RE and RE will get cancelled. And what if you say that R pi upon beta plus 1 is large? Then you will not have the constant gain, because this is GM only. This is approximately equals to 1 by GM. R pi equals to beta upon GM. R pi is equals to beta upon GM. So beta R pi upon, yeah, this is approximately equals to 1 by GM. If I am saying that this value is large, so what gain can be replaced with? RE upon R pi upon beta plus 1, that is approximately equals to 1 by GM. So gain will be GM RE, which is not constant. GM is depending on the current, IC by VT. So it is not constant. So for having a constant gain, what should be the condition? That this value should be very less. If this value is very less, then the denominator would depend on RE, and RE will get cancelled, and the gain will approximately be equals to 1, right? So this should be the condition. Now what is R pi? What is this R pi by beta? This is 1 by GM. So 1 by GM, approximately 1 by GM it is, should be less than RE, or you can say GM RE should be very greater than 1. What is GM? GM is IC by VT. So IC RE by VT should be very greater than 1, or IC by RE should be greater than VT. So this is the correct option. This is not the correct option, okay? GMRE should be very less than 1. Nah, GMRE should be very greater than 1. Did you understand the question? First you find out the gain, then we got to know that for a constant gain, this value should be lesser. If this value is lesser, than the nearly constant gain we will have. So this value R pi upon beta plus 1, that is nearly equals to GM only. So that is nearly equals to GM. So 1 by GM should be very less than RE, and GM RE should be very greater than 1. That means IC by RE, because GM is IC by VT, so IC into RE should be very greater than VT. Let's move towards the next question. You have to find midband voltage gain. This is just a question on PNP transistor, that's why I took it. PNP transistor, beta value is 80, and all these things are given. So do you have the value of IC? I only have the beta value, so I have to do the DC analysis. If I do the DC analysis, can you tell me how will I do the DC analysis? If I do the DC analysis, this is the AC potential. Vin is the AC potential, small signal potential, that will be shorted. So from here 9 volt I can apply KVL. So 9 volt is equals to 11k into IE, right? Plus 0.7 plus, I will move in this direction, 2k into IB. Did you understand this point? 9 is equals to 11k into IE plus 0.7 plus 2k into IB. That's it. My target is to find IC. So beta value is 80. So what I can do? 11k into 81 IB, and this would be 8.3 plus 2k into IB. From here I can write down the IC value. First I will find the IB value, then I will write down the IC value. So 11 into 81 plus 2 reciprocal into 8.3. This milliampere is your IB into 80 is your IC. So 0.743 milliampere is your IC. So what is the GM value you are having? GM is IC by VT. VT they have given 25.9 milli. So 28.7 milli. 28.7 milli maho. This is the GM value we are having. This is the value of GM we are having. What kind of transistor is that? Common source amplifier with degeneration. Common source amplifier with the degeneration. Say yes or no. Do you agree to my point? Let's do the AC analysis. Let's do the AC analysis. Now we will do the AC analysis. I will copy the circuit. So this is the AC equivalent circuit. Now in this AC equivalent circuit, there is this IC current is flowing. So V0 would be IC into 3.71 kilo ohm parallel with 10 kilo ohm. This will be your V0. So my target is to find IC now. So how will I find IC? So let's see from here. This is my V in. This is my V in. From V in directly 2 kilo ohm is connected. V in directly 2 kilo ohm is connected. From emitter to base. Sorry, from base to emitter. From base to emitter. What will be there? R pi. R pi will be there. Right? R pi will be there. And then from emitter to ground you have 11 kilo ohm. You have 11 kilo ohm. Right? How much current is flowing in 11 kilo ohm? That is IE. The direction is from ground to 11 kilo ohm. This is the direction of IE, right? This is the direction of IE. So this current is IE. What about this current? What is the value of R pi? R pi. Have we found the value of R pi? We did not find. So R pi equals to beta upon GM. 80 by 28.7 milli. So 80 by 28.7, 2.78 kilo ohm. So R pi is 2.78 kilo ohm. So in 11 kilo ohm there is IE current. In this 2.78 kilo ohm, this is the IB current, and in 2 kilo ohm this is the IB current. You see the direction. This is the IB current direction. This is the IE current direction. IB, and one more IB will be flowing from R pi. This is the IB current direction. So what you can write? V in is equals to 4.78 IB, 4.78 K into IB plus minus V in is equals to, because the current direction is this opposite. So minus V in is equals to 4.78 K into IB plus 11 K into IE. What is the beta value? Beta value is 80. So from here I can find the value of IC. IC would be minus V in by, or I should write the value of IB first. So IB would be minus V in by 4.78 K plus 11 K into 81. So IC will be simply multiplied with 80, because beta value is 80. So simply multiplied with 80. So what will be your V0 by V in? V0 by V in would simply be minus 80 into 3.71 K, 3.71 K parallel with 10 K divided by 4.78 K plus 11 K into 81. This is the final answer. 11 K into 81. So I will solve it and will write down the final answer. I hope you have understood the concept. Very simple concept was there. This was IC. So 3.71 K parallel with 10 K into IC is your V0. Then you needed to find the relation between IC and V in. So for that from V in IB current, R pi IB current, and in 1 kilo ohm there is IE current. So from that you find out the relation. Now we need to calculate this value. So after the calculation, this is the approximate answer we get, minus 0.24. Okay, very easy question. These kind of questions should be solved by you till now. You need to find the Rin. You need to find input resistance, this Rin. So what do you think, what will be your Rin? Rin would be V in by IE. Say yes or no. V in by IE, because this is the IE current. So your Rin is V in by IE. This is what you need to find. But from V in, what do you see? This is your V in. So from here to emitter to base, what do you see? You always see R pi resistance. Emitter to base, you always see R pi resistance. Then there is this one more resistance is there. This is grounded, right? This you can take as ground. This is 1.54 kilo ohm. And this is your R pi. This is your R pi. What is your R pi? R pi is beta is given, IC is given. So R pi is beta upon GM, and GM is IC by VT. So beta into VT, beta is 75 into VT is 75 into VT is 25.9 divided by IC is 1. Milli and milli will get cancelled. So this will be your R pi, 25.9 into 75, 1.942 kilo ohm. This is 1.942 kilo ohm. So in R pi, how much current flows? IB current flows, right? The direction will be this. IB current flows. And in this 1.54 kilo ohm resistance, IB current flows. So what you can write? V in is equals to 1.942 plus 1.54 plus 1.54, that is 3.48. So 3.48 kilo ohm into IB. You need to find V in by IE. You need to find V in by IE. We need to find IE. So I can replace IB with IE. That would be 3.48K into IE by 71. So your Rin would be 3.482 whatever it is divided by 71. So it would be some 49 ohm. The answer would be some 49 ohm. So Rin value is some 49 ohm. This is the answer we are getting. Let me recheck once if this is the correct answer. Answer is 45 ohm. So is there any calculation error? Let me check. Okay, so there was this error. This would be 76, no? This would be 76. Why 70? Because beta is 75, so this would be 76. So it would be approximately 45 ohm only. So it would approximately be 45 ohm. Well and good. Let's move towards the next question now. I hope you are understanding this concept. This was very easy. Rin is V in by IE. Okay, from V in what do you see? R pi you see, and this resistance also you see. So here you can apply KVL. In this loop you can apply KVL. So this is what we did. But from R pi and this particular resistance, IB current is flowing. We need V in by IE. So for that we converted IB into IE. Well and good. Let's move towards the next question. You have to find the current gain and you have to find the voltage gain. This is also a very good question. So current gain and voltage gain. So you have the beta value. What else do you have? You don't have R pi value, you neither have GM value. So you need to do the DC analysis. So let's just do the DC analysis first. Let's copy this circuit and we have to do the DC analysis. Why we have to do the DC analysis? Because we don't have the values of beta and GM. Beta value we have, but we don't have the values of GM and R pi. So this will be gone. Simply this is your 0.7. If this is 0, this is your 0.7. So what is your IE? IE is 10 minus 0.7, 9.3 divided by 10K. So that is 0.93 milliampere. This is your IE. So what will be your IC? 0.93 into 100 by 101. Nearly it will be equals to 0.93 only, whatever it is. Then I need to find VT. Then I need to find GM. GM is IC by VT. VT value they must have given, that is 26. So what we will get, that I can check now. 0.93 milliampere only it was. 0.93 into 100 divided by 101 divided by 26. So 35.41 millimho. This is the GM value we are getting. This is the value of GM you are getting, right? Now what we need to find, current gain and voltage gain. So let's find the current gain. They should have shown what is your I in. I in is this. This is your I in. This is your I in. They should have shown what is I in. So if I find the current gain, what do you think what will be the answer? First what we need to do, we need to do the AC analysis. So for that I guess we have to add a page. So let's do the AC analysis. For that I have to copy the circuit. This is my I in, and this will be shorted, right? This 10 volt will be gone. This 10 volt will be shorted. So if that is shorted, this is also shorted, this is also shorted. So you can short circuit them. What you can do, you can short circuit them. That's it. Because 10 volt is gone and this is also gone. This is also gone. So you can short circuit them as well, like this. This will be your equivalent circuit. Say yes or no. So what is your I in? This current is, what is this current? This current is IE. This current is IE. IE current. This current is I naught. I naught, or you can say IC current. This current is IC only, and this current is IB. In downward direction, this current is IB, right? So what this current will be? This current is IC. Okay, this current is IC. This current is IB. So what this current will be? This current will be IE only. If this current is IE only, then complete IE current is flowing here. So actually I in is 0. I in is 0 only. This is just now I noticed it, because if I short circuit them, all this will be grounded. So this is your I naught, or you can say IC, because this is your IC only, right? IC will be flowing in I naught, and now this is your IB. So IB plus IC is IE only, and this current is IE only. So complete IE is flowing here. So what is the I in current now? I in current will be 0 ampere only, right? Because from here 0 ampere current is coming. This is also, this is IE, this is IE. So must be 0 ampere current coming from here, no? At one node IE current is there, here IE current is also there. So IE current is flowing in this loop. So from here 0 ampere current is coming. So I in is 0 ampere. So what is the current gain? I naught by I in. Whatever I naught is some IC divided by 0. Current gain is infinity here. Let's find out the voltage gain now. So voltage gain Vs by V naught we need to find, right? Voltage gain Vs by V naught we need to find. So for that what we need to do? Vs by V naught. So Vs is equals to, what I see here is that Vs is equals to R pi into IB. Do you agree to this point? Because this will be shorted. Eventually this is going to be shorted. This I forgot to short. So this is shorted only. So this node will be Vs only, right? This node will be Vs, and this node is grounded. This node is Vs, this node is grounded. So Vs is R pi into IB. From Vs to ground, what do you see? From emitter to base, what do you see? R by resistance. From emitter to base. Or you can directly see this is 0, this is Vs. So you are having Vs potential across VEB. You are having Vs potential across VEB. Say yes or no. So GMVS current would have been flowing in this direction. IC current would have been GMVS. Are you getting this point or not? This node is 0, this node is Vs. So what would be the current in this direction? In this direction, the current would have been GMVS. Look, in case of this BJT, what was the scene? If this was your Vs, so your current was GMVS in this direction. Now what is the scene? Here this is grounded and this is your Vs. So your current would be in this direction from up to down, that is GMVS. GMVEB. Here the current was GMVBE. GMVBE. And here the current is GM VEB, GMVS. So this is IC is equals to GMVS, or you can solve by this as well. You can find out VS potential, then you can find out V0 potential. But we got to know this is your GMVS that is flowing through V0, that is flowing through this 5 kilo ohm resistance. So what will be your V0? V0 will be 5 kilo ohm into GMVS. 5 kilo ohm into GMVS. So your V0 by VS is GM into 5 kilo ohm. What is the value of GM? GM is 35.41 milli into 5 kilo into 5 kilo. So 177.1. This is the voltage gain you are having. Well and good. Did you understand this concept or not? Voltage gain. In voltage gain, we got to know that here we can directly see our VEB potential. That is VS. So GMVS current would be flowing in this direction. That would be your IC current. IC current would be GMVS. This is your IC current, that is GMVS. So your V0 would be GMVS into 5 kilo ohm. Okay, so GM value is 35.41 into 5 kilo ohm. So 177.1 you are getting. Let's solve this question. You have to find that overall transconductance. So what will be the overall transconductance? GM. That would be output current, which is I0 divided by VE. Tell me one thing, beta value they did not mention, so you can take it to be infinity. If this is I0, this will also be I0. Say yes or no. This is I0. Collector current is equal to emitter current. What is your GM1? GM1 is simply output current I0 divided by input voltage VE. So what is your overload transconductance? That is equal to GM1 only. That's it. This is your answer, nothing else. Very easy question, very straightforward. This was your I0 current. This would also be I0 current. What is your GM1? GM1 is I0 by V. GM1 is I0 by V. So GM is equal to GM1. Well and good. Let's move towards the next question. Again, you have to find overall transconductance, right? You don't know the current here. You don't know the current here. What is the current here? You don't know. But you know the current here as well. You know the current here. So can you write GM2? What is your GM2? Transconductor. Output current, that is IC divided by VBE. Now for this whole circuit, what is the input voltage? If I say this is my input voltage, so what will be my GM for whole circuit? Overall transconductance, that I am calling GM. Overall transconductance, that would be IC. This is the output current. They have to assume one of the output current, right? Now the thing is, why this would be output current? We cannot say this would be output current, right? The output current would be somewhat different, because IC this will drive, IC this will drive. So 2IC that would be 2IC. So output current would be 2IC. The thing is, both are having the same VB, no? Both are having the same VB. Both are matched as well. This should be given. Both are matched. Both are having same VB. So if this is driving IC current, this would also drive IC current. So effectively from VCC, how much current is coming? What I mean to say is that I will redraw this circuit on the next page. I will have to add a page. I will redraw it here. What I will do is that from VCC you are having IC current. From another VCC you are having IC current. If you cannot see it properly, this is what I mean to say. This supply is VCC. Do you agree? In this direction there is IC current, and in this direction there is IC current. So how much current is coming from VCC? 2IC. So basically if if this is your black box, this is your black box, output current is 2IC, that I need to show like this. So what will be your overall transconductance? That would be 2IC upon V in. Say yes or no, right? 2IC upon V in. What is your V in? V in is VB plus VB, 2VB. What will be GM? GM would be 2IC upon 2VB. So it would be equals to IC by VB, right? So GM is IC by VB. So IC by VB is equals to GM1 as well. It is equals to GM2 and GM1, both are equal only. So GM is equals to GM1 is equals to GM2. Did you understand this point or not? What is your GM2? GM2 is IC by VB. What is your GM1? That is also IC by VB. What would be your overall transconductance? Your overall transconductance would be IC 2 IC. 2 IC by V in. 2 IC by V in. V in is 2 VB. V in is 2 VB. So IC by VB, GM is equals to GM1 is equals to GM2. This is actually a gate question. In gate question, they did not specify what is VB. So there was a confusion. I couldn't understand what is VB. So this is not the exactly gate question. I modified it in my manner. Okay. So don't think that this is the gate question that I am dealing. You will find this question in gate PYQ as well. But that question was different. This question is different. Okay. So don't think that I have done this. I have given the wrong answer. That particular question is different. Well and good. Okay. In that case, I guess there was something that I did not know. They couldn't define VB potential accurately. Okay. So let's move to the next question. You have to find small signal voltage gain. Very easy question, but you have to find the exact answer. Okay. Exact gain. If this was the most, it would have been very easy. But you have to find the exact answer. How will you find? And there are no R naught, so you can take what you can take. You can take VA to be infinity. So let's take this circuit on the next page and we will solve it there. I must have given space. Yeah. So this is grounded. VCC will be grounded because we are doing the EC analysis. So this will be grounded. Now this is V0, this is 0. This is 0, this is V0. So in upward direction, here the current would be GM V0. Say yes or no. This current would be GM to V0. Do you agree to my point or not? This is V0, this is 0. Your VBE potential, your VBE for 2, that is equals to minus V0. So what will be your IC? IC will be minus GM VBE. That would be minus GM V0. So IC would be in downward direction. So in upward direction, I can take GM V0 current, IC2. In upward direction, you are having GM V0 current. So what would be the current here? What would be the current? IE current. If you have IC2, what will be your IE2? GM2 V0 I am writing. Okay. So minus GM2 V0 into beta 2 upon into beta 2 plus 1 upon beta 2. Say yes or no. This is your IE2 current, right? Now if this is V in, so what would be this current? This current would be GM1 into V in. Say yes or no. Because VB potential is V in. So this current, IC current would be GM1 into V in, right? And this current you have written, that is IE2 in upward direction. And this current is this. IE2, this is not IE2, this is IE2 because IE2 will be positive. Are you getting this point? What was my IC2? IC2 was this. This is my IC2. This is my IC2. And this I am making IE2. IE2. So my IE2 is negative. So my IE2 is equals to GM1 V in. Do you agree to my point? Look, what did I do? This is my V0 and this is grounded. So I have VBE potential equals to minus V0. So my IC current would be minus GM2 V0, or you can say in upward direction GM2 V0. If that is the current, if my IC2 is minus GM2 V0, that means what will be my IE2? That would be minus GM2 V0 into beta 2 plus 1 divided by beta 2. And now what will be this current? GM1 V in. So IE2 is equals to GM1 V in. So basically GM1 V in is equals to minus GM2 V0 into beta 2 plus 1 divided by beta 2. So what will be your V0 by V in? V0 by V in would be minus GM1 beta 2 divided by GM2 beta 2, or GM2 you can keep as it is. GM2 is there upon beta 2 plus 1. So what is the value of R pi we have? R pi is, because we don't want GM, we don't want beta. In final answer we don't want beta, so I need to replace beta. So R pi is beta upon Gm. So if I take Gm to upward, in final answer I don't want beta. So R pi equals to beta upon Gm. R pi 2 I need to replace anyhow. Beta 2 by Gm2 would be R pi 2 only. There is something wrong. Let me check. No, nothing is wrong. So beta 2 by Gm2 would be R pi 2, right? And here I can replace beta 2 as Gm2 R pi 2. Gm2 R pi 2. Look, this beta 2 by Gm2, this has become R pi 2. Beta 2 by Gm2 has become R pi 2. And this beta 2 is replaced by R pi 2 into Gm2 plus 1. So this is the voltage gain we are having. That's it. Minus Gm1 into R pi 2 divided by Gm2 R pi 2 plus 1. Gm1 R pi 2 divided by 1 plus Gm2 R pi 2. They asked the mode, so this would be the answer. They actually asked the mode value they asked. Gm1 R pi 2 upon Gm2 R pi 2 plus 1. Did you understand this question or not? This was a very good question. You need to find the relations. What was your IC2, what was your IE2, and what was your current in the Q1, IC1. So IC1 is equals to IE2, and that we equated. From there we got this relation. Now we need to replace. So what will be beta? So beta would be R pi into Gm. So these two things we replaced. Beta 2 by Gm2 is replaced with R pi 2, and beta 2 is replaced with R pi 2 into Gm2 plus 1. So this is the final answer. Well and good. Let's solve this question. This is the final question. Overall voltage gain you need to find. Okay. So if I need to find voltage gain, so what I will do, I will apply the AC analysis circuit I need to draw. AC circuit I need to draw. I am drawing it here. So this is gone. So what would be this current? This current would be Gm1 V in. Say yes or no? Because VB potential is V in. So this current is Gm1 V in. The same current is the base current of this one. Base current of this one. Do you agree to my point? The same current is the base current of this one. This node is V0. So what will be the base current? Base current will be V0 by R by 2. Base current would be V0 by R by 2. V0 by R by 2. So Gm1 V in. Gm1 V in is equals to V0 by R by 2. So what is your V0 by V in? That is equals to V0 by V in is Gm1 R by 2. That's it. This is the final answer. Did you understand this? This is your V0. What is the base current? V0 by R by 2. And this was the collector current. Gm1 V in. So Gm1 V in is equals to V0 by R by 2. We know only two models. First is the current in R pi, and the other one is the current in collector. So current in collector directly we can see here VB is V in. So Gm1 V in, and current in R pi, that would be V0 by R by 2. So V0 by R by 2 is equals to Gm1 V in. So V0 by V in is Gm1 R by 2. That's it. So that is it about the BJT amplifiers. So nothing apart from this would be asked. So you don't need to stress much about BJT amplifiers. It is very rare that they can ask this question, but anything can happen in gate examination, so they can ask anything. If I am talking about interviews, so in interview you will not expect these questions, okay, in interview or even in written test of placements. So in placements you will not expect these questions from BJT amplifiers, but certainly in gate examination it can come. Not certainly, there is 1% chance that in gate examination it can come. So that is more than enough for BJT amplifiers. The last video will be there on differential amplifier. So we will see the video on differential amplifier. You will be able to analyze the complete differential amplifier on your own. We are going to see only the AC analysis. DC analysis we have already studied in some of the question of biasing only. So we are going to see only the AC analysis, and you will be able to analyze that on your own. We will be able to write down the gain. It will be same as MOSFET amplifier. Well and good. So in the next video we will see that. Okay then, thank you.
Hi everyone. So in this video we are going to study differential amplifier using BJTs. So we have already seen differential amplifier in a very in-depth manner, but using MOSFETs. So there we saw why do we use differential amplifier, what is the issue in the biasing, what is the issue in the supply. Then we saw what is differential gain, what is common mode gain, what is common mode differential gain, what is CMRR. So everything we have already seen in very in-depth manner. Here we are only going to do the analysis. Just for the analysis purpose we are dealing this particular topic here, because concept is the same. For BJT MOSFET concept is the same, but the analysis is different. So that we are going to do here. Also, we are not going to see the DC analysis. We are not going to see the large signal model, because large signal we have already seen in the biasing chapter. In one of the assignment we dealt two questions there, right? That was based on your this differential amplifier only. So we have seen the large signal analysis. Only small signal analysis we are going to see for different differential amplifier circuits that I have drawn here. So for all these circuits we will see the small signal analysis, AC analysis. Well and good. Okay. Now let's start with the first circuit. But there I have written this thing: dual input balanced output. So this is a very famous term. I did not introduce this term when we were studying MOSFETs, right? In when we were studying differential amplifier using MOSFETs, we did not introduce this term, dual input balanced output. But this is a very famous term when they are taking BJTs. If they are talking about BJTs, you will get to see this term dual input balanced output. So what do they mean by that? Dual input means you have applied two inputs, and balanced output means you are collecting your output from both of the terminals. Dual input balanced output, that means you are collecting your output from both of the terminals and then taking a difference. Dual input balanced output. And what about dual input unbalanced output? So there will be this term as well, dual input unbalanced output. So what does that mean? You are collecting your output from one of the end only. Input is dual, but you are collecting your output from one of the end only. So sometimes in the examination that is very rare, because I don't think they are going to ask question from BJT differential amplifier. But still, if they ask, sometimes they can just write in the theory that dual input and balanced output. This they can write sometimes only in theory. So you should be able to understand what do they mean by dual input and balanced output. So there should be no confusion. Okay, so let's start with the first circuit. You have to analyze this one. So there is a current source as a tail. We will connect current source as a tail. We will connect a resistance as a tail. Okay. So first we need to find the differential gain. So what do you mean by differential gain? This current source will be open circuited, right? This current source will be open circuited because we are doing the AC analysis. If we are doing the AC analysis, this will be open circuited. And what about this DC bias? This will go to ground, right? This will go to ground. And what about the inputs? Input will be applied V in by 2 and minus V in by 2. V in by 2 and minus V in by 2. So what will happen to this node? If this increases, if V in increases, that means minus V in by 2 goes down. If V in increases, then this node goes down. If this increases, then this node increases. Because from here to here, there is 0 degree inversion. And if this node decreases, then again from here to here, there is 0 degree inversion. So this node decreases. So this node is increasing and decreasing. So eventually it will be ground only, right? We don't need to analyze anything here. We don't need to do any AC analysis. We can intuitively tell why this will be ground. Because if this is increasing, this will increase. If this is decreasing, this will decrease. If this increases, this would decrease, and this would increase. So one particular node from 0 to up it is going, from 0 to down it is going. That means it will stay at 0 only. Well and good. Also, how you can see it with the concept of half circuit, because circuit is symmetric. If the circuit is symmetric, then you can apply the concept of half circuit. And for differential input, if you are applying the concept of half circuit, that means this particular node, wherever it cuts the circuit, that will be grounded. So this particular node will be grounded. No doubt about it, because we have already seen these kind of concepts in MOSFET differential amplifier, right? Half circuit, in case of differential gain, if both inputs are negative of each other, then this will be grounded. In case of common mode gain, this will be open circuited. Well and good. Okay. What is this node? This node I can call V02, and this node I can call V01. So what will be your V01? What do you think? Here your VB is fixed. VBE is fixed, that is equals to V in by 2, because base is at V in by 2 and emitter is at 0. So your VBE is fixed. So what do you think? What will be your V01? Your V01 will simply be minus GM RC into V in by 2. And what about your V02? V02 would be GMRC. Again, you can say minus GMRC into minus V in by 2 because your VB is minus V in by 2. So it would be GMRC V in by 2. Right? So what will be your final V naught? V naught would be V naught 2 minus V naught 1. V naught 2 minus V naught 1. V naught 2 minus V naught 1. So that would be GMRC V in. So what will be your differential gain now? Differential gain, I can write AD, that is V naught by V in, that is simply equals to GMRC. It is the same as BJTs. GMRD was there, here it is GMRC. Let's calculate common mode differential gain. Because what is your CMRR? CMRR is differential gain divided by common mode gain. Sorry, differential gain divided by common mode differential gain. If you remember CMRR, what is your CMRR? Differential gain divided by common mode differential gain, right? You remember, this is your CMRR. So for calculating common mode differential gain, what you will do? You will apply VCM as the input. You will apply VCM as the input. VCM as the input, and these will be gone. These will be grounded because we are doing the AC analysis. And this node is V01 and this node is V02. And what I am going to do, I am going to apply the concept of half circuit. If I apply the concept of half circuit, what will happen to this node? This node will be open circuited. And if this node is open circuited, what will happen to this node? This will be open circuited. And if this node is open circuited, that means here the current is 0 amp. Also here also the current is 0 amp. If these currents are 0 amp, then what do you think? What will be your V02 and V01 equals to 0 because the currents are 0 amp. So V02, V01 is equals to 0. So what will be your common mode differential gain? Because if your output is 0, because what do you actually calculate in common mode differential gain? You take the difference of output, not the average. In case of common mode gain, we take the average of output. But in case of common mode differential gain, we take the difference. Right? I hope you remember it. So we are taking the difference, that would be 0 only. So I will write V02 minus V01 divided by VCM. That would be 0. So your common mode differential gain is 0. So what is your CMRR here? CMRR is infinity. CMRR is infinity. CMRR is infinity. Well and good. So sometimes they can ask, differential amplifier with current source as a tail, what will be the CMRR? Infinity. Differential amplifier, current source as a tail, CMRR will be infinity. Well and good. Let's see the other one. Now the resistance is at the tail. We are using resistance as a tail. So we can again analyze these kind of circuits, right? What do we calculate? First we will calculate differential. So let's calculate the differential gain now. So for finding differential gain, what we will do? This will be shorted. This will also be shorted. Right? This will be shorted. This will also be shorted. And your input here, it would be V in by 2. And this would be minus V in by 2. Well and good. And what will happen to this RE? This RE will be replaced with two parallel combination of 2 RE. Why I am doing this? Because I am going to apply the concept of half circuit. That's why I am doing this thing. I am going to apply the concept of half circuit now. So now the circuit looks symmetric. So what I can do? I can simply divide it like this. And since we are finding differential gain, then what will happen to this node? This node will be grounded, right? This node where it cuts, that would go to ground. If that goes to ground, then what will be the equivalent circuit? The equivalent circuit will be something like this. Something like this. V in by 2. And this is RC. This is your VO1. Right? So you know one thing, from the half circuit itself, you can write the complete differential gain. From the half circuit itself, whatever the gain you are getting for half circuit, that would be your complete differential gain. So what will be your complete differential gain? That would be minus GMRC. Okay. Or if you don't understand by this thing, if it is not like ये बात हजम नहीं हो रही आपको, so what you will do? What will be your VO1? VO1 would be minus GMRC V in by 2. Say yes or no? what would be your VO2? What would be your VO2? Better we should write it in good manner only. So what will be your VO1? VO1 would be minus GMRC into Vin by 2. And what would be your VO2? VO2 would be GMRC into Vin by 2, right? Because input will be simply minus Vin by 2. So what would be your VO? VO would be GMRC into Vin. And what is your differential input? Differential input is equals to Vin only. So what will be your gain? Gain will simply be GMRC only. That's it. Or if you remember one thing, I told you, whatever the gain is there for a single side, whatever the gain that is there after applying the concept of half circuit, that would be the final gain. Right? This is what I have told you. Let's find the common mode gain now. For common mode gain, what will happen? This will go to VCM. This will go to VCM. Again, I need to apply the concept of half circuit. So what I will do? I will replace this one with 2RE and this one also with 2RE. Right? I need to apply the concept of half circuit. So this will be gone. This is your VO1. This is your VO2. So how will your half circuit look like? And VCC, certainly these will be grounded. Certainly these will be grounded. So how will your circuit look like? This is RC. This is 2RE. This is VCM. This is VO1. And this is your RC. So whatever the gain I will have for one side, that would be the final gain. Right? Here did I put negative sign here? No, here the negative sign should not be there because you are calculating. If this is your Vin by 2, this is your VO1. Are you getting this point? If this is Vin by 2, you are calculating the opposite output from here to here, and you are applying your input from here to here. So for opposite output, it will be positive only, and here also we can verify it will be positive, right? So sometimes people get confused in the sign. So what people prefer is they will find VO1 and VO2 separately. Now the circuit is same, so VO1 and VO2 will be same only, right? The circuit is same, so VO1 and VO2 will be same only. Are you getting this point? VO1 and VO2 will be same because the circuit is completely symmetric. But yeah, let's find VO1 first. Let's find VO1. So how will you find VO1? So for finding VO1, what do I need? What do I know? If this is your IC, so what would be my VO1? That would be minus IC into RC. Generally, people remember the formula of VO1, but we don't need to remember. In the examination, within 1 minute, we will be able to derive it. Within 1 minute or less than 1 minute. Now, what will you will write? VCM is equals to what? VCM is equals to from R pi what current is flowing? From R pi IB current is flowing, right? And from RE how much current is flowing? From RE IE current is flowing. Now people can have one doubt that sir, if this was my circuit, then from RE to IE current is flowing because from here IE current is coming and from here IE current is coming. That is right. From RE to IE current is flowing, but you have made your half circuit. No, you have made your half circuit like this. Now from to RE only IE current is flowing. Are you getting this point? If I had replaced this 2RE, if I had replaced this RE with 2RE, and from here to IE current is coming. So how much current would have been going here? This is 2RE, this is also 2RE. IE current only, right? IE current only. So 2RE will take IE current only, not 2IE. Yeah. So R pi into IB and 2RE is taking IE current. So 2RE into IE. What is IE? IE is beta plus 1 IB. IE is beta plus 1 IB. So what is your IB? IB is VCM divided by R pi plus 2RE into beta plus 1. Right? So what will be your IC? IC will be beta times of IB. Right? This is your IC. So what will be your VO1? VO1 is minus beta RC into VCM divided by r pi upon divided by r pi plus 2 re into beta plus 1. So this is your VO1. You don't need to mug it up. You don't need to mug it up at all, right? And same will be your VO2. So I need to add a page now. Same will be your VO2. What will be your VO2? VO2 will be exactly the same because the circuit is exactly same. Minus beta RC VCM divided by RE plus, sorry, R pi plus 2 RE into beta plus 1. Right? What is your common mode input? Common mode input is VCM only. VCM only. What is your common mode output? Common mode differential output. That would be VO2 minus VO1. That would be VO2 minus VO1. VO2 minus VO1. So what would be your VO2 minus VO1? 0 only. So because both are same. So what is your common mode differential gain? Since output is 0, so it would be 0 only. So common mode differential gain is 0. We can find common mode gain as well. We can find common mode gain as well. For finding common mode gain, what do? We take the differential input that is equals to VCM only. For output, what do? Common mode output. We take the average VO1 plus VO2 divided by 2. VO1 plus VO2 divided by 2. So what will be the average of this one? This only because VO2 and VO1 are VO2 and VO1 are equal only. So what will be the average? This will be the average. Minus beta RC VCM upon R pi plus 2 RE into beta plus 1. Okay, so this is your common mode gain. Okay. What is CMRR? CMRR is actually differential gain divided by common mode gain. Do you agree to my point? Sorry, differential gain divided by common mode differential gain. You agree to my point, right? This will be infinity. This should be infinity. But what happens is that in older GATE question paper, in GATE 2014 and in GATE 2009, they asked the same circuit and they said that if you change RE, what will be the change in CMRR? What was the question? This was the same circuit. This was the same circuit. And the question was, if you change RE, what will be the change in CMRR? What will be the change? No change should be there, no. Because CMRR is not AD by AC. CMRR is AD by ACM DM. Differential gain divided by common mode differential gain. Since VO2 and VO1 are equal, then common mode differential gain is 0. Then CMRR is infinity, irrespective of the value of RE. Are you getting this point? But in the options, no option was there where it said that there will be no change. In the option, they consider that your CMRR is differential gain divided by common mode gain. So based on that, you needed to reply. Based on that, you needed to mark your answer. So we will deal that question. So sometimes it may happen in the examination as well that your CMRR can be taken as differential gain divided by common mode gain. But they will define the CMRR there. Okay. Differential gain divided by common mode gain. Ideally, what is CMRR? CMRR is differential gain divided by common mode differential gain. This is what CMRR is. But in the examination, they can redefine it. So you should be able to know the common mode gain as well. That's why we solved common mode equation here as well. Okay. So we have done the analysis, but sometimes in the examination, it may come that if you change RE, what will happen? So if you increase RE, if RE is increased, then what will happen? Your common mode gain will decrease, right? But you cannot comment on CMRR. If CMRR is defined as differential gain divided by common mode gain, then if RE increases, then what will happen? ACM will go down. If RE increases, then ACM will go down, and then CMRR would increase. But ideally, CMRR should not change because that would always be infinity. Well and good. Let's move towards the next circuit. Now we are going to see dual input and single-ended output. So here in this case, what will be your output? Your differential output. In this case, your differential output, your common mode output, your common mode differential output, all will be same and will be equals to V naught only, because you are calculating only one output. No, you are calculating only one output. There is no difference you can take. There is no average you can take. So differential output, common mode output, and common mode differential output all will be same, will be equals to V naught. This is the terminology. This is how it is taken. If I am asking, find the differential gain for this circuit. Find the differential gain for this circuit. So what you are going to do? You are going to apply V in by 2 here. You are going to apply minus V in by 2 here. They will define what is the input. They will give this one as positive and this one as negative. They will give it in the question. So you will put V in by 2 here, minus V in by 2 here, and these will be grounded. These will be grounded, right? If it is V in by 2, if this is minus V in by 2, where will this node go? This node will be grounded only. Where will this node go? This node will be grounded. So what will be your V out? V out would be GMRC into V in by 2. GMRC into V in by 2. And what will be your differential input? This is your differential output. That is equals to V naught only. That would be GMRC V in by 2. You can calculate. If this node goes to ground, this would be, the current would be flowing in the upward direction. That would be GM V in by 2. So the output would be GMRC into V in by 2. And what is your differential input? That is V in only. So what will be your gain? Differential gain. That would be GMRC by 2. So here your differential gain would be GMRC by 2. Right? Now if I am asking calculate common mode gain or common mode differential gain, both will be same only. Are you getting this point? Common mode gain slash common mode differential gain slash common mode differential gain. Why is it so? Why both will be same? Because input for both of them is the same only. What is the input for common mode gain and common mode differential gain? That is VCM. For output, there are differences. In case of common mode gain, we take the average. In case of differential gain, we take the difference. But in this case, only one output is defined. So both of them, for both of them, output will be same. If output is same, input is same, then certainly gain will be same. So common mode differential gain. Common mode differential gain. So for this, you will take this as VCM, this also as VCM. Right? You can certainly apply the concept of half circuit. How will you apply the concept of half circuit? This will be your 2RE. And this will also be your 2RE. If you apply the concept of half circuit, what will happen? This will be broken here and this will be open circuited. This will be open circuited. So what will be your VO? VO, do I remember the formula? Let's check. So your VO is beta RC upon, I don't need to remember it, but yeah, I am trying to see if I remember it. Beta RC upon R pi plus 2RE into beta plus 1. Yeah, I have good memory. So this is your VO. VO. This is your VO. So what will be your gain? Gain will be, you can say common mode gain, or that would be equals to common mode differential gain. That would be beta RC upon R pi plus 2RE into beta plus 1. Okay, right? Let's move back. What you can write this one as well. GMRC by 2. What is beta? Beta is equals to R pi upon GM. So you can write what GM would be equals to R pi equals to beta upon GM. What I am doing here. R pi equals to beta upon GM. R pi equals to beta upon GM. So GM would be equals to beta by R pi. GM would be equals to beta by R pi. So what you can write? Beta RC by 2 R pi. Right? So what would be your CMRR? CMRR would be differential gain upon common mode differential gain. That would be, what is differential gain? Beta RC upon R pi. Beta RC upon 2 R pi. Beta RC upon 2 R pi. 2 R pi. And just the reciprocal of this, that would be R pi plus 2 RE into beta plus 1 divided by beta RC. Beta RC and beta RC will get cancelled. Beta RC and beta RC will get cancelled, right? So what would be your CMRR? From here you can check. Beta RC and beta RC is getting cancelled. So it would be, and R pi will be divided by this. So 1 by 2 plus RE upon R pi. RE upon R pi into beta plus 1. This is your CMRR. I should write it on the next page. Okay, let's write it on the next page. I will add up a page. Page is already added. So what is happening is that this R pi is upward. Did I write the gain correctly? Yeah. 2 RE into beta plus 1. Now this went upward. Beta RC upon 2 R pi. Beta RC upon 2 R pi. And this got cancelled. Now this would be 1 by 2 plus CMRR would be 1 by 2 plus 1 by 2 plus RE by R pi, RE by R pi into beta plus 1, right? So CMRR would be what? This 1 by 2 will be a very lesser value because beta is generally very high. And what you can put beta upon R pi. What is beta upon R pi? That is equals to GM. Beta upon R pi is equals to GM. And beta plus 1 can be approximated to beta only, right? Beta plus 1 can be approximated to beta. So this can be replaced with GM into RE. So 1 by 2 plus GM into RE. And generally GM into RE value will be higher than 1 by 2. So your CMRR can be approximated to GM RE. So in this case, when you are calculating the single-ended output, it can be approximated to GM RE, right? This is also an approximation. This was the exact one. Then after the approximation, you got GMRE. Well and good. So this is the differential gain. Now this much concept is more than enough. You have the tendency to analyze the circuit, whatever that is coming in front of you. Let's see the questions now. So this was the question coming in GATE 2014 examination. What they are asking, they are talking about common mode rejection ratio. What is common mode rejection ratio for this circuit? Because what will happen to this I naught? This I naught will be open circuited. Right? And if you apply here, what they are saying that here you are calculating the magnitude of common mode gain and differential gain. Common mode gain and differential mode gains. So they are defining CMRR as AD by AC. AD by AC. Because what is the ideal scene? This circuit we have already solved. Here, I told you when we were solving this circuit. Where is that circuit? Yeah, this is the circuit. No, RE is there, no? RE is there. Yeah. So this is the circuit. Here our AD was GMRC and our common mode gain was this one. Common mode gain was this thing. Common mode differential gain was 0 and this was our common mode gain. Then I told you that CMRR is infinity here, irrespective of the value of RE. But what they are asking in the question? In the question they are saying if RE resistance is increased, then what will happen to ACM, AD, common mode rejection ratio and common mode rejection ratio? Okay, yeah. So what will happen to AD, AC and common mode rejection ratio? So do we remember the formula? No, we don't remember the formula, but we can derive it in the examination. Directly we can see what is our AD. AD would be GMRC. What would be our AC? That would be beta RC upon because both of the side we are having the same game, so it would be beta RC upon R pi plus 2 into beta plus 1 into R. Right? This would be Wait a second. Yeah, okay, fine. Yeah, so this would be our AC. So if your RE increases, if RE is increased, then what will happen to AC? AC will go down. And if AC will go down, and there will be no change in, no change, no change, no change in AD, right? There will be no change in AD. So does any option matches? We need to check if any option matches. AD should no change. Sorry, in AD there should be no change. And ACM should decrease. The common mode gain should decrease. Now what are the two options left? These are the two options left. That common mode ratio should increase or decrease. Ideally, it should be constant. It should be not constant, it should be infinity only. It should be the same only. Ideally, irrespective of RE value, CMRR should be infinity. But here, this is not the case. You have to pick one of the option. So common mode ratio increases or decreases. So then I thought that they are defining CMRR as this thing. Actually, your CMRR is not AD by AC. It is AD by ACM DM. AD by common mode differential gain. Common mode differential gain divided by common mode differential gain. That is your CMRR. But that is not available in your option. So for that, you need to check AD by AC. So if you do AD by AC, what will happen to CMRR? CMRR will rise, right? Because if AC is decreasing, then CMRR will rise. So CMRR increases. Common mode ratio increases. And this question has been asked twice in the GATE examination. That's why some people say that it is AD by AC. No. As a designer, ideally it is AD by ACM DM, not AD by AC. Because in AC, we are taking the average of the output. But if you are calculating ACM DM, you are taking the difference. So if you are taking the difference, that would be 0 and CMRR would be infinity only. But in this case, they are defining it as AD by AC, where AC is the average of the two outputs that you are taking when you are applying common mode input. Right? So you should be able to do this kind of question in the examination. In the interview, they will not ask you these kind of steps because they also know that it is absolutely needless because CMRR is the definition of CMRR is something different, right? So yeah, these kind of questions you shouldn't be getting confused in the examination. You just need to pick the option what the question setter would have thought in the manner what question paper setter would have thought, right? Let's move towards the next. Yeah, so let's solve this question. Very easy question. Q1, Q2 are given. Small signal input voltage is given. Other node is grounded here. VB is given. So these circuit is given. This circuit is given. VB is 0.7. Beta is 100. R1, R2, R3 value are defined. VT value is defined. Collector current through Q3 is 2 milliampere. Collector current through Q3 is 2 milliampere. This is 1 kilo. And this is 2 milliampere current. This is 2 milliampere current. So what will be the drop here? 2 milliampere into 1 kilo ohm. This will be 2 volt. So what will be this potential? This potential will be minus 10 volt. And here VB is 0.7. So what would be your VB? VB would be minus 10 plus 0.7. That would be minus 9.3 volt. Minus 10 plus 0.7 minus 9.3 volt. This would be your VB. Okay, what did you get to know? There was 2 milliampere current. Okay, collector current was 2 milliampere current, although this current was 2 milliampere. Okay. Nearly emitter current would be 2 milliampere only, right? It would be somewhat greater than 2 milliampere. It could be 2.01 milliampere or 2.1 milliampere. But here in the option, you can see that there is huge difference in the options. So we can take nearly it would be 2 milliampere. Emitter current would also be 2 milliampere. So that would give the drop of 2 volt. So minus 12 plus 2 minus 10 plus 0.7 minus 9.3. This is your VB. Now what you need to find? You need to find small signal voltage gain. Small signal voltage gain. So for that, I have to redraw the circuit, I guess. Okay, if we are finding small signal voltage gain, what will happen? This VB will go to ground. This VB will go to ground. If I am finding small signal voltage gain, this VB will go to ground. Okay. Okay, let me draw the circuit, then I will analyze it. Yeah, so this will be the small signal circuit, and where you are collecting the output, you are collecting the output here. You need to find small signal voltage gain. Tell me one thing, what will happen to this one? This will simply be open circuited. Why is it so? Let's just assume this node is grounded because this was a DC bias. This node would become ground. This particular node would become ground, right? Let's just say some small signal voltage is coming here. Some small signal Vx is coming. That you don't know what is that small signal voltage, but you are assuming some small signal Vx potential is coming. Okay. So what will be the current in upward direction? That would be GMVx. And what would be the current in downward direction? Let's just call this resistance as R3. This is R3. So what would be the current in downward direction? That would be Vx by R3. Both current will be equal. Look, there is no R naught. Va is infinity. So I don't know if there can be some Vx potential. There can be some non-zero Vx potential. I am assuming there is a small signal voltage, that is Vx, which is non-zero. I don't know what is the potential of that. So if I assume that to be non-zero, then Gm Vx is equals to negative of minus Vx by 3. From here, what do you get to know? Vx is equals to 0 only. So first I thought that this would be some potential, but this is actually 0. This node is actually going towards 0. Okay, this is actually grounded. If this is grounded, if this node is grounded, then how much current this will drive? 0 amp. Eventually, this will drive 0 amp current. And if this is driving 0 amp current, that means this will simply be open circuited. This will simply be open circuited. Now you need to find small signal voltage gain. You need to find small signal voltage gain of this circuit. Tell me one thing, where will this node go? What will be the potential of this node? If you have studied MOS amplifier in an in-depth manner, you will be able to analyze it. If you have studied MOS amplifier in an in-depth manner, you will be able to analyze it. Don't mess it up, do it on your own. Where this node will go? Vin by 2. Right? Say yes or no? Okay, let's start. If this is driving IB current, if this was MOS, then what would have been your answer? If this was MOS, if this was the MOS circuit, because there is high probability that this question can be asked with MOS circuit. So if this was MOS, what will be this node? It will be Vin by 2. Why so? Because you will say that, sir, this is Vin, and from here we see 1 by Gm resistance and another 1 by Gm resistance we see. Another 1 by Gm is grounded. So this is 1 by Gm and this is also 1 by Gm. So simply we can divide the potential. This would be Vin by 2. Vin 1 by Gm, 1 by Gm. That's it. But this is BJT and we are going to do the exact analysis. So let's do the exact analysis. This is your IB. What will be this current? IE. Now the same current will flow here, no? IE in this direction. Now you will say that, sir, how emitter current is flowing in upward direction? Because it cannot drive current in the upward direction. This is a small signal current. It can flow in upward direction. It can flow in any direction. In MOS, what did we show? That ID current is flowing in upward direction. Why is it so? Small signal ID current. Because the current is small, so it can flow. Because this IE current has no other path, it has to flow like this. If this is your IE, what this would be? This would be your IB. Say yes or no. Now what you can say? Sir, this is my Vin. From Vin to emitter, from the Vin to this node I am calling X. From Vin to X node, from Vin to X, what do I see? R pi. From Vin to X, I see R pi, and in that R pi, IB current is flowing. Now come to this X. This was your X. From X to ground, this is again your VBE. So from X to ground, again I see one more R pi. Again I see one more R pi. And this node is also grounded. And what is the current in this one? IB current. That is going into ground. IB current that is going into ground. So where will this X node go? What will be the potential of X node? This is simply becoming a series RC circuit. What will be the potential of this node? You can simply divide. You can simply apply potential division. Why you can apply potential division? Because both of the resistors are having the same current. Both of the resistors are having same IB current. So you can simply apply potential division. So where X will go? X will go to Vn by 2. So directly, just by looking at the circuit, you will be able to tell, sir, where this X node will go. It will go to Vn by 2. Right? In case of MOS circuit as well, in case of BJT circuit as well. If one of the node is grounded, it will go to Vn by 2. If this node was at Vn, then this node would go to 0. But if other node is grounded, you cannot apply the concept of half circuit here. You cannot say that this node is increasing, then this node will go to 0. Nah, because what is happening to this node? You don't even know. So if this node is increasing, that is Vn, this node will be Vn by 2. So this particular node is Vn by 2. So how much current it will drive in upward direction? That would be Gm Vn by 2. Say yes or no. The current in upward direction would be Gm Vn by 2. Are you agreeing to this point? The current in upward direction would be Gm Vn by 2. So what will be your V naught? Your V naught would be, why it is Gm Vn by 2? Because VEB is minus Vn. So that would drive minus Gm Vn by 2 current in downward direction. What is your VBE? That is minus Vn by 2. and that would drive minus GM V in by 2 current in downward direction. So in upward direction, the current would be GM V in by 2. Or directly by the method, you can see where we will always take current in the positive direction. So from V in by 2 to 0, so current would be in this one, right? GM V in by 2. So what would be your V naught? Your V naught would be GM into V in by 2 into 1 kilo. This would be your V naught. Positive sign will be there, right? There will be positive sign. Now your target is to find GM value. Your target is to find GM value. So what will be your GM? What do you think? How much current was there? 2 milliampere. So how much current would have been here? 1 milliampere, right? IC current would have been 1 milliampere. IC current would have been 1 milliampere. So what will be your GM? GM would be IC by VT. Why I am saying it would be 1 milliampere? Now no one will say that, sir, this node is at high potential, this node is at lower potential, so this will drive all the 2 milliampere current. If you are saying this, you are messing it up. You are messing it up big, right? ऐसी चीजें नहीं बोलनी है. V needs small signal. V needs small signal. So here this node is also grounded. This node is also grounded. This node is also grounded. When we are doing the DC analysis, if you are doing the DC analysis, this node is also grounded and both of the nodes are grounded when you are doing the DC analysis. And both of them are having the same potential, that is 0.7. VB is equal to 0.7. So both will drive the current. This 2 milliampere will have to flow from Q1 and Q2. Both will drive 1 milliampere current. Where Q1, if I talk about Q1, DC circuit of Q1, this node will be ground. This node will be at minus 0.7 and this node will be at some potential that we don't know. Both will drive the current. This will be at some potential that I can tell 12 into 1 into 1. This will be at 11 volt. So this potential will be at 11 volts. So this will be in active region and driving 1 milliampere current. It's driving 1 milliampere current. So certainly both of them will be on. If this was the scene that DC potential here was 2.5 and DC potential here was grounded, so this will take up all the 2 milliampere current. But in case of DC analysis, both are grounded. So you should have the crystal clear concept, which is small signal, why it is driving this much of current. Crystal clear concept is there. That in case of DC analysis, both are grounded only. So both are driving 1 milliampere current. So IC is 1 milliampere. IC is 1 milliampere. So what will be your GM is IC by VT divided by 26 or 25. 25. So 25. So GM is 1 by 25. So GM value is 1 by 25. So what is your voltage gain? V naught by V in. 1 by 50 into 1000. That would be 20. The voltage gain is 20. Somewhere you will see answer is minus 40, whatever they have given. That is absolutely wrong. This answer is absolutely correct. Because they will just mug up the formula and I don't know from where they will get this answer. They will mug up the formula, they will apply it. In a lot of coaching I have seen they have given minus 40 as the answer by applying some formulas. But we did not apply any formula. In the examination, within 1 minute we will be able to solve it. Because we will know this will go to open circuit. This node will be V in by 2. So GM V in by 2 current would be flowing upward. So gain would be GM by 2 into 1 kilo ohm. What is the value of GM? GM is, this will drive 1 milliampere current, this will drive 1 milliampere current. So both are driving 1 milliampere current. So GM would be 1 by 25. That's it. So GM is 1 by 25. So 1 by 25 by 2, 1 by 50 into 1 kilo ohm. 1 by 50 into 1 kilo ohm, AV would be 20 volt per volt. I know what they would have taken is that they would see, okay, here V in is applied, here ground is applied. So this will take all the 2 milliampere current. So they write the GM value as 2 by 25. I think this is what they have done. Then only you will get minus 40 as answer. And from where you will get negative sign, that I don't know. The sign would be positive, right? Also, how you can check sign would be positive. Intuitively, if you need to check what will be the sign, how will you check? You will check if this node goes up, if V in goes up, then this node goes up. Because this is a common collector amplifier. Common collector. So if we study from the most point of view, if gate goes up, source goes up. And if source goes up, this node will also go up. This node go up, this node go up, this node will also go up. So this is how also you can check. If this node is going up, this node will also go up. That means there is 0 degree phase shift. From here to here, there is 0 degree phase shift. If there is 0 degree phase shift, that means the sign will be positive. Why they are taking negative, that I don't know. But here the answer is, correct answer is plus 20. No one can stop it. Well and good. So that is the complete concept of our BJT differential amplifier. So you have studied differential amplifier in a very good manner now. Okay, so you will be able to solve every single question that can come to in your examination. But there is a very rare chance that they will ask questions from BJT differential amplifier. But certainly, I am hopeful there will be one question from MOSFET differential amplifier, and that would be very good. Those who have studied in in-depth manner, that guy only will be able to solve it. Those who are remembering the formula, eventually they will forget the formula or they will mess it up, right? So yeah, let's move to our next concept, that is feedback topology, which is same as MOSFET, completely same as MOSFET. Feedback topology completely same as MOSFET. Okay, so you need to comment on feedback topology. Do you remember the feedback topology? Voltage, 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 current, current, voltage, current, current. So tell me what kind of feedback topology is there. In case of input, what is the scene? In input, there is mixing. In input, there is mixing, right? And in output, there is sampling. So what is being sampled here? So I got a trick. First, you need to analyze the feedback. What is the feedback? This is the feedback. This is the feedback, no? R dash is the feedback. So from feedback, if your output is directly connected, then it will be voltage sampling. That's it. From feedback, if your output is directly connected, feedback output directly connected. What I am saying, feedback output connected. This would be voltage sampling. And what about input? There is current mixing surely, because this is your input. Current has two paths to be mixed. This path and this path. So current has two paths. So current mixing. Current mixing. So what kind of feedback topology is there? Current voltage. Current voltage. Other names also you can write. I am keeping it up to you. What will be the other names? We need to think. Okay. So let's write it in series, shunt. In that manner we will write. So in case of okay, current mixing at input side there is mixing. So sampling at the output side. So voltage current it is. Voltage current. It is voltage current. Okay, it is voltage current. Because output is sampling, input is mixing. So we always write output input manner. But in case of series shunt series, we write input output manner. So current mixing, current is mixed in shunt. And voltage sampling, voltage is sample in shunt. So it is shunt. It is shunt. This is the other name, right? Third name also you can write. What will be the third name? First of this, second of this, voltage shunt. This is also written in output input manner. So third name would be voltage shunt. Well and good. Let's move towards the next one. What kind of feedback topology is there? Where is the feedback? This is the feedback, right? This is the feedback. Where is the feedback? This is the feedback. In this one, where is the feedback? This is the feedback only. This is the feedback, right? So output and feedback are directly connected. Output and feedback are directly connected. No. So what kind of sampling is there? Current sampling. Current sampling. Practically, not theoretically, intuitively, how will you tell? Not intuitively, conceptually, how will you tell? There will be some I out current flowing through it that would give a drop of I naught into RE, and that will be mixed with the input, right? That will be mixed with the input voltage. Also, what you can see here, the current has no path to separate. If this is the input current, it has no other path to mix. So this is voltage sampling, voltage mixing, and here you can directly see. This is V in minus I naught into RE, that would be your VB, and that would generate some current here, right? So yeah. So what kind of feedback topology is this one? Current voltage. Current voltage. Here output is directly connected to feedback, so this is voltage sampling. And what about mixing? Current has no other path, so it is current mixing. Sorry, voltage mixing. Sorry. because current has no other path. So this is voltage. This was current voltage. This would be voltage. You can write down the other names as well. I'm leaving it up to you, right? What about this one? Is this the last? Yeah, this is the last. What about this one? Where is the feedback? You can say this will be the feedback. This is the feedback. This is the feedback. So output is directly connected to feedback? Yes, it is connected. And what about input current? Input current has two paths, this path and this path. So from output is directly connected, so voltage sampling. And what about current? Current mixing. So this is what? Voltage current. Voltage current. Well and good. So this is the final answer. You should be able to tell the final answer on your own. Current, voltage, because here the current is being mixed. Sorry, current is being sampled. Here what was sampled? Voltage is being sampled because feedback is directly connected to output. This is your feedback. And current has two paths to flow. So it would be current mixing, voltage sampling. Here this would be current sampling, voltage mixing, and this would be voltage sampling, voltage mixing, and this would be voltage sampling, current mixing. Well and good. So these are the examples. You must have understood the concept of feedback topology here. So now your syllabus is completed. You have completed the BJT circuits as well. Now you can go to CMOS inverter as well. You can study CMOS inverter. Certainly that is a very, very good concept. You can certainly study CMOS inverter. Well and good. Okay then. Thank you very much.